Hello.
Hello, Kung Fu.
Yes, hello. Let me try out the sharing my screen.
Okay. Let me stop first.
Yeah, so, yeah. Do you see the screen? Do you see my slide?
I see. Yeah, I can see it.
Okay. So it seems to be working.
It's work well. Okay.
Okay. So looks good to me. So in order to share the screen, the one that the person who's sharing the screen now has to stop sharing it first? Or
Yeah, I think it's, we need to stop share first, so
okay,
the
so
section share need to remind.
Stop sharing, and then someone else can share the screen.
Yeah, I think it's.
I think.
But the co-host may have right to just
Override?
switch it.
Okay, co-host can just make override the decision.
Yeah.
I see. Maybe I'll stop sharing. Okay.
Okay, so let me share the part.
So what's the number of attendees so far? Registrations?
Now is six people, 6 participants.
No.
Eight.
Who already signed up for the registration?
Oh, it's about 300.
300? Wow, this is good.
Yeah.
Maybe because it's free, or it, or
Yeah, maybe it's free. So.
And then maybe because it's the program is really good.
Yeah.
Okay, that's good.
교수님,
예, 안녕하세요.
네, 안녕하세요.
네.
이거 슬라이드 어떻게 공유했더라?
아, 밑에 보시면은 화면 공유라는 게 있습니다. 밑에 그 버튼들이 있거든요.
예.
네, 보면 화면 공유. So you might want to try out sharing the screen. Okay, looks good. Okay, yeah, I see it.
됐어요?
Yeah, looks good.
Today what I'm going to talk about is learning to make decision optimally for self-driving network. My
Sounds
name is
good.
Song. Yeah. Can you hear me clearly?
Yes, I can hear you. So we have about 17 people join the Zoom streaming. But General Chair isn't here. Okay.
Who's going to introduce me? You or General Chair?
Yeah, I'm going
Who's
to introduce
session
you.
chair?
So but we have 10 minutes before your talk. We're going to have an opening remark for 10 minutes.
Okay.
So it's just
So my talk will start at 9:10, right?
Yeah, 9:10 in Korean time.
So when are you going to come back to Korea?
I don't know. So I'm just monitoring what's happening here. So if in the fall semester, if everything is shut down again, I'll really seriously reconsider going back to Korea.
Oh, really? It's
It
very
was getting
unfortunate.
better in Massachusetts, but recently it's getting slightly worse. So other states.
Worse in what sense?
I'm sorry, can you say that again?
Worse in what sense? Worse in what sense?
Worse in terms of new patients. So like coronavirus, the pandemic. So in New York, New Jersey, all New England states were really bad, but nowadays it's much better than the other states. The other states are getting really worse these days. And then Massachusetts seems to be getting worse slightly. So it's very unclear whether we have school opening in the fall or not. It's not decided.
Do we expect about less than 50 people joining us, right?
Actually, over 300 people registered for the workshop. So I don't know. I think probably a couple hundred people will join here, but we also have other broadcasting streaming thing, and then so yeah, you can just listen to it, but you cannot ask question there. It's kind of a unique experience to the workshop online. We do many things very uniquely this year.
Are you going to do video recording too for my talk? So that I can get.
So you're going to record a video recording, right? But we will not release the video unless you consent to release the video. Agree to.
And the reason is that I like to keep the video.
Oh, you want to have a
Yeah,
video.
yeah, for my record. Yeah, you know.
Yeah.
If you do video recording, yeah.
Yeah, I do video recording.
Okay, great. Thanks.
Okay, good morning, Tom. Yeah, we actually have over 300 people registered for this for Zoom. I think it's because now it's just 8 in Beijing time. Many people they join later.
Still in the bed.
Yeah. We expect your talk to I think many more audience. Yeah.
Okay. Nice to meet you.
Nice to meet you. Yeah.
Yeah.
오전 9시입니다.
So like in Beijing, it's 8 a.m. Here is 8 p.m. It's exactly 12 hours difference.
Yeah.
Do we have general chair? No. Harry is here. I see Harry.
Hi, everybody.
Yep.
Is this a main conference channel or just between us?
This is the main conference, main workshop.
Yeah, this is the main conference channel, and the people on the live streaming can see us, even they're not in the Zoom, I think, right?
Right.
Yeah, there are maybe some people in the live chat.
How many people are in the? I think people will gradually increase, right? It's just 8, maybe they'll join later. How many on the video streaming?
Let me check.
I think it's okay. We now have 30 people, almost 30 people in the Zoom. I think it's well. Yeah, during the talk.
I see 29 participants.
Yeah.
Okay, maybe it's too early in the morning in China time, in Beijing time. The Professor Jongwon Kim has not joined yet, or Keku? No. Yeah, he might be figuring out the password, I think.
Maybe you and Harry can do the
Just
opening.
Opening. Okay. So, Professor Jung-sung, can you stop sharing the screen?
Yeah.
Oh. So I have my slide here. Do you see it?
Yes.
Okay.
Yes.
Thank you and welcome to 4th Asia Pacific Workshop on Networking, Apnet 2020. My name is Jung-soo Park. I'm going to talk a little bit about the reviewing process of this year's workshop. So Harry Liu from Alibaba, and me, Jung-soo Park from KAIST, are 2 co-chairs of program co-chairs. And we had 20 TPC members, technical program committee members from 6 countries here. This year, we received 20 papers, 20 submissions, significantly dropped actually from the last year, probably because we are impacted by COVID-19 pandemic. But each paper got 3 to 4 reviews. And then we discussed the papers after all reviews turned in for 1 week. And then we ended up accepting 8 high-quality papers. We decided not to have a best paper because the number of submissions too small this year. And I'd like to express special thanks to 2 persons in the process. Of course, one is the first one is Professor Kai Chen, who is the co-chair of the Apnet itself, and his students, especially Hao Wang. Virtually nothing really progresses without his help. Every time we hit the barrier, he actually come out and help. He also volunteered to support streaming with Zoom. I really thank Professor Kai Chen and his students. And the other person that I'd like to thank is Dr. Sun Park from GIST, who is our publication chair. And it's really difficult. It's literally kind of, it requires a lot of effort to publish at ACM Digital Library. So I saw her exchange a lot of email exchanges with the ACM. She did a lot of work. And I also thank the rest of the organizing committee. With that, I'd like to hand my microphone to Harry Liu, the other program chair. So stop sharing. Okay, Harry.
Oh, you hear me?
Yeah.
Hi, everybody. So welcome to Apnet 20. I also want to express my thanks to Hongsu. So he carried a lot of work as a TBC chair. So
Hongsu, are you to show the slides? Okay.
The slide. Yeah.
Okay.
Yeah, I would just give a brief introduction of the instructions for our online session. During the talk, please mute yourself, and if during the Q&A part, you can raise your hand with Zoom and before speaking, and the session chair will choose one person at a time, and the session chair will in charge of unmuting him or her. So, and you're free to type in the chat, and note that due to the time limit, your question might not be chosen, but you're free to just contact the speaker after the session, and also feel free to contact us if you have any question. And the following are the the following is the brief schedule, and I think also you can find the agenda from the web page. So today we will have several sessions. First, we will have the keynotes, and then we'll have Apnet paper, and we will have the SIGCOMM talks session, and also an industrial session. And the next day, we start from the morning, 9:10 of the Korea time, and we will still have another keynote talk, and the industry talk, and the data center networking, and the SIGCOMM talk session too. So it's pretty much quite full. So please remember time, and remember that the data shown in the Korea times, you need to calculate your own time zone. So and next, so thank you for coming, and we hope you enjoy the workshop.
Okay, so I'll introduce today's keynote speaker. So it's my honor to introduce, do you hear me? Okay, it's my honor to introduce Professor Song Jung. Song Jung is the professor and head of the Graduate School of Artificial Intelligence and the ICT Endowed Chair Professor of Electrical Engineering at KAIST. Actually, bio is shown up in the homepage. It's kind of rather wrong, so I will not read everything. I will summarize 3 points. One, he's one of the leading experts in the world in the fields of wireless, mobile networking, and theoretical aspect of networking. Second, for the past 20 years, he has received numerous awards. One of the notable awards is winning William Bennett Prize paper awards twice, which is given to the best original paper published in transactional networking in the previous 3 calendar years. The only person other than Professor Jung Song who won this award twice is Sally Floyd, who presumably I think she has already retired. And then the third point, which is important, he has really good vision and intuition in hiring. He actually is the one who hired me in KAIST. So without further ado, here is Song Jung. I think he's talking about today self-driving networks, how to realize self-driving networks with by applying one of the reinforced learning AI techniques. Okay, without further ado, here's Professor Jung Song. You can share the screen, Professor Jung Song.
Yeah, thank you very much for the great introduction. Okay, somehow, let me see, just a minute. Just a minute. I'm sorry, I cannot see.
You can press F5.
Yeah, sure. It's working now. Okay, good morning, everybody. Yeah, I'm Song Chung from KAIST. Today, what I'm going to talk about is learning to make decision in a networking environment towards the self-driving networks. So everybody these days actually see that AI decision making based on AI means some kind of a concept of a network autonomy, self-driving networks. So this is the one of the earlier work coined this concept, which is also called as knowledge-defined networking, which appeared in the SIGCOMM 2017. So if you look at the left-hand side, typical protocol stack of the computer network is you have a data plane on the bottom, and then you have a control plane on the top. But they somehow envision that we will have some kind of a knowledge plane on top of a control plane. So what actually the knowledge plane would do is on the right hand side that if you observe SDN controller, which means a control which belongs to control plane, and they will have a forwarding element on a data plane, so you will get a data operational experience. The data of an operational experience, you will get it, and also in many learning situation, especially in an online learning situation, this operation data is not enough. So that learning cannot be successful. So that people try to these days to make some kind of artificial data through simulation, so more accurate simulation, And also people sometimes use the artificial intelligence technique called the generative model, so that they want to generate artificial experience data from the real experience data, so that you collect operational experience data or simulation data or the artificial data generated from the generative model. So basically you analyze this data and then you will get some knowledge or feature of the network state. And then this knowledge will be forwarded into some kind of machine learning engine. Then you will generate intelligence from the machine learning, and then this intelligence will help human decision to better operate the network underlying network. So basically human decision and this AI based decision will coexist. So we will have a better decision, so that somehow through this group, so we are somehow trying to move forward to the so-called network autonomy or self-driving network. This is basically the concept concept about the knowledge-defined network or self-driving network. Okay, let's take a more carefully network control problems. Many of those, actually most of the network control problem is in fact a sequential decision-making problem in a dynamical system. Of course, the network is a dynamical system. Say, for a given state, if you take action, that the network state will change to the next state. It's a state transition exists, which means this is a dynamical system. And then also we have to do this sequential decision-making online. But the problem is that there are two well-known problems of this decision-making problem. The first thing is the large scale system. Network is a huge system. The cardinality of the possible space is really huge, so that it's hard to compute, even hard to store the network state. So this is known as a curse over complexity. And secondly, as I already said, that the system is a dynamical, but we don't know how this system make a transition to the next state, meaning system model is largely unknown. And also it's a stochastic, which is also known as a curse of uncertainty. Because of this two difficulty, the online sequential decision-making problem in a real world is not an easy problem to solve. So, and also, as you already noticed, this network control is mostly about resource management. The example of the network control, congestion control, wireless scheduling, or other data processing scheduling, or bitrate adaptation in video streaming, and also network function placement embedding, dynamic service training, research management in data, all are about network resource or computing resource. It's about resource management. What about today? Today, these problems are solved mostly using meticulously designed heuristics. Painstakingly test and tune the heuristics for the good performance over and over again. And especially if the workload and the environment or metric of interest is changing, you have to do this painstaking test and tune again and again. Okay, so this is the motivation that we like to have some kind of automation in managing and controlling resources in the network or computing environment. So self-deriving network, the question is something written in, it can be written in below. So can network learn, the important word is learn, to operate by their own decision with very little human intervention, directly from experience interacting with the environment? That's the question we like to address today. So as I said, that most of the network problems are decision-making problem, and also many cases a sequential decision-making. And then I said that already, it's a complex decision-making. Remember curse of the complexity, and it's a dynamical system make transition, but we don't know the model. There's an uncertainty exists in the system. Okay, so you know the terminology or the machine learning area known as reinforcement learning is in fact the algorithmic approach to solve this complex, dynamical, uncertain decision-making problem. Okay, so what is the reinforcement? As you might already know very well about this reinforcement learning concept, that on the right-hand side, you have an environment. You are competing with the Isedo, with a game Go, or you are driving you are driving the car on a road, and you want to manage 5G network. That's the environment. And then if you look at the equation under the word environment, you have a state st, it's a state s at time t. And then given the state, if you look at the left-hand side, you have a brain, agent. Agent will observe this state from the environment at time t, which will be denoted by S on the script T. And then given ST, you have some kind of intelligence, we call it policy, which is the function that if the state is given, you will generate action, control, or decision. So we would denote it by A underscript T. Okay, AT. So you take action, then you will make this environment will change the state from ST to ST plus 1 for under some environmental function. Okay, so ST and AT given, but there's just some randomness involved. That's a WT. That's uncertain part of environment. And also they make a state change, but also this agent or the people can also observe some kind of a feedback signal from the environment, which we call it reward. Okay, RT. Okay, then the goal of this agent or the goal of the brain, the intelligence on the left-hand side is to learn a policy pi, the function pi, to generate sequence of the action A0, A1, A2, and so on, to maximize expected return. Expected return given by this equation, the formula, where as you can see that it's a cumulative reward, RT, summation of the RT over the time, but you have some kind of a discounted factor. So you are more interested in reward in a close time. You are not really, we discount reward in a future time. But you know, it is expectation over the policy. This is a stochastic system, so that you will you want to maximize this all possible sample paths for a given policy pi, and then you have to take this expectation. Okay, that's the definition of the problem. Okay, so reinforcement learning is one of the hottest topic in a machine learning community. A little bit old data, but if you look at the statistics of 2018 ICML, then reinforcement learning paper has a second most submitted papers, and also first most accepted papers. So that the first topic is a neural net architecture. Second hottest topic is reinforcement learning. So many people talks that now this AI area is moving from the supervised learning. In fact, in some sense, reinforcement learning itself is a supervised learning, but it's moving from the classification type problem to this decision making problem called reinforcement learning. Okay. So these are the list of the previous work on RL-based network control or computing system control. So just to take a look at it one by one. So here, in order to understand this sequential decision making or decision making AI, what we like to have is the action, right action. Then in order to design the policy to generate this action, the first thing, the first concept we have to define and then we have to have is that we should be able to evaluate the action. In other words, we have to define value of action so that if you have a different actions, a set of actions, if you can evaluate each action, then you can choose the best action. So that the most fundamental concept of this decision making is the value of the action. So, but so that this is the point where learning comes into the picture. So the value of the action is not given, so that we have to learn it. And also, the action space or state space is huge, so that it's difficult to handle computationally this value of action, so that we need to have some approximation method. That's the main. So I will, although there are some mathematics involved, I will try to deliver before moving to the application. I will try to deliver this a few important fundamental concepts. So decision-making problem is a long-standing problem. People in the operations research or electrical engineering or economics actually had a model called the Markov decision process for this sequential decision-making problem. So that if you the system model is given by the transition probability in the if you look at the first line, then so it's a probability. So given current state S and given current state A, we are interested in transition probability that the next state will be the S prime. So they will be denoted by this notation transition probability. Okay, that's a system model. And then we like to have a policy function, as I already mentioned once, that the policy function pi is the function generate the action A for a given state S. Okay. And then I was also already talk about the reward signal, feedback signal from the environment, which is R. The value is R. And also I will denote that the reward function itself as R is a function of S current state. And the action I take. And then I make it, and then the system make a transition to the S prime. So from S, if transition occurs from S to S prime under the action A, what is the R? Okay. So this is the one. This figure shows the one sample pass of the system transition. The system start from the S0. I take I happen to take action A0, and then I will get a reward R0 at time 0, and then the system happen to make a transition to some state S1. Then I will happen to take action A1, then I will get a reward I1, but I will multiply this I1 will be multiplied by the discount factor gamma. Basically, I said that the reward at the stage 1 is less important than the reward at the stage 0 by factor of gamma. Okay, so So again, this is a overall return, cumulative return, discounted weighted sum with the discount factor expectation. We want to find the pi superstar, which maximize the expectation of this cumulative return. That's we call it optimal policy, right? That's a mathematical model. Okay. So the most fundamental concept, action value. So take a look at the function, action value function, QSA. The meaning, this is a fundamental concept of this reinforcement learning, that for a given state S, Q is the function that returns the value of the possible action A. Okay, for a given state A, if your action is A, then you will get a value Q. If you take action B, then you will get a corresponding value of the action B, Q. Okay, so if you have such a function, then I can basically plug all possible action into this function, such that I can find the action which returns the largest value. Okay, so this is the starting concept, and actually this value must consider future potential action to the end of the system running time. Okay. So that's why if you take a look at the right hand side, the value of the action A is the immediate reward at a current stage, that's RSA, plus from the second stage to the end, the expected reward is the second term. Okay, it's a mathematically is an expectation, it's a cumulative, but from time 1 to infinite. It's not from time 0 to infinite. Okay, but here, if you look at red circle, assuming that from the stage 1, from the second stage, I'm going to use optimal policy, optimal action. So that if I assume that somehow if from the second stage to the end, optimal policy is applied, optimal action is applied, then if the only the first reward is first term matters, so that if you just plug A or B such that if this additional two term maximize, then that's the best action that I will have to take at the current stage. Okay, that's the concept. So if I can somehow get able to get this so-called Q function, action value function, then look at the equation at the last, that if you have some action, then you just plug all possible A from the action space capital A, you just plug all possible A, and then you find then you will have a policy, optimal policy for a given state S. So that's called optimal policy. So once you will be able to get Q function, action value function, getting optimal policy pi super is just a very, very simple work. Okay. Interestingly, this operational research people, electrical engineer people, actually electrical engineer Richard Bellman actually find that this most important value function Q must satisfy this set of this fixed point equation. It's a system of equation, but it's a linear equation. But you know, this function S belongs to the capital set capital S. A action belongs to capital A. So imagine that the cardinality of the state space S, imagine cardinality of the action space A, then you know this is a set of equation with a huge number of equation. It's a set it's a vector fixed point equation with a huge number of equation. Okay, so we will denote this as a vector matrix equation as a Q equal mapping T and Q. Q is the vector of the value. Okay, so this is a fixed point equation, and then people you can actually people can prove it that the mapping T is a contraction, so that this fixed point equation has a unique solution, and also known as a dynamic programming algorithm, which is also known as a value iteration method, is that this fixed point problem can be solved by this iteration, meaning starting from the arbitrary Q0 and then initial value vector, action value vector, and then you apply this T mapping, the contraction DP mapping, dynamic program mapping, and then you will get Q1 vector, and then you just to repeat this recursion iteration, keep doing this iteration, then this will converge to this unique fixed point, a solution. But because this mapping is a contraction, so in a exponential space, that's provable. Okay, it's a geometrical geometrical space. Okay, since this is a discrete system. Okay, but the problem is that this is a well-known theory, but this dynamic programming can apply to very, very small toy problem, cannot handle real-world problem. Why? Because take a look at Bellman optimality condition. Oh, this is of course, this is once you find that this Q value function, that's truly optimal in a sufficient because this Bellman equation is a sufficient and necessary condition for Bellman is optimality. Okay, here, but that cannot handle the real world problem. Why? As I already said that, take a look at the equation. The transition probability is unknown. That's a system model. Most of cases unknown. The reward signal, no. It's not observable in many cases. Even you observable, but you know, it also reward function itself may not be known. Okay. I will. And also, the number of equation is prohibitively large due to this huge cardinality of the action space, and also the huge cardinality of the state space. And in some cases, even the state space and the action space can be a continuous space. Okay. That's why learning comes into the picture. In order to solve this curse of dimensionality, curse of complexity, curse of uncertainty. So in 1989, one of the PhD students at the Cambridge University proposed an algorithm called the Q-learning to solve this Bellman optimality equation. So since, as I mentioned that, look at this, the first equation, there's a transition probability involved, so that this value iteration cannot be updated because we don't know transition probability, and then we don't know this reward value. Okay, so the basic idea is that, oh, what is the summation over some value multiplied by probability in this Bellman equation? That's the expectation, right? So what is the if you cannot really get a real expectation value, what is in terms due to the point estimation theory, what is the how to calculate it? Sample average, known as also known as a Monte Carlo average. So basically, for this value iterate dynamic programming, this expectation part will be replaced by the with the sample average. Take a look at the second equation, second update equation, right? expectation part has been replaced by the sample average. That's Q-learning, right? So upon k+1 sample of SKAK, let's say that sample is the value of that sample is SA or S prime. Then you plug that sample onto the right-hand side, and then you just keep adding and then dividing by the number of the sample will be the new update. But this Monte Carlo averaging form is inconvenient in the online setting. That's why we will modify, we will rearrange this second equation and then to the third equation, which will be given as a. So basically, you will just keep maintaining this sample average, and then we will just add this new sample value. So it will be presented as a stochastic, is a recursive form, which is also known as a technique called the stochastic approximation. Then the professor at MIT actually proved that this in 1994, this Cambridge PhD students Q-learning in fact converge to the true Bellman equation solution. Okay, that's why the Q-learning became popular. Okay, so this is Q-learning in action. Okay, so once you learned through once you learn Q function, action value function, you will be stored in a tabular form on the right and right and lower corner. Okay. So a table. So it's a QSA table. So you will have a S value, and also you will have a value, and then you will have a value element on this table, so that if the current state S is 1, and then you can have two possible action, A equal 1 and then A equal 2, then you choose A equal 2, which gives a larger action value 4.1 than 3.1, right? Okay, I will explain here in this policy making algorithm. I will explain important concept later. They're called the exploitation and export trade-off. Okay, so this collects. Okay, so Q-learning actually breaks the curse of the uncertainty by replacing this true expectation by this sample average, right? So without knowing system transition probability, I can actually solve Bellman equation. That's a Q-learning, right? But what is unsolved is what? How to handle this curse of complexity. Why this is so important is that if you look at this Q-learning, you know, the second equation, you are updating in the second equation, you are updating the Q value for a given SA, for a given state and given state A, action A. But you have a huge number of possible SNA pair. But you know, this Q value for SNA are updated only when this pair SNA are sampled. In other words, only when this pair SNA are observed in a real operation environment. But imagine that if this cardinality of a SNA pair are huge, and then if imagine online setting, in an operational setting, can you really expect that you will sample this particular SNA pair? No, impossible. So Q-learning is beautiful, but it's a complex system, meaning where the number of SA pair are prohibitively large, Q-learning never works, will never work. So we need to have a methodology to handle this. That's where the neural network comes into the picture. Okay. So how many state and A pair? If you look at the well-known AlphaGo problem, if you count the cardinality of the state S, state space is a 10 to the power of 170, a huge number. You know, well-known this Atari game of Google DeepMind, breakout game. Even only this cardinality of the state space is a 256 to the power of 28,000. You cannot handle this computation. You cannot apply, of course, you cannot apply Q-learning. And you cannot even store this Q table, assuming somehow you are able to compute by some magic. You cannot even store the cardinality of a state space S, cardinality of a state space action A is prohibitively large. Okay. So the idea is that we cannot handle the Q function. Take a look at this equation. Q function, which is the function of SNA, as it is. In fact, we want to group possible state and A action into some representative value. We call it feature. So some feature can represent huge number of state and action pair. By doing so, instead of directly dealing with the huge cardinality of the state space S and the state action space A, we just need to this embedding space called feature space, where you just need few number of feature. Cardinality of the feature space is much smaller than the original state space and the action space. So this feature extraction is required. Once you have this feature extracted, and then you consider this feature as an input, and then you design neural network parameterized by theta. This is a Q tilde. No, it will be. I will denote this as a Q tilde. It's a Q action value approximation by neural network with some clever design of a future. So this is the design pipeline. Okay, you have a state space action pair, and then you have a feature extraction strategy so that you will have a feature vector. Given feature vector as an input, you design some kind of a multi-layer perceptron type of a deep neural network so that you will have a functional approximation using neural network. And also, typically in the old days, feature extraction mapping has been done by handcrafted manner. But after the introduction of this convolution neural network, this feature extraction mapping itself become automatic. Automatic process. It's included in the convolution network. This is a convolutional layer do the feature extraction automatically, and then this second layer called what is called it's something like a multi-layer perceptron layer will do this functional approximation for a given feature. Okay. So I'm not going to do again. This is a DQN structure using a convolution neural network. In our context, I'm going to use this deep convolutional neural Q network in order to approximate the Q function. in order to what? Overcome the so-called curse of complexity. Okay. So Q-learning algorithm proposed by a Cambridge student breaks the what? The curse of uncertainty by replacing expectation in the Bellman equation by sample average. So learning, this sample average is a learning. You need to sample it. You need to experience sample. You need to collect data. And neural network approximation breaks the curse of the complex. So that's another type of neural net learning. So it's a learning tool. Okay. So instead of maintaining Q table, we are going to embed this Q table into the neural network parameters of a certain architecture. Okay. Given the limited time, yes, but you might ask me that, oh, if Q is a true Q value function, okay, then Bellman equation will hold. The second equation, Q equal TQ. Well, now instead of using this true Q function, Q value function, action value function, we decide to use the Q tilde, neural net approximate Q tilde. Then question is the Q tilde, then Q tilde will be equal to the dynamic program mapping T applied to a Q tilde? No, the equation will no longer hold. So that we need to have some projection operation into the picture. So that, in other words, if you take a look at the picture on the right-hand side, so Q tilde is the approximation of the value. And then you apply dynamic program Bellman equation mapping T, then it will be some vector in some space. And then you have to make a projection. You have to make projection this vector onto the space where this Q tilde vector, all possible Q tilde vector exists, the space where all possible Q tilde vector exists. So that now we have a new Bellman equation called projective Bellman equation. Projection is a you know in a L2 norm minimization, as you might know, so that you can write down in the as in the right as the last equation. So you have to find the neural net parameter theta to minimize Q tilde, to minimize this distance between the Q tilde and TQ tilde in terms of Euclidean and the L2 norm distance. Okay. And you have to minimize, and then this norm can be written as an expectation expectation over the all possible data distribution SNA. That's why this well-known loss function of neural network is defined, because it's an expectation. If you look at the expectation of the what is a sample path Bellman equation, right? TD error, you know, a temporal difference error, and then you have an expectation of all possible sample, meaning it's an expectation over SAS prime data distribution. Okay, but again, who knows this distribution? Yeah, nobody knows. So same as a Q-learning situation. So we replace this expectation by a Monte Carlo average, in other words, sample average. And then, so the expectation become summation over all possible SA gamma S prime. It's a, you know, the reinforcement thing, the data is a data, one single data consists of the current state, current S, and then action I will take, action A. and the reward I will get is R. And then the system, the next state of the system S prime. These are the single data. Okay, we have a collection of this data. But instead of optimizing over all possible this sample, this in the current neural machine learning area, we call it that this is a stochastic approximation version of this sample average called stochastic gradient descent method is used. Okay, so it's a well known. So I'll just skip it. This is a deep QN network in action. Everybody, some of you may know well. So before moving to application part, the last part is that okay. So we actually I explained the key concept of the key concept to determine this how to determine how to calculate, but the calculation is impossible. So how to learn this action value, and then by coping with the curse of dimensionality and the curse of uncertainty, so that once you have a Q function known or Q approximation known, then you can actually calculate the policy. If you look at the last equation, if you have once you learn Q function, you can just plug all possible A, then you got a policy, optimal policy, right? For a given S, you know what is the best action, right? But imagine we are learning, we are approximating the Q function online. So this is the estimation process. So if you keep doing this learning again for a very, very long time, yes, this Q estimate will likely to converge the true Q. But during this estimation process, we have to, this is the online situation, we have to select the action from this estimate, which may not be the true Q value. That's why we need to have some kind of exploitation and exploration concept. In other words, so one of the exploration, most common or most popular exploration trade-off policy, the epsilon greedy policy, which is that, okay, so if you take a look at that, if you have a Q function estimate, this is an estimate, then you just believe this is as if this, you believe this Q function as if this is true. Okay, so you just take a max, you do maximization and pick the best possible action. Okay, but here we believe too much this estimate, current estimate may be far from the true Q value. That's why we add some kind of exploration, because current Q estimate is what we learn from our previous exploitation. So we have to believe it to some extent. But on the other hand, we never visited some other state space. We never try some other possible action. So we didn't know what kind of better option available from the state space. That's why with some probability epsilon, we just randomly choose some action to go to some state where we never visited, we never experienced. But this is, we call it exploration, okay? So with probability epsilon, we do exploration, with a 1 minus epsilon probability, we just believe the current estimate of the Q function, and then take action from the, we choose the action from the this okay, I'm sorry, I'm going to skip this UBC. UBC is more elegant and sophisticated policy, which can provide provably a much better sample efficiency than epsilon graded policy. Sample efficiency means when you have a sample, it will impact more significantly to in finding a true Q function. Okay. But RL is not a panacea for all our problems. So the most important thing is that, you know, these days AI is so popular. Everybody try to use AI technique, machine learning technique to every problem. But there are many problems which can have a better solution technique than machine learning. So that you should, before you apply AI or machine learning, what you have to do is that you have to really carefully, deeply think about whether this is really the machine learning problem or not. Okay. In that sense, RLED is the same. Reinforcement is not a panacea for all our problems. You have to carefully select the right RLED problem in the networking context. I will go to the Maxwell scheduling. Maxwell scheduling, everybody has been used. Longest queue scheduling, longest backlog scheduling is another name. So it has been used in many scheduling, resource scheduling problem in a networking context or computing context, switch scheduling, or in a wireless scheduling. It's a state-of-the-art scheduling. It's known to be throughput optimal. And then it's a myopic policy in the sense that it determines the action, scheduling decision. It makes its decision based on a current state observation. They do not take into account the so-called the future reward. But you know, this reinforcement learning, the key feature of the reinforcement is taking into account to future cost or future reward, but Maxwell scheduling does not take into account the future. So it suffered from a very, very poor delay performance. It's well known problem of a Maxwell scheduling. And mathematically speaking, the Maxwell scheduling algorithm is an algorithm to minimize the upper bound of the conditional Q drift, meaning given network Q vector, the Maxwell scheduling try to minimize the expectation of the positive Q drift, so that it will aim to stabilize the system. So Maxwell scheduling is a throughput optimal. What that means? A throughput optimal that means is that here, take a look at the right hand side of the picture. You have a end user. Each user has their own arrival stochastic process. And then it has a separate queue, per-user queue. That's also modeled as a stochastic process. And also each individual queue has a service capacity C1 and CNT. Is again stochastic process, but C1 and CNT, this capacity is a time varying and stochastic, and also they are coupled each other. Okay, so in this setting, it's a very general setting. Okay, in the general setting. So the question is, it's a time slotted system, so that the scheduling is that at each time slot, which user have to be served. is a scheduling problem. And again, this is the capacity region has been coupled and stochastic, so that is unknown in advance. So that we want to have a scheduling algorithm. If we take a look at the picture below, the shaded area is the unknown capacity region uh, of the two user case. Then but unknown. But we as long as we have a arrival vector within the arrival rate vector within the unknown capacity region, we want to have some scheduling algorithm that process this any arrival vector within this region without divergence of this Q, without experiencing the instability, instability. Meaning we should be able, we want to find some scheduling we can accommodate all the arrival vector within the unknown capacity region. That's the throughput optimal scheduling, and Maxwell scheduling does this job. That's known. Okay. But we actually propose beyond the Maxwell scheduling Q plus, and simply considering return to go, future reward. And then in order to consider this future reward, we actually, of course, we run, we use a reinforcement learning. By doing so, we were mathematically able to prove that this algorithm is in fact throughput optimal, same as Maxwell scheduling, but as well as it's a delay optimal too. So it's a joint throughput and delay optimal policy, Q plus UCB. Moreover, we want to have a better sample efficiency, so that as you see there, it's a Q plus algorithm, learning algorithm, but with a UCB exploitation. We use a UCB and the UCB exploitation and exploration scheme. And then moreover, if you take a look at the picture below, one of this learning based algorithm, the problem is that this initial learning phase. Maxwell's algorithm is not an iterative algorithm, it's just a fixed algorithm, so that it will give some constant performance over the iteration because there's no iteration involved. But other algorithm is we need the training, so that it's a training iteration involved, so that it will improve and eventually it will outperform Maxwell algorithm as in the picture. But the problem is the initial learning phase. Initial learning phase, so we do not have enough experience, enough data, so that we are generating very, very wrong action for a while. That's why it will have a, so that we actually have some idea to have an initial phase, initial learning phase. We actually have a performance better than max weight. And then once as learning goes by, then this will replace by the better learned policy, so that we can also overcome this is a learning. So that our reward, if you take a look at reward, is we want to have a delay optimal term, the term to reward. We do have a reward term to achieve delay optimality. We also have this Q drifted term, which we want to have a stability, meaning throughput optimality. By doing so, if you take a left-hand side, I compare with the Maxwell and the algorithm proposed. So both algorithm is a throughput optimal, so that if the traffic load goes to the one means is approaching to the capacity boundary, but still the system never diverges because both algorithms are throughput optimal. But our algorithm achieves a 40% delay reduction. It's in fact mathematically also we can prove that that's our algorithm actually achieve delay optimality asymptotically. Okay, I will skip. Okay, second application is also the results of our lab. It's a recent one which has been submitted to the ACM Movis. It's a census. We want to apply this AI into the OS operation, operating system operation. Many of the operating system level strategy is rather static, and it's a rule based. It's not really data driven strategies, but there are several limitations. Particularly if you look at the mobile devices, dynamic voltage and frequency scaling issue, the controlling the voltage frequency level of the processor to save the battery or to save the to improve the energy efficiency is a long-standing problem, and there are many approaches has been proposed, and also every mobile devices CPU has their own default DVFS strategy built in. Okay. Another problem in a mobile device is thermal sorting, because you know this temperature issue in a mobile device is crucial. That's why they have some thermal sorting strategy built in the mobile devices, which is if the temperature go above some level of the of some threshold, the system OS just based on rule just immediately lower the this voltage frequency level to the very low level when overheated, to go back to go down, to lower the process temperature at a very fast speed, so that application will be affected largely. So the thing you have to notice is that this dynamic voltage DVFS strategy, thermal sorting strategy, is application agnostic. Just OS, or simply they made a strategy simply based on OS point of view. In other words, they just observe the utilization of a processor, and just the temperature goes beyond over the threshold or something. So, and also the more important is just one more minute, please. I know this is 12, so just one more minute. And also this stage, mobile dista has a CPU and the GPU are in a single SoC chip, so that we don't know this thermal coupling between CPU and GPU. But on the other hand, this machine learning application or this today's workload actually has been the workload has been distributed by a certain policy over CPU and the GPU, in a sense, in a certain depending on an application demand. Okay, so that this has been taken into context, but they don't care the current state. And also, yeah, they're agnostic about CPU, GPU, thermal coupling, and thermal environment. When my mobile devices in my pocket will experience a different thermal environment, and it is a hot summer or it's a cold winter, and so on. So we need to have some kind of a prediction how application require CPU and GPU resource, and also how this what will be the temperature headroom budget left up to the this heat temperature threshold. So we need to predict somehow, and then we need to have some kind of a predictive management. Okay, so it works. We design GTT, and it works pretty well. Okay, I'm sorry, but we actually evaluate this solution over the two platforms. One is a Google Android phone, okay, and the other is which is a platform with NVIDIA ARM CPU and NVIDIA Pascal GPU. And so we have we expand over this two different platform, and then we actually show it actually works much better than what is known as a state of Maestro, and also default of this two platform strategy. Okay, thank you very much.
Okay, thank you very much for your talk. So we have a few minutes of questions and answer, Q&A. So if you have any questions, audience, please raise your hand and I'll unmute you. So I have a question. So it's very interesting to apply Q-learning to real world problems. But you talked about networking, like here, self-driving networking. And I'm wondering what specific problems you can solve. For example, like there is like congestion control in terms of networking, right? Congestion control, routing, many problems already there. And then they have their own existing solutions. But I'm wondering if applying this Q-learning or reinforcement learning can improve the existing solutions, or so you showed a few applications, DBFS and then scheduling, but I'm wondering if you have any specific application in networking itself. Is that
okay?
Yeah.
Yeah. So I can answer with some few words. And first of all, many of the resource management problem and the network control problem has been formulated as some kind of a mathematical problem and optimization problem, and then people try to derive a solution to that optimization problem or mathematical problem, or in some cases they try to derive the heuristics, or they just derive the heuristic from the experience. So those problems, which some of the important network problem which cannot be handled by computation. I mean, in a existing algorithmic approach, like a mathematical optimization. Then I think maybe there's opportunity for this machine learning technique get into the picture, because I keep mentioning that the machine learning technique here, especially the reinforcement learning, is the algorithmic approach to tackle the complexity. Is an algorithmic technique to tackle uncertainty. So any of the problem you are suffering from this curse of complexity, curse of uncertainty, when you design heuristics or you design mathematical algorithm, then I think you might consider this learning-based approach. And secondly, self-deriving, going back to self-deriving concept, so that this algorithm or heuristics, whatever you design from the mathematics or from the experience, does not adapt to the changes of the workload or environment or metric of interest. So you have to redesign from the redesign all these strategies or policy or algorithm, maybe in many cases from the scratch, so that people try to avoid this labor. They want to make this operation to be autonomous. I don't know. These are the concepts people are trying to pursue toward the future network or toward the 6G. but whether this network autonomy is something really we really want to have, or is the concept that support the human decision, we have to take a look at it. But that's the point. But anyway, does that
Okay.
answer it?
Yeah, thank you. I think Dan Lee raised a hand. Dan Lee, can you? Mute yourself? Yeah.
Hear me?
Yeah.
Okay. Thank Professor Song for the excellent talk. I just want to follow Consul's question. In network, such as congestion control or routing, it depends on the traffic demand or the network states, but it is just dynamic changing. If we use RL, just do we have an assumption that the environment should be relatively stable? If we have that kind of assumption, I'm just curious whether we can use it in dynamic network environment. Yeah, that's my question.
Yeah, dynamic has two types of dynamics. Even the stationary system, there's a dynamics, right? That dynamic. So basically, mathematically, this reinforced learning assumes a stationary, a stochastic process, a stationary system assumption. So, but you are talking about some kind of a non-stationarity, right? So if environment workload drastically changed, so it became different system, then I think we need to have some kind of we have to combine this known as a transfer learning kind of idea into the reinforcement learning, so that we have to train policy from the beginning again, but with some previous knowledge. Previous knowledge comes from the previous environment. Okay, that answers to you?
Yeah, thank you. I learned a lot from it. Yeah.
Okay, do you have any other questions? Okay, let's thank our speaker. We have a applause icon here. Thank you very much.
Actually, I cannot keep the time. I mean, I use 4 minutes more. Okay, I'm sorry there.
Okay, thank you very much. So we're going to have a break until 10:30 in Korean time, which is 9:30 a.m. in Beijing time. Okay, we resume at 10:30 with the paper session. Okay, thank you very much.
Thank you. Thank you very much for the attention. Okay.
Thank you.
아, 교수님, 내 시간을 가능한 맞추려고 그랬는데 이게 그 뒤에 조금 오히려 애플리케이션을 더 설명을 했었어야 되는데. So you have to turn on the microphone.
Yeah. But I think it's broadcast to everyone what you're saying right now.
사람들이 그 질문할 시간을 너무 못 줬네.
예. 교수님 감사합니다.
예, 그 저기 뭐야? 그 애들은 그럼 아예 학교 못 가고 있어요?
이거 지금 브로드캐스팅 돼서 다.
I'm sorry.
나중에 제가 연락드리겠습니다.
Okay, talk.
예, 감사합니다. 예.
Talk later. 아, 이게 완전 브로드캐스팅. Okay, sorry.
So speakers in the next session, maybe you can try sharing the screen and
Yes.
see if it works. Yeah.
Yeah,
So you,
I'll be
Asim is here. So yeah.
yes, I'm here.
Please take it
So
over.
yeah, hi, Heijing. We have some time, so you can try sharing the screen. I'll
Yep.
probably give you permission first. One second. Heijing, can you try sharing?
Oh, yeah, okay.
Okay,
Can
great.
you see it? Oh,
Okay.
yeah.
And Okay, so let me begin. Good morning, good afternoon, and good evening to the entire audience all around the world. I'm Asim Jamshed, the program chair. I'm working in Intel Labs. For this session, we have an exciting round of talks. Let me just remind you, in case you are joining late, we shall be muting all the participants' mics before the talk begins. And at the end of each talk, we will scan through the participant list and see who has raised the hands or hit the thumbs up button. So based on that list, we will sequentially iterate through the list and unmute the person. And so he or she can ask the questions to the presenter of the papers. Okay, so please keep your questions brief and to the point because we are following a tight schedule. Okay, so let's begin. Our first talk is from KAIST. Our first presenter is Hee-Jing Lee, who is currently an intern in MPI SWS. Before joining MPI, she was a master's student in KAIST, and she's going to be talking about how one can use smart SIMD optimization techniques to reduce memory access latencies in network applications. Hee-Jing, please take it away.
Yeah, sure. Yeah. Good morning. I'm Hee-Jing. Can you hear me?
Yes, we can. Go ahead.
Oh, yeah. Okay. So today I'm presenting this work I've done in KAIST, leveraging SIMD parallelism for accelerating network applications. The market size of the network function virtualization is growing due to its flexibility and cost efficiency. Many network applications have been shifted from dedicated hardware to software running on standard servers. A variety of those network application logics are implemented with hash-based data structures, like packet classification algorithm of Open vSwitch heavily relies on hash table lookup, and Bloom filter is typically used in pattern matching algorithms of intrusion detection systems. These applications need to process more than 140 millions of packets per second in a network environment with 100 gigabps link. To handle this amount of packets, it is imperative for the underlying hash-based data structures to deliver a good performance. Using single instruction, multiple data parallelism might be helpful for computing hash functions in such applications. A SIMD instruction can conduct the same operation on several data in parallel, thus improves data processing performance. These days, many manufacturers like Intel, AMD, IBM adopt SIMD technology on their mainstream CPUs. And its capabilities keep growing. For Intel CPU, with the SIMD technologies evolving, the vector size recently grows to 512 bits and also supports a variety of functional instructions, like instructions accessing several discontiguous memory addresses, and some existing network application and network processing framework, such as DPDK and VPP, are already using SIMD instructions. But to the best of our knowledge, it is used in a relatively simple memory copy or comparison operation, not in a data structure manipulation logic. However, adopting SIMD instructions to the existing hash-based data structure is not trivial. First, naively converting the scalar code to the parallel code is hard to effectively utilize vectors. Depends on the control flow of the program. Data from several different packets might take different branches. In that case, not all the lanes need to be processed with the operation. If we execute the vector operation without considering it, some lanes in the vector will be wasted. To reduce the wasted lanes, our approach is to use new functional instructions in AVX 512 that can operate on specific lanes to properly replace the wasting lanes with the data need to be processed. The second challenge is that naive vectorization leads to accessing several discontiguous memory addresses, and this memory access pattern introduces overhead. The probability of all cache hits for accessing several addresses would be much smaller than accessing a single address. Any data misses the cache will pass upon all other data in the vector to be processed, thus degrades the performance. To handle that, we prefetch the data before accessing it, also transform the data structure to a form of structure of array, which collects the data to be loaded on the vector into an array so that prevents to access discontiguous memory addresses. In this paper, we show the impact of our approaches with two case studies. One is a highly parallelized Bloom filter that fully utilizes vectors, and obvious megaflow cache acceleration by parallelizing packet classification with data structure transformation. First, I will introduce Bloom filter lookup acceleration. A Bloom filter is a data structure used to check if a key is a member of a set. It tests several bits in the filter, indexed by several hash values. If all the bits are set, the keys likely belong to the set. Or if there's any 0 bit, then the keys definitely not belong to the set. In the serial Bloom filter lookup, we assume there is an array of 32-bit input keys to be searched against the filter, and one key is processed at a time. There's an existing vector implementation of it with 256-bit instruction set. It first packs 8 keys in the register and perform parallelized hash function on it and get 8 values. According to the hash values, we access the bits in the filter. It is done by the gathering instruction, which loads the data on the register from several discontiguous memory space. And then we check whether the bit is 0 or 1 with vector AND operation. Then we get 8 Boolean results for the keys. Once a key failed in a bit test, we don't need to compute the latter hash functions for the failed keys. Compute the second hash function on this lane will waste the computation. So the existing vectorization, they separate the failed and succeed keys using permute instruction. The permutation index tells how those lanes should move inside the vector. That index is stored in a table and accessed using bit test result. And after separation, then the failed keys are replaced with the new keys. Naive expanded to AVX 512 will make the permutation table too large to reside in the nearest cache and drags the performance. So we designed our Bloom filter with 3 more optimizations. We use new functional instructions in AVX 512 for the algorithm to remove to use of permutation lookup table, and vector level loop unrolling and prefetching for the memory access latency hiding. Instead of referring to the permutation table for replacing the failed keys, we use expand load instruction in AVX 512. It can select specific lanes in the register to load the data. So after we get the bit test result indicating which lanes of keys are failed and which lanes of keys are passed, we use it as the mask of the expand load instruction that shows the lanes where the data should be loaded. And the new keys are loaded at those lanes, replacing the old keys without permutation table. Upon it, we implemented vector level loop unrolling. Several independent vectors in a loop body, we can more effectively utilize the pipeline. So we cut the input array into several parts. The number depends on the unrolling vector we want to configure. And each vector loads keys from the start of the partition. Once a vector touches the end of the partition, left keys are processed serially. Gathering the Bloom filter from the memory is a random access and depends on the size of the Bloom filter. The gathering latency can be dominant. So we use prefetch instruction to load the filter on the cache so that further reduce the latency. Then the size of the Bloom filter grows, the benefit of prefetching is distinct. We measure the performance of the Bloom filter with Xeon Silver platform running on a single core. And the Bloom filter is implemented with murmur hash function, which is known for its uniform and fast performance. And we compare the time for processing 1 million of random keys. HPBF is the implementation that only adopted new instructions without loop unrolling and prefetching. It performs the existing 256-bit implementation up to 94% for small size Bloom filter. But the naive AVX file 12 has much less improvement due to enlarged permutation table. Then we add loop unrolling to the HPBF. We see more improvements that outperforms the baseline up to 162%. We see loop unrolling has a huge impact on the performance, and it has an optimal factor which increases with the size of the Bloom filter. And finally, we show the prefetching effect given to the result. When the Bloom filter size far exceeds all the layers of cache, HPBF with prefetching outperforms the baseline up to 65%. Next, I will introduce the Open vSwitch case study. OVS is a de facto virtual switch for NFV environments. And among the packet classification pipeline in Open vSwitch, Megaflow cache processes most of the packets. And inside the Megaflow cache, a rule is inserted in one of the subtables. And lookup is done by sequentially search each subtable until the packet finds a match. When we stress tested the OVS with most of packets being matched in Megaflow cache, we found that packet classification in Megaflow cache occupies more than 80% of the CPU cycles. So our goal is accelerating the Megaflow cache so that improve the whole performance of the Open vSwitch. Our existing subtable lookup consists of 3 steps. They are hash computation, table lookup, and verification. And hash computation consumes most of the CPU cycles due to the costly data gathering and hash computation. We parallelize it by computing 16 packets at once instead of a single packet. So the main idea we insist here is that naively using SIMD instructions across several packets is not effective or even has worse performance because the packet batch spreads over many cache lines. When gathering data from them, the possibility of all data resides in cache is very low. So in that case, the serial code performs better. So we changed the data batch, the packet batch data structure to a transposed form as structure of array. We put together the data to be gathered in one register. By transposing the data structure, we can load from the contiguous memory space and reduce cache misses. So when a batch of packets comes into the Megaflow cache, the header data is extracted to the transposed data structure. Then in each subtable lookup, we load 16 32-bit header data from the array and apply the subtable mask by vector AND operation. Then the hash values are generated by vector hash functions. We compared the time for computing hash values of different number of packets. The time cost of 2 hash functions provided by the OVS grows linearly with the number of packets, but AVX implementation can handle all packets with 2 iterations, so the time cost remains same. The vector implementation is not always faster. When the number of packet is less than a certain number, it's better to do it serially. So based on this micro benchmark, we set the threshold to 8 for using parallel implementation. When the packet left in the batch is larger than 8, we process it with vector instructions. And with the more packets finding matching rules and the number of packets left reduced to 8, we process these packets in serial in the downstream subtables. So we set up the end-to-end evaluation environment as it. We run the bridge on a single core, and we use Mungen as our packet generator. The packets are generated with minimal size, and they are all matched in Megaflow cache. Here is the end-to-end evaluation for throughput over the number of subtables in the Megaflow cache. Our transposed vector implementation has initial cost for making new data structure. So when the number of subtables is small, it has negative speed up rate, but it grows up to 48% with more computation load. And also we see the naive implementation, which doesn't consider the data structure. It is always slower than the baseline. So to conclude, we adopted SIMD vector instructions to the algorithms used in the network application. And we argued that to effectively utilize SIMD instruction is more than a parallel algorithm that effectively utilizes vectors, but also reducing the memory access latency. We show that with 2 case studies of Bloom filter and OVS Megaflow cache. Thank you very much.
Okay, thanks, Hee-Jing, for a great talk. So we still have a few minutes. Are there any? So I do receive some raised hands. Dan, do you have a question? Dan Lee. Okay, so I'll move on. Lai Long Lu, you can ask your question. Can anyone hear my voice?
Oh, yes, I can
Yeah,
hear
okay,
you.
all right. So, okay, so I can move on, it's fine.
Asim, that's applause. That's not raise hand.
Oh, okay. Oh, okay. I need to look at thumbs up then.
Right, right.
Okay, yeah, okay. So, is there anyone here? Oh no. Sheng Huang, do you have a question? Can you hear me, Shenghuang?
I think I can unmute, or if anyone have questions, so just
Okay.
Ask.
Okay. Okay, so I guess I can ask the question if Hejing, did you try your techniques in full-fledged applications like full-blown IDS stacks or some other network applications?
Not yet. That's one of the future work for our work. Like we want to port our boom filters on the real network applications in the future.
Okay. And what about the packet sizes? When you were showing the graphs,
Yes.
did you try using Immunogen packet generator by blasting various packet sizes all at once and then see what was the overall performance?
Actually, we evaluated only with the smallest size packets.
Okay.
Yes, because in OVS they are processing the packets with the with mini flow data structure, which is fixed for every size packet. So
okay. Okay. All right. I guess we can thank the speaker and ask the next presenter to share his screen. So, Hejing, can you unshare your screen?
yeah, thank you.
Thanks. So, our next presenter is Hao Li, who is an associate professor in the School of Computer Science and Technology at Xi'an Jietong University. I hope I got the pronunciation right. He got his PhD from the same university, and his research interests include topics pertaining to SDN, NFV, and network measurement. So today he's going to be talking about a new intermediate representation for network programming languages. How you can begin?
Okay, can anyone hear me?
Yes.
Okay. Hi, everyone. I'm Hao from Xi'an University. Today, I'm going to talk about the intermediate representation for network programming languages. This is a joint work of Xi'an University, Xilinx Labs Asia Pacific, BUPT, and Victoria University of Wellington. So first, I want to present how we program the networks in current days, especially for the software-defined networks. So in SDN, there are switches that forward the packet in real time and a centralized controller that control the behaviors of the switches. So the switches from the network data plane, NDP, and the controller from the network control plane. So the first way we can program the SDN is to directly issue the NDP configurations from the controller to the switches. Such configurations are usually with the match plus action form, indicating how a single switch behaves against the specific packet. So in this way, we need to manually program each switch in the network to enforce a high-level intent, like routing a flow. So the second way is to use the APIs provided by the controller. These APIs are usually bounded to a general purpose language. For example, we can write Python program in RYU controller, or Java program in ONOS controller. The controller APIs facilitates the programming for the network-wide behaviors. For example, we can easily write a routing program according to a map structure that stores the global topology. However, we still need to manually design the algorithms running on the topology. For example, to compose a routing program, we may have to implement a shortest path algorithm using general purpose languages. So the third level of SDN programming is to write a domain-specific program using the network programming languages. We call it NPL, which offers a set of high-level abstractions like routing, waypoint, queues, something like that. So the NPLs are specifically designed for network semantics. which hide most of the low-level details so that the operators could write their programs within minor lines of code. And NPLs provide large efficiency for the operators, so this is focus of our paper. In practice, the high-level programs written in NPL will be translated into NDP configurations for each switch automatically through the so-called NPL compiler. And nowadays, multiple NPLs and NDPs interfaces, sorry, open the camera. Multiple NPLs and NDPs interfaces coexist. For NPLs, we have Frenict, PGA, Predict, Snap, Merlin, and something like that. And for NDPs, we also have classical OpenFlow, NetConf, NetASM, and the recent P4. So according to 2 recent surveys, more than 15 NPLs and more than 10 NDP interfaces coexist in current networks. And we believe such diversity of NPLs and NDPs will persist in the near future. And the reason is twofold. First, the features of different NPLs and NDPs are different. For example, the operator Alice wants to deploy 2 programs. One is routing the packet with a waypoint, and the other is a stateful firewall that checks the TCP connection. The routing program needs the path control semantics in the NPL, which can specify the internal paths in the network, while the firewall program needs the stateful abstractions that can record the state of the TCP connections. So intuitively, Alice would use Merlin to write the routing program, since she can specify a regular expression as the following path with Merlin. And she would use Snap to write the firewall program, as it provides variables to record the network state. So we emphasize that Merlin does not support the stateful operations, and Snap cannot control the internal path. So these 2 NPLs cannot prevail the other in this case. And the second reason that we think the multiple NPLs and NDPs would coexist is that deploy a unified NPL or NDP in current networks is very risky and costly. These are the mainstream NPLs before 2016, and it showed that NPLs are frequently updating. We are proposing many more NPLs. And similarly for the NDP, deploying a unified NDP may cost much more money for buying new devices and retraining the operators. So given the fact that multiple NPLs and NDPs will coexist, we believe that the operators may have to deploy programs written in different NPLs in a single network for drawing all their merits. And they may have to port programs into different NDPs to serve the heterogeneous networks. However, unfortunately, the current monolithic compilation process of NPLs provide neither of the above features. So what is the monolithic compilation? For each NPL, an individual compiler would translate its program all the way into the specific form of NDP configurations. That's the monolithic compilation. So for Merlin, we have a Merlin compiler. And for Frenict, we have a full Frenict compiler. Such compilation scheme would raise many problems. The most critical one is that the cross-NPL program cannot interoperate in a single network. Consider these simple networks. The Merlin program may set a waypoint B for flow, and its individual compiler interprets this intent into the path A, B, D. And another Frenict program may set another waypoint C for the same flow, and its individual compiler chooses to route it with the path A, C, D. And obviously, it will generate a rule conflict at switch A. And here we want to emphasize that the rule conflict does not mean an intent conflict. For example, in this case, we can use a new path like A, B, C, D to satisfy both intents for the programs. But such solution cannot be obtained without the high-level intents. So it is not possible if we only have the generated OpenFlow rules, something like that. And the second problem raised by the compilation process is that the NPLs and NDPs cannot independently evolve. So note that inherit compilers from Merlin and Frenict only produce the OpenFlow rules as the NDP configurations. So now we consider Snap a new NPL, whose inherent compiler produces the net ASM configurations. And so we cannot directly deploy a Snap program in an OpenFlow network unless we implement a completely new compiler for Snap that generates the OpenFlow rules. Similarly, since Merlin and Frantic only produce the OpenFlow rules, their programs cannot run in the OpenState networks. So in summary, assuming that we have M NPLs and N NDPs, if you want to let every NPL program to properly run at every NDP networks, then we need to implement M times N compilers, which would be a huge burden for both NPL and NDP designers. So to address above two problems, we turn to the successful PC compilers, which is an intuitive choice. So in PC systems, we also have many languages, C++, Java, Python, and also have many targeted instructions like x86 and ARM. So the PC compilers firstly compile their programs into a unified intermediate representation, IR, usually in LLVM form. And the IR is then translated, into an optimal form. Finally, the optimized IR is translated into the target instruction. This scheme divides the compilation into three stages. The front end that translates the program into IR, and the middle end that optimizes the IR, and the back end that translates the IR into the target code. So making analog to this successful scheme, what if we also adopt this scheme for NPL compilation? So each NPL has a same front end that translates its program into a unified NPL IR. And each NDP has a lightweight backend that translates IR into its configurations. In this way, the above two problems are naturally addressed. First, the cross NPL programs can be composed at IR level. And we only need M front ends and N backends to let every NPL program run at every NDP networks. Obviously, here the most critical part is the IR for NPLs. And then the intuitive question becomes, what is a good IR for NPL compiler? So the answer is also very straightforward. First, the IR has to be expressive so as to cover most of the NPL semantics. And second, the IR should be composable so that we can interoperate multiple NPL programs at the IR level. So now we present the design philosophy of our proposed IR. We start from revisiting the common programming needs from the compilers so as to ensure the expressiveness of our IR. The first one is to control the following paths, possibly with a waypoint. To express these semantics, the very intuitive choice is to leverage the regular expression. For example, a waypoint B can be expressed as a regular expression dot star B dot star. And we can draw the corresponding automaton for this regular expression. Here we have 4 nodes. Node 0 means the packet is ready to enter the network, and the accept node, node 3, means the packet just left the network. So the symbols in the transition, means the acceptable next hop for these semantics. So it can be easily verified that all acceptable sequence for this automaton must traverse switch B once and only once. So this automaton is the basis of our IR, since it perfectly expresses the hop-by-hop path control. The next semantics we consider is the path control with the resource requirement. For example, to route a flow with 100 megabytes bandwidth reserved. To express these semantics, we need to consume the resource through preceding the automaton. So this is a basic automaton with a simple end-to-end routing, right? And we can extend the loop transition at node 1 so that each transition inside the network would consume 100 megabytes bandwidth for that hop. The last semantics we consider is the stateful operations in the switches. For example, we can count all security packets at a certain switch. And to express this semantics, we need to check and update the network variables when proceeding the automaton. So this automaton shows that the counter update operation should be performed once and only once through the routing path. So putting all this together, we can obtain our IR for NPLs, which is the network transaction automaton, NTA. And we'll first define the network transaction. Network transaction is 3 tuples, HRD. H is the next hop to be forwarded. R is the consumption of the network resources in that hop. And D checks and updates the network variables. So each transition in NTA is a network transaction. And the automaton actually is a language of all legal sequences of network transaction. The compilation of NTA is to produce a sentence from the language according to the physical topology and the network resources. So having this design, we intuitively raise 3 questions about it. First, can NTA express most semantics from NPLs? And second, can NTAs be composed without semantic loss? And finally, can NTAs be efficiently compiled into NDP configurations? And in this workshop paper, we only discuss the first 2 questions and leave the last one to our future work. So let's first talk about the expressiveness of NTA. Actually, we have considered most common needs when designing NTAs in the first place. So here we give some examples of how NTA express the programs written in mainstream NPLs. So this is a Marine program, which defines a policy that routes IP1 to IP2 with a waypoint B and with 100 megabytes bandwidth reserved. So the corresponding NTA is quite simple. The first tuple of each transition represents the waypoint semantics, and the consumption R1 indicates that 100 megabytes bandwidth should be reserved for each link it traverses. The next example is a snap program that counts every packet sent from IP1 to IP2. And we use a variable number of packets here. So its NTA is also quite simple, like we presented in early slides. And here we give more examples of using NTAs to express NPL programs. For these 2 end-to-end routing semantics written in Predict and Netcat, and we can use a very simple NTA to express. It's just an end-to-end routing, right? And for flow log program that blocks some IP addresses, we can use a variable to record the blacklist. We can use a variable to record the blacklist and forward such packet to a black hole. And this is a PGA policy graph that specifies a waypoint region, and we can simply use a waypoint NTA to express it. So we believe these examples can partially confirm that NTA is expressive enough for mainstream NPLs. And you can find more analysis and examples in our paper. Next, we want to discuss the composition ability of NTA. Composition is possibly the most wanted feature from the NPLs, as it can enable multiple programs running in the same network. We know that NTA is an automaton, right, which largely facilitates the design of composition because we can directly adopt many classical operations of the automaton as our theoretical basis. So specifically, NTA supports 2 kinds of compositions. First is the parallel composition, which maps to the intersection of NTAs. So the parallel composition of 2 NTAs would produce a new NTA that accepts the original 2 NTAs simultaneously. So for example, we can parallel compose a routing program and a failover program so that we can route all traffic properly while protect some certain traffic. The second type of composition is the sequential composition, which maps to the concatenation of NTAs. The sequential composition of 2 NTAs would produce a new NTA that performs the original 2 NTAs sequentially. So the typical example is that we may sequentially compose the failover program and a counting program. So the later one only counts the suspicious flows identified by the Federal program. So in this talk, we omit the formal definition and analysis of compositions, but give an intuitive example of parallel composition to show how it works. Recall that the two NTAs for Marine and SNAP program. And if we parallel compose them, we can obtain a larger NTA like this. And it can be easily verified that this NTA accepts the intersection of the original two NTAs, which expresses the semantics that forwarding the packets with 100 megabytes bandwidth while traversing B and counting them. So for example, consider the following acceptable input sequence. So the first transition is transition 0 to 1, which means the packet just enters the network. And maybe we will take the next transition, transition 1 to 3, and which means the packet traverse B, and with the reserved bandwidth. And then we take transition 3 to 4. This is a joint network transaction that counts the packet and forwards the packet to another switch with the reserved bandwidth. Finally, it may take the transition 4 to 5 to leave the network. So the above is the major contributions we made in this paper, and there are still lots of possibilities to be explored in our future work. First, we want to talk about is the semantics completeness of NTA. Currently, NTA only supports the static semantics like routing, resource consumption, something like that, but cannot express the dynamic ones like latency negotiation in the real time. So, but it's possible to achieve that if we further extend the expressiveness of the transition in the NTA. And second one I want to discuss is that currently we only implement the most critical optimizations, which is the composition. But it is also possible that we can perform more optimizations upon NTA, like network verification, which is also would be very interesting. Finally, we want to raise a technical challenge when we want to employ NTA into a real compiler, which is the efficiency of compilation. Current compilation techniques usually adopt the mixed integer linear programming, which would quickly grow to an unacceptable scale in a large topology, especially when we considering that NTA carries much richer semantics than other representations. Besides, there are few works that can compile programs into the heterogeneous networks. So that's also should be considered in our future work. And to conclude, in this paper, we demonstrate that multiple NPLs and NDPs would coexist in the near future, which makes the IR a necessity in the NPL compiler if we want to interoperate the cross NPL programs and develop NPLs and NDPs independently. And in this paper, we propose NTA as the IR, which is expressive for many NPLs and is composable without semantic loss. And please refer to our paper for more details, including the formal analysis and composition efficiencies of NTA. Okay, that's all. Thanks for your attention. I'm happy to take your questions.
Thank you, Hao, for a great talk. So are there any questions for Hao? So Professor Dong-Soo Han, you can ask a question.
Yes, thank you for the great talk. So I was wondering, you started from a DFA as an intermediate language, right? So
Right.
Do you see in the future any need for extending it beyond DFA and maybe go into a full-blown intermediate language like any other intermediate language that we have today?
Okay. So the question was about the why we use DFA as a basis of our intermediate representation, because
right.
The intuition here is that the network itself is a graph, right? So the packets, the behavior of the packets is just like the triggering the automaton in the network. So DFA is perfect for expressing such hop by hop behaviors So we forward the packet from this node to another node. So each node in the DFA can map to multiple physical switches in the physical topology. So we believe that DFA could be a good basis so that we can review the internal behavior of each hop. And we also know that there are other representations like FDD in XFDD used by Snap, but they are assuming that the network is one big switch, so they don't control the internal paths. They just want to properly process the packet in an end-to-end way. So many representations can be used for realizing the specific features of their own languages. But if we want to drawing all their merits, we think DFA could be a good start.
Okay, are there any questions? Other questions? I don't see any others. So let's thank the speaker. So thank you very much, Professor Hao.
Thank you.
Yep. So we can switch to the next talk. Okay, so let me check the schedule. Yeah, okay. So our third talk is again from authors of KAIST. Our presenter will be Dak-Woo Kim. He is a graduate student from Networked and Distributed Computing Systems Lab in KAIST. And he's going to be talking about a really cool way where we can offload TCP and TLS handshakes to SmartNICs. So Dak-Woo, if you can hear me, you can try sharing your screen.
Okay. So, can you hear me?
Yes, I can hear you, and the screen is also visible. You can start off anytime you want.
Okay. Okay, hello, my name is Dak-Woo Kim, and I'm going to present the paper, Case for SmartNIC Accelerated Private Communication. Yeah, so most of network communication throughout the internet use secure communication, online meeting, mailing service, SNS, and online shopping. To protect private information and sensitive content, this network application encrypts user data and prevent a malicious one to eavesdrop them. Also, you can find most of web pages use secure connection as default. It is known that over 70% of whole internet traffic is encrypted with TLS since 2018. Yes, secure connection is common now. However, there have been a trade-off between security and performance of web server. Below figure present Nginx web server evaluation, where clients download 1 byte file from single web server with HTTP and HTTPS respectively. So as you see, the orange one, the web server shows really poor performance when it serves HTTPS connection, from 12 to 33 times slower for a different core number. So why does it happen? In the case of TLS, there are two major workloads added. First of all, after TCP handshake, a client and server should process the TLS handshake, which include the server authentication and session key exchange. In here, client and server generate one shared session key, which will be used during subsequent connection. In here, an asymmetric cryptography like RSA and ECC is often used here. And second, data encryption. After a TLS handshake, client and server should encrypt their message before they send, and they should decrypt the data when receive the data. In here, they use symmetric key or shared key generated at TLS handshake. And the most popular example is AES. So both factors affect the performance of the web server, but their features are different. data encryption have a variable overhead by message size. That is, the overhead becomes significant when serving large file like video streaming, and it is less serious for short-lived connections. Also, there are existing optimizations such as AES-GCM and AES-NI, which make CPU core treat them well. However, TLS handshake always do same process regardless of the message size, so it becomes critical for short-lived connection, like 1 byte file download. Also, CPU is relatively poor at asymmetric cryptography used in key exchange compared to the data encryption. So it is obvious that the TLS handshake is the main reason of low performance of before the benchmark. So there are one alternative to address this problem. Use dedicated accelerator for key exchange. So in this case, the data flow is shown like a following figure. So when the processing TLS key exchange, CPU send the crypto information to the accelerator, then the accelerator operate the crypto algorithm instead of CPU. After processing, the accelerator send the result to the CPU, and CPU resume the handshake. While while this can largely boost TLS handshake performance, there are still a few challenges. First of all, the data paths become longer. CPU and accelerator should send data to each other. In these figures, step 2 and step 4. This makes DMA overhead and lengthen the latency. There are another issue. If we do not consider accelerator, CPU get encryption in place and it continue the key exchange. But in using accelerator, the program now should be aware of the accelerator, which with its own API and design, which is not compatible with the legacy program that do not use the accelerator. For example, after step 2 in the figure, CPU should not be blocked and receive results using event pulse or signal from the accelerator. It is implemented using the asynchronous API that largely modifies the application that have used synchronous API. So therefore, we propose the smart TLS. All TCP and TLS handshake is offloaded into network card, especially SmartNIC. The SmartNIC, as known as the programmable NIC, is offloaded in So programmable NIC has its own embedded system, including processor, memory, and crypto accelerator. Compared to the ordinary NIC, it can perform a quite complicated operation. So when the client tries to connect with server, the SmartNIC process TCP handshake first, and then the SmartNIC continue the TLS handshake too. And then after TLS handshake, the SmartNIC send the connection information to the host CPU. And then the CPU processed other data encryption and other state management for this connection. There are 3 advantages with smart TLS. First of all, host CPU does not care until a handshake is completed. This means CPU only treats the data encryption-decryption. That saves the CPU utilization. Second, SmartNIC can exploit accelerator, so that boosts the overall performance. Last of all, this design still presents synchronous API, and the programmer can program application with Apnet SSL-like API, but not using the asynchronous mode. So now we are going to introduce challenges on SmartNICs. We met and our approaches for each other. The first challenge is that the TCP state tracking is too complex for a NIC. You know, TLS protocol is over the TCP stack layer, so offloading TLS handshake means offloading TCP too. It includes the TCP handshake, retransmission, duplicated ACK detection, congestion control, and so on. Obviously, SmartNIC processors are not so good compared with the host CPU, so it seems impossible to implement all into the SmartNIC. Then the advantage of the smart TLS will disappear. So our answer is that actually we do not need to consider all of them, since TLS handshake can be offloaded with minimal flow stage, simple enough to be implemented into SmartNIC. So the entire process is divided into 2 phases, TCP handshake and the TLS handshake. First one is TCP handshake, which below figure shows. The key point is that using same cookie so that NIC does not store any state for establishing connection. When client sends SYN packet to the server, SmartNIC replies SYN packet, but instead of storing the connection state into SYN queues, it generates a cookie using a 4-tuple information and set the cookie to the sequence number. In here, sequence 2. When client sends packet, the egg number should be the cookie plus 1 value. So SmartNIC verify this by reassembling sequence number again using same algorithm. So in this way, SmartNIC can process TCP handshake in a stateless manner. The next phase is the TLS handshake. The figure shows the abstract of the TLS handshake. So client send client hello first, and then the server reply the server hello. Then server send client key exchange packet again. Then the server replies the finished packet. Then client and the server communicated with encrypted data. Basically, it should be operated over a TCP stack, ensuring reliable transfer. However, as you see, handshake process is finished only in 1 to 2 RTT, so it is really short. Also, the packet size is not very large. So even though server use very large certificate like RSA 4096-bit, the data transfer during handshake is not huge at all, packed inside just few packets. So these two facts leads us to adopt a passive reaction on SmartNIC. So SmartNIC only react with receiving packet and do not manage the connection during the TLS handshake. So so SmartNIC does not detect the packet loss nor actively retransmit packet. Instead, SmartNIC exploit the client for inferring packet loss and retransmission. Now, yes, let's see the client send the first handshake packet. So client hello. Then the SmartNIC only prepare the proper reply and respond. Yes, the packet loss occurred. However, SmartNIC does nothing in here. Then the client detects the packet loss and retransmit the packet again. Then SmartNIC do same thing, only react current received packet. And when client get the packet, it sends second handshake packet, client key exchange. Then SmartNIC read the packet and appropriately respond following the packet type. Of course, if packet loss occurred in the second RTT, SmartNIC also does nothing and just wait the client to retransmit the packet. Then after they use the encrypted application data. So these two ways largely relieve the burden of SmartNIC, work well in most average case. In detail, SmartNIC does not consider the flow control, congestion control, and retransmission. And SmartNIC only needs to hold and manage following things. 4-tuple of connection, which is used to make a SYN cookie and identify each flows. A handshake package, which should be used at the last stage of the TLS handshake. And the global timer needs to remove stale connections, like client does not send next handshake packet for a long time. And note that managing this does not require lots of CPU cycles. SmartNIC can successfully offload the TLS handshake with limited resources. And so second challenge is that SmartNIC processor should handle application packets after handshake, because packet first enter the SmartNIC embedded system first, and then forward it to the host. Again, SmartNIC has not enough computational power compared to the host CPU, so that even just forwarding packets for long-lived connection like video streaming cannot be processed at fast speed in the SmartNIC. Therefore, SmartNIC should process only handshake packets if possible, and application data should bypass the SmartNIC embedded system. To resolve this, we explore the hardware packet switch equipped on the SmartNIC. The Bluefield SmartNIC that we used has embedded hardware switch where a NIC processor can dynamically install traffic control rule. So in default, the switch forwards packet to the NIC processor. Therefore, TLS handshake is processed at NIC processor. But after TLS handshake completed, the SmartNIC send the connection information to host CPU, and at that time, NIC install the redirection rule for that designated connection. After installed, hardware switch now redirects all package matched in that rule to the host directly, bypassing SmartNIC system. So yeah, like this. After connection closed, NIC removes the rule. But however, this approach has one limitation. Actually, installing a single TC rule takes about 1 millisecond. So this will create an extra latency. Nevertheless, the idea is still able to be used for long-lived connection, with which lasts for a few seconds to minutes. SmartNIC will not care about that heavy network I/O and purely focus on short connections. Then how to find the connection is long-lived or short-lived? Actually, we'll leave this question in the future work. Maybe CPU can tell SmartNIC to install T0 or some method, but we don't cover this. The last challenge is about the unfair load distribution. So when most of the connections are short-lived, SmartNIC should establish too much connections at once. When the workload exceeds the capacity of the NIC processor or accelerator, SmartNIC can't handle every connections, while host CPU utilization remains low. So our approach is opportunistic offload. SmartNIC does not offload TLS handshake when it is too busy. So this is our design again. When too much new connections are incoming, SmartNIC core and accelerator can be overloaded. Drop some connections, but while the CPU gets less workload. But with the opportunistic offload, SmartNIC checks whether it is now overloaded or not, and do not process TLS handshake if SmartNIC is already handling maximum connections. Then SmartNIC only process the TCP handshake and send the TCP information to host. After that, host handle all the TLS handshake and application data instead of the SmartNIC. So both SmartNIC and host process TCP handshake. When forwarding package, NIC might use hardware switch explained above to reduce overhead, but our current implementation do not make use of it due to the latency issue. So we implemented our Smart TLS into two spaces, SmartNIC and host. On SmartNIC, we implemented TCP and TLS handshake protocol using DPDK. On the host, we modified mTCP, which is existing user-level TCP stack, to implement the TLS handshake, same with SmartNIC, and to present the OpenSSL-like API, synchronous API. And then we implemented a web server which supports the TLS 1.2. We don't explain the details here, and to get further information, please refer our paper. I'm sorry. Now we are going to explain our evaluation of our work. We measure the performance of one server with 4 clients, and below is the machine specs. All server and clients have same CPU, DRAM, and server used this Bluefield SmartNIC, and the client used the normal conventional NIC. About TLS, we consider the TLS RSA with AES 256-bit GCM and SHA-384. And the baseline of the evaluation is Nginx server, which uses the Linux TCP stack. So we present the 2 evaluations here. First, handshake performance. Client connects the TLS session and immediately close. And below compares the throughput of the TLS connection setup. X-axis means the number of the host CPU cores of web server, and the Y-axis means the number of the TLS handshake per second. The Linux TCP means the baseline, Nginx server. And the user level TCP is our implemented mTCP application, but without the SmartNIC. And finally, the Smart TLS is our application with SmartNIC. So this shows that the SmartNIC can perform about 5 CPU cores too. The overall performance is accelerated by 1.7 to 5.9 with a different number of cores. And please note that the opportunity offload is applied here, and the performance is still scalable when CPU cores increases. Nevertheless, the TLS offload gets best advantage when host CPU is weak. In this case, at the 1 core. And the second evaluation shows the web server performance with mixed workload. Clients download large and small file all together. So x-axis means the concurrency of the short connections. So the leftmost part, it means the 0 short-lived connections. It means that the client purely download the large file, which can saturate the link. However, as more and more short-lived connections added, baseline Linux TCP cannot properly handle large file data I/O due to the short connections. On the other hand, in the case of the Smart TLS, all heavy TLS handshake is offloaded into Smart NIC, so the host can focus on data I/O and still saturate the link. So we want to explore the potential of the offloading TLS handshake into network card using Smart NIC. And we designed architecture with dualized processing unit and implemented it and evaluated. So our Smart NIC shows that it can reduce CPU overhead, improving the performance. And there are still future works we lived, but we believe that the TLS handshake has potential to be offloaded into hardware in the future, as TSO, LRO, and TOE is already implemented into NIC now. Yeah, and thank you for listening, and I happily take the questions.
Thank you very much for your talk, Dakwu. So are there any questions for Dakwu and his team? We are way ahead of time, so we can ask questions.
So I have a question. Can you hear me?
Go ahead.
Okay.
Yes.
So in this presentation, I saw there are few NICs. One is Mellanox Bluefield Smart NIC. One is Intel Smart NIC. So the final test result is based on Bluefield or based on that Intel NIC?
So yeah, we evaluate with the Mellanox Bluefield Smart NIC.
Okay. So did you compare with NIC without the offload TLS offload, or you only compare with the kernel TLS?
So did you mean that the...
Okay, so you mean the kernel TLS use standard NIC, then use the kernel to run TLS, right? This KTLS, the comparison data. Can you go to the benchmark slide?
So the question is the comparison about the QTLS, Intel QTLS, right?
Okay.
So actually QTLS has really good performance due to the great accelerator, which is Q80, and its own asynchronous design with OpenSSL and Nginx. But in our work, we use the Mellanox Smart NIC, but if we use the more good accelerator or the Mellanox Smart NIC is upgraded, then this design will still have the advantage. So the main point is the design that offload the TLS handshake has some potential. So using the which accelerator is another problem, I think. So we can use the we may use the Q80 with our design. So yeah.
I see. Oh, thank you.
Are there any other questions for Dakwu? Okay, I guess I can ask one question. Actually, Litong from Huawei is interested in asking a question. Litong, can you speak up?
Yes. Can you hear me?
Yes, we can hear you.
Very nice talk. I have a very small question about the handshakes. We all know we have some technologies are using the 0 RTT or 1 RTT handshakes for TLS, for example, Quick. And
Yeah.
for this kind of technologies, so how does your solution interact with this kind of technologies?
So actually, now TLS 1.3 is released and it supports the 1RTT, and even the Google Quick support the 0RTT, right? But yeah, that's right. And so the idea is the same. So because the handshake process is really simple, so in the case of the TLS 1.3 or the Quick, it still needs the asymmetric crypto algorithm, right? Which is quite slow in the CPU. So we can also offload it into the network card. So yeah. So we may make use of other crypto protocol, like the Quick or DTLS or other things.
Okay, thank you.
I guess I have one question. It was really interesting talk, Daku. How would you compare the performance or the ROI, return on investment, on a solution where we're offloading TLS to SmartNICs, for example, Bluefield SmartNICs, compared to a GPU-based offloading SSL engine? So that what I'm trying to say is that when it comes to cost economics, what would, based on performance to cost to performance ratio, is GPU offload technique more beneficial or SmartNIC offloading technique more beneficial?
In frank, actually now the SmartNIC is quite expensive because it is not off the shelf and it is only used for the research and or some specialized case. So the SmartNIC is actually some quite expensive in terms of the cost efficiency compared to the GPU. So actually now the using GPU may be more GPU or using dedicated accelerator might be more cost efficient, but if the SmartNIC becomes common and when the SmartNIC and this TLS offload accelerator it becomes normal, then the price will be lower. So now the SmartNIC is not the commonly used, so cost efficiency is not very good at this time.
Okay, makes sense. Okay. So I guess these are all the questions that we had. Thank you very much, Daku. Well, by the way, so we still have time. I have one more question. What happens if I can come up with a security attack in which we just blast tiny packets, where the keys can be divided into multiple TCP packets? How will the SmartNIC solution be helpful in that case? Because you'll have to end up reassembling TCP packets or quick packets or whatever. So my question is, like, can you support reassembling in the SmartNIC, or is it too challenging, too costly?
I'm sorry, but can you explain your question one more time?
So I'm assuming the SSL keys would be in a payload, right? So
yeah, that's right.
What if there's a security attack in which we just split the packets into tiny segments so that the entire SSL message is split up into multiple packets, right? That in that case, the package will have to be reassembled. Can SmartNIC reassemble those things and then do the TLS calculation?
Now current Smart TLS implementation can reassemble the TCP package which to make the one TLS record. So
okay, it can. Okay.
Yeah.
Okay. Okay.
It is possible to see the multiple and its minimum per flow stage. Yeah.
Okay.
Using that stage, we can implement this.
Okay. 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 Thank you very much, Daku. once again. So we can move on to the next talk. This is going to be the final talk. Go ahead. I think there's a question.
Yeah, hello.
Juan?
I'm sorry. Yeah.
Yeah,
So
Juan, yes. Question, go ahead.
So I have one small question. So like, thank you for the very interesting talk. So I understand that the Mellanox Bluefield has 8 ARM cores inside, right? So, and you are leveraging those 8 cores for your acceleration, is it correct?
So do you mean using the ARM core accelerator or
Yes,
another?
so when you are doing the acceleration inside of the Mellanox Bluefield, are you using the ARM cores there as well?
So now our smart TLS only cover the TLS handshake, not the data encryption like the AES. So actually we do not use the ARM core accelerator, which is for the AES encryption. But we used another dedicated accelerator equipped it in the SmartNIC, which can operate the public crypto acceleration. So like the RSA or ECC. So using that accelerator, we do the we design the smart TLS and implement it.
Okay.
Okay, I guess we're out of time, but thanks a lot for your questions. And Aku, thank you very much. So we can now move on to the last speaker. So our final talk is from Lizo Yu. Lizo completed his PhD in information engineering from the Chinese University of Hong Kong. He is now a research engineer at Huawei, and his research interests lie in the computer networks and wireless networks, and he has recently been working on network verification. So he's going to be presenting a network configuration verifier for DCNs. So take it away, Lizo. I can see your screen, and you can start talk. You can start the talk.
Okay, can you hear me?
Yes, perfect.
Okay. Hello everyone. This talk is about fast configuration change impact analysis for network overlay data center networks. I'm the first author and initiated joint work with my colleagues at Huawei. Network overlay data center networks are widely adopted by device vendors such as Huawei and Cisco to build enterprise private cloud. Similar to a DCN for the public cloud, the fabric also uses a spine leaf architecture, including the tall leaves, spines, border leaves. The fabric also has firewall, load balancer, and other middle boxes, and provider edge routers. Different from the host overlay solution, network overlay solution places we-extend tunnel endpoints and distributed gateways such as Layer 3 virtual bridge domain interface (VBDE) on tall switches. They use distributed BGP EVM protocol to establish we-extend tunnels and to advertise overlay rules. In addition, they place ACL and the micro segmentation policies to control the traffic access. There is also a SDN controller in the network. To deploy a new service, users design a VPC network and specify the policies through a controller. And the controller generates the Delta configurations and push them to the network switches in the fabric. In this network, we are interested in the all-pair reachability change problem. Initially, there are some endpoint interfaces that owns the service virtual machines, and we can construct the all-pair reachability matrix that shows the mutual reachability of these endpoints. After Delta configuration are generated, before they are deployed to the fabric, we would like to see which elements in the matrix will change. In this way, users can check whether these changes justify their intent and whether they have specified the correct policies. To find the reachability changes, the simple solution is to recompute the whole metric. By comparing with the old metric, we can easily find the change elements. However, this approach is not scalable, given the potential large number of endpoints in the network. A better solution is to identify the possibly changed pairs and recompute these pairs only. There are some existing incremental approaches. However, they don't completely address the new challenges introduced by network overlay data center networks. The first challenge is about model expressiveness. There are several new features in the network. The first one is tunneling, where both underlay and overlay packet exist. This figure shows the VXLAN frame format. We can see that for the overlay packet, there is an additional outer header and a VXLAN header. For underlay packet, only the inner frame exists. Inside the VXLAN header, there is a VNI field, which represents the VPC that the packet belongs to. A packet may go through several tunnels. For example, endpoints A and endpoint C belongs to two different VPCs. To support cross-VPC communication, cross-VRF setting rules are usually configured in border leaves. In this way, the traffic from A to C will go through two VXLAN tunnels, which means it will rewrite the VRF field in the packet. Another notable feature is microsegmentation, MCS. For MCS, policies are defined on groups instead of individual IPs, and the group definitions are distributed. Take the same network, for example. Group 10 is defined on A with IP 1110/24 and 1120/24. B may also define the same group 10 with 1130/24. And the group 20 is defined on C with IP 114.0/24. And the policies is defined on groups. The packet that belongs to source ID 10, destination group ID 20, and the source port 80 is denied. Given these new features, existing BDD-based equivalence classes, EC approaches such as APV and APKeep, and the ternary bit vector-based EC approaches such as Veriflow and DataNet may not work. The EC computation model doesn't support tunneling. Meanwhile, extensive packet rewrites may lead to performance degradation. On the other hand, the TPV model depends on IP rules instead of group ID rules. Although we can construct the IP rules from MCS policies, the rules may be excessive and may be invalid in some times. The second challenge is to improve the indexing method. The key idea of an indexing method is to store some information about network and the reachable pairs. If part of the network changes, we can find affected pairs and recompute these pairs only. Take the Tanner graph method, for example. In this paper, after we compute a reachable path, it will associate the visit device with a reachable pair. In this example, we have two reachable paths, A to B and A to C. They both visit the device B1, so we can establish a table B1 with pair AB and AC. If any changes happens on device B1, then we can look up the table and recompute the pair AB and AC. This approach narrows down the recomputation scope and can find the reachability changes. However, the device level association is coarse-grained and inefficient. If a change only happens, only affect the pair AC, for example, the device, the interface E in device B1, actually there is no need to recompute the reachability of AB. Therefore, interface level association may be more preferable. Another problem is that this approach could not find new reachable pairs, since no association is established initially. Take the same network, for example. If we add a static node on B2 to allow traffic from A to D, since B2 doesn't have traffic initially, we cannot trigger the computation of the pair AD, and therefore we will not find a new reachable pair AD. Given the above problems, we present our solutions. This figure shows the architecture of our verifier. We follow the control plane verification approach. Configurations are first simulated to generate FIPS, and then we perform reachability analysis. And our verifier supports the CLI based configuration and the Young incremental configurations. There are three key components in our verifier. We adopt the BDD predicate model to build a forwarding graph. After computing the all-pair reachability metric, we establish a fine-grained indexing table. For the delta configurations, we first find the changes interfaces. Using a waypoint path computation approach, we can find all relevant reachable pairs. And with the indexing table, we can do comparison to get the reachability changes. We first introduce our port predicate model. In this model, we will define a symbolic packet with reachability relevant fields, such as outer IP headers, group ID, VNI, and the inner IP headers. Then we use Boolean formula to encode each packet. Each bit is a predicate. Xi means the bit is 1. Negative Xi means the bit is 0. True means this bit is either 0 or 1 or irrelevant. In this way, we can encode each packet as a function fx. Furthermore, we can define the IP header space Gx by intersection union difference of all packets. Notice that all Boolean formulas are represented by BDD. This BDD is an efficient data structure for Boolean formula operations. Then we present our forwarding graph model. For each device, we aggregate the internal processing and only keeps the inbound interfaces and outbound interfaces. For example, this device has inbound interface BD interface 1 and outbound interfaces NVE, BD interface true and deny, while NVE is a VXLAN tunnel outgoing interface. The edge from BD interface 1 to NVE means that some packets can be forwarded between the two interfaces. Therefore, this edge has a header space constraint that aggregates the null space of the ACL constraint in BD interface 1, the FIB forwarding constraint, and the ACL constraint in NVE interface. Together with the forwarding topology, we can define the whole network model, where nodes are the forwarding ports, and each edge has a header space constraint. We enhance our predicate model with quantifiers. In the new predicate model, we can differentiate the underlay and the overlay packet using quantifiers. We can use a universal quantifier to check whether the packet has a VNI field. If the assertion is false, then it's an overlay packet. Otherwise, it's an underlay packet. On the other hand, the existence quantifier can be used to input the packet rewrite. The existence quantifier removes the original constraint on a particular field. Combined with the intersection operation, we can set a new constraint on the field. These two cases cannot be represented using predicate only. Predicate conquer improve our model expressiveness. Then we have an abstract forwarding graph for the all-pair reachability computation. We first define some endpoints where virtual machines are attached. They are both starting nodes and ending nodes in our graph. We perform a depth-first search for each starting endpoints. The DFS backtrace when it finds an endpoint or its header space become empty. In the end, it will find all reachable paths and endpoints. In this way, we can build an initial all-pair reachability metric with reachable paths and reachable header space. Meanwhile, we can analyze the reachable paths, find the visit interfaces, and establish an indexing table. Take a reachable path A to B, for example. We can link the outbound interface 1, inbound interface 2 with the pair AB. So the complete table is shown on the right side. Then we consider the change impact analysis. After simulating the delta configurations, we can construct a new forwarding graph. By comparison, we can find the change interface with new header space. The change interface are divided into 3 categories: delete, modify, and add. To avoid the potential miss, we use waypoint computation to find all new reachabilities due to change interface. For each change interface, we issue a forward search and find all forward paths. Then we issue a backward search and find all backward paths. By cross-producting these paths and eliminating paths that don't have intersected header space, we get final reachable paths and reachable pairs for each change interface. Then we do comparison to find the reachability changes. First, we've got the new reachability pairs by waypoint computation. By looking up the indexing table, we can get old reachability pairs using change interface as keys. Then comparing them, we can get reachability changes, which are also classified into delete, modify, and add. In this way, we can find all the reachability changes. Next, we show some preliminary evaluation results for our configuration web file. We implement our web file based on open source backface. We made some enhancement, including we support Huawei command line and the Yang configurations, and we support the BGP EVPN protocol. For the BDD library, we reuse Java BDD as interface. We use synthesized datasets to evaluate the performance. These datasets are similar to the configurations in real networks. We construct some base datasets that have both inter-VPC traffic and intra-VPC traffic. The number of tall leaves is varied from 20 to 100. Each leaf have 20 endpoints interfaces. So the maximum number of endpoints is 2000. For the Delta configurations, we simulate 4 service update cases, such as at subnet, at VPC, at crosswalk setting rules, and modify MCS policies. We measure the incremental verification time, including the new graph building time, the change interface detection time, the waypoint computation time, and the comparison time. This figure plot the overall change analysis time for our web file. This is a CTF plot. Overall, the time is less than 25 seconds for 2,000 endpoints and 4 million endpoint pairs. For case A to C, the time increased slightly for different networks. This is due to the increased modeling, detection, and comparison time. And for case D, the time increased a lot, and the increase is mostly due to the waypoint computation, because micro-segmentation modification leads to many irrelevant computations. So this part needs further optimization in future. The right figure shows the comparison result with related work, the Tanner-Grad algorithm and the baseline algorithm. For Tanner-Grad, they use device level association, and the baseline algorithm recomputes the full matrix. As discussed previously, device level association may lead to irrelevant recomputation. So its performance approach the baseline algorithm. And our algorithm is smoother and better because waypoint computation only involved with necessary computation. We can see that the improvement is 2 times to 6 times, and it's at the most 6 times for this data set. So before ending, let me summarize my presentation. In this paper, we make the following contributions. We are the first to design and demonstrate an incremental configuration verifier for network overlay data center networks. We also design a fast incremental verification algorithm and leverage fine-grained indexing and waypoint computation methods to find all pair reachability changes. In future, we will further explore new forwarding features such as policy-based routing, firewall zoom policies, and net policies. That's the end of my talk. Thank you for listening and welcome your questions.
Okay, Lizu, thank you very much for your presentation. Do we have any questions for Lizu? Okay, I guess someone is unmuted. Vexley, do you have a question? I guess I'm just going to mute him. Okay. So I guess let's thank Nizu for his talk. And if there aren't any questions, so right now, this is the end of our session. And the next session is going to begin at 1:30 p.m. Korean time. And it's going to be chaired by Dan Lee, and it's going to be regarding SIGCOMM talk sections. So please stick around. We have a break now, and I'll talk to Dan soon. Thank you. Hello, everyone. So I think we're about to start the new session. So if Dan Lee is around, I request him to take over, please.
Yeah, I'm
Okay.
online.
Yeah, I'll stop sharing my screen then.
Okay, thank you.
Okay, all done.
Yeah. I just wait for 2 more minutes and we will start. Yeah. Thank you, Asim. Yeah.
Sure, you're very welcome.
Is Hongqiang online? Hongqiang, are you around? Let's just wait for Hongqiang to get online, then we will start. Okay, Hongqiang, are you online?
Yes, I'm here.
Okay. Good afternoon, everyone. Next is our CCOM talk session. We know that this year there are more than 10 CCOM papers from Asia Pacific area. So before the CCOM conference, we were very glad to invite the speakers to present their CCOM work in our Apnet conference workshop. Our first speaker is Dr. Hongqiang Liu. He's now a senior staff engineer and a director of research development in Alibaba Cloud. He and his group are working on future technologies for cloud networks, mobile networks, and wireless networks. So, okay, let's give the time to Hongqiang. Yeah. Hongqiang, you can start.
Hello?
Yeah, you can share your screen. Yeah.
I tried to share my screen, but it asked me to reboot. I think it's working now. Okay, can you see my screen?
Yes, yes. You can start.
Okay. Okay. Let me show this. Hi, everyone. So I'm very glad to be here to start the SIGCOMM session. And today, I will present an industry paper in this year's SIGCOMM and published by Alibaba and together with Tsinghua, Brown, and Nanjing University. And it's called Accuracy, Scalability, and Coverage, a Practical Configuration Verifier on a Global WAN. So this system is actually, as far as I know, is the first published production system that is a verification system used on a global WAN environment. So this is our motivation of why Alibaba built a network verification tool. Because as the growth of the Alibaba's global WAN and as we support more kind of applications in our ecosystem, we found that it's very hard to keep up with this growth and to make the network as stable as needed. So there are several kind of maintenance risk in our WAN configuration. The first is that there are a lot of latent problems, because the WAN is very unlike with data center. Data center's configuration is generated in a snapshot, but once configuration is accumulated and it's configured by thousands of operators and over years. So there are a lot of hidden problems that will be triggered in the future when we made some update or make some expansion. And then that is one thing. The other thing is that the applications also frequently change their requirement of reachability and the capacity of the network. So the network is keep evolving, and so that every time we change the network, the reliability and stability is the highest priority. And with the increasing size of the WAN, we found that it's harder and harder for human beings to handle that. We have to get a way to rely on some more rigorous kind of technology to help human beings to manage the WAN. So this is why we introduced network verification in Alibaba, and there are actually two parts of this whole system. And we just cited the Monkey King's Fair and Golden Eye, 火眼金睛. And actually last year we published Jingjing, which is in-network ACL verification. And this year we published 火眼, which is a routing configuration verification. So network verification is talked about around the academia and the industry for years, but it only had some kind of a small or kind of specific environment like a data center deployment. This is because on the WAN environment there are a lot of practical challenges that we need to figure out how to solve that before we deploy it. The first is that on the WAN there are a lot of vendors, and different vendors will just implement their routers behavior, and they have different kind of ways to understand the same RFC standard. So that this is very hard to accurately mimic their behaviors to do the verification. And the second is that the WAN network is very large, and the topology is not symmetric, and you cannot use a kind of a trick to handle the larger scale. And it have to be very scalable in your general topology and with a large number of IP prefix devices, links, and data centers. And the third one is it has to handle multiple protocols, because on the WAN we have, for example, we have eBGP, IBGP, ISS, OSPF, and routed, and also ACL. So it kind of coupled together. You have to support them all. And the finally is that we are facing failures. There are a lot of uncertainties, and in academia, people mostly talk about the failures like link failures, switch failures, but we also find that something like non-deterministic arrival of routing updates will also create some critical problems. Later, I will explain it. So that, when we start to design Hoyan, so we clearly, we talk to a lot of operators and clearly list what we want and what we don't. And these are all the properties that in academia and industry people used to talk about. And but we should make it clear that which one is mandatory and which one is preferred. That means that it's better to have, but not as important as the mandatory one. And which one is optional, which means that I can just give it up if for some scalability or some other purpose to guarantee that the mandatory is achievable. So that when you just look at the properties in this way, you can find that, for example, for the simulation-based verification like Badfish, CBGP, we find that it has very good scalability, which is good. And because the simulation, it can cover almost all the protocols. But of course, it is famously, it has the problem to handle the failures like K failures, because it's a simulation. And when you want to handle the K failure, you should just enumerate all the cases, which is combinatory. So it's not scalable. And on the other hand, like a formal, like pure formal modeling based, like Minesweeper, and it has very beautiful, property that you handle, the protocol coverage, the uncertainties, the failures, and also the general route input. But it kind of pushed the technology in another extreme that, for this property, it has poor scalability, especially on our one. And the third one is kind of a graph-based. It's also well known that it can only handle some kind of graph-based like OSPF routing, but it has a problem to support BGP, especially when BGP has some specific policies. And if you look at all of them, they all suffer one problem that they never talk about, is that as I mentioned before, so due to the vendors' heterogeneity, so there is a serious correctness problems in all the verifiers. And this is a practical problem, but as a production system, it has to solve it in a very good way. So this is why we, kind of learn from the experience from the previous solutions, and we design our solutions. And we can observe that the simulation part has good scalability, and the formal model part has good coverage of the preferred properties. And then our strategy, very high level strategy, is to combine them together. And our strategy is to we call it a global simulation and the local formal modeling. And later I will explain that what exactly it means. But with this strategy, we can show that Hoyan can achieve all the properties from mandatory to preferred. So this is how the system look like. So when the operators can always just submit some properties that to verify, and of course the system is continuously probing grabbing all the online reads and routing updates and do the online configurations, and then the feed to the from the behavior model of the devices, we just generate a target network model, and from this model we do the verification. But of course, there's another background. There is another background. We call it behavior model validator. Later I will explain. So this model job is that it in the background it keeps comparing what the current behavior model, the device behavior model computes under the real network model, network feeds, and then we can see the difference between the behavior we think or and the behavior of the device that the real device behave, so that we find this gap and we continuously make patches on our model and to to approach the realistic behavior of the actual devices, so that the verification can be more and more accurate. So that this is our first innovation. So we have a systematic way to tune our behavior model to approach to the real model, and to guarantee the correctness of verifier. But of course, our second innovation is that, just as I mentioned, our strategy to make the verification both scalable and also can handle the uncertainties. I will present them one by one. So let me give you an example of why the vendor-specific behaviors can create an accuracy problem. Okay, so here the example. This is a kind of very simple network, which is a line, and the 4 routers actually they have different configurations, and as you note that 3 routers R1, R3, R4 are from vendor A and R2 are from vendor B. So they actually, vendor A and vendor B, they have some different behavior, but at first we don't know that, and we just treat their behavior as the same, and then what happened in our simulation is that one of BGP update come, and R1 will just hit this rule and say that, okay, it will add the community 920 append to the update and forward to R2, and R2 will forward it to R3, and R3 will hit this and forward it to the R4, so that R4 will get the read that, okay, it can reach both of the IP prefixes with this ASA path. This is our result, but this is not right. Just because the vendor B in R2 has the different behavior that we don't know. And the behavior is that it will remove all the community. Okay, so that what actually happened is that when R1 forwarded to R2, R2 will remove the community, and then R3 will add 1 back to the community. So finally, what R4 get is only 1 prefix. This is the difference between what we simulate and what the real network behave. So that you can know that when this kind of VSB, vendor specific behavior happen, and our verifications result cannot be trusted. So that we have to handle this, and to handle this, we build up a systematic method. And to handle the challenge, the key idea is that we need to use the production network as a debugger. What exactly mean is that we continuously use our verification to compute the RIB and FIB of the current production network and compare with the current production network. And when there is a difference, we need a way to trace back to the root configuration and the configuration block and where the different originally from. And this is the most challenging part, right? So when you find the difference, how you trace back. So that to do that, we need a little bit more better design. For example, if you just compare with the real world routing table and the simulated routing table, we will find that the diff start from R4. So that you might just think that, okay, maybe the difference is from either R3 or R4, but we actually know the difference is starting from R2. So that the root reason why is the difficulty is that you don't have enough information. So that in our system, we extend to RIBs to add all the properties that can be used in the routing selection. For example, when we for example, in our monitoring system and the verification system, we add all the property, and if you compare it, the properties with the extended properties you will clearly find that the diff is between R2 and R3, so that this kind of method can significantly accelerate the speed that we located the VSB and then to fix it. So just with this process, at first you can see that without the tuning, our accuracy is just about 50%. And but after 6 months, with this continuous monitoring and tuning, and we kind of converge to the nearly 100% accurate. And until then, so we can say the verifier is usable. And of course, another innovation is our global simulation and local modeling method to handle the scalability problem. So let's just briefly introduce what is K-failure. We just use K-failure as an example. So for example, this network, it can only hold one arbitrary link down, because when this link down, the reachability breaks. But this network can handle two, right? So with this K-failure, we just verify the reachability under arbitrary K-failure, and this is a well-known hard problem. And why it's challenging is that when you enumerate these cases, it will be just explode very quickly, and our one does not have any symmetric, so that reduction cannot help. And what we do is that we just simulate the propagation of routes or packets, and but with this process, we use local formulation to formal the topology condition under which the update can reach a point. So let me give an example. If I want to just verify the reachability from A to D, we started the simulation. So if we named all the links with A1 to A4, so that one BGP got announced from A, so this will go two paths, right? And you can notice the A1 here means that when A1 is alive, this can achieve this message can arrive C. Under the same, so C will build a RIP, and the normal RIP is just the AS path and the next hop. But we also encode the topology condition under which this route exists. And this process will continue. And when it reaches here, so you can see C1 has another route for this prefix, which is 100, 200 path, and with next hop B, and the topology condition is A2 and A3. Right? This means that only under this and R2 can exist. And then C will make a routing selection, and obviously if C treat the shortest path first, so C will run the route in this way, and C will forward. So because this is the best route, C will first forward this with the same condition, and because this is the second best, the condition that it can be forwarded by C is that the first one, it does not exist. So that the condition that the C forward R2 is that it's neg A1 and A2 A3, which means that R1 does not exist and R2 got forwarded. So that if these two messages reach D, this RIP will be like this, right? It means that under this condition it will have this route, and under this condition it will have R4. Under the condition that there will be at least one route from A to D is that this condition or this condition, right? And then when we check this, when we put this into the SMP solver, it will tell you, so what's the if there is one condition that make this false by only one variable false, so that we can find if it's A4. So this is just a very simple example, but it shows you the whole process and the idea behind it. And in the real run, so it has a good scalability because we are essentially a simulation, so that when it reaches some point that is impossible to happen, we will just cut the trunk and get rid of all the conditions. Just like in the simulation, when we find that the condition have more than k net, which means it's out of our consideration, so we can withdraw that route, and we can also drop in the impossible cases, and in the simulation we can keep simplifying the logical formulation. That all be very helpful to just simplify the final formal verification. So that in the paper, we actually introduced these two ideas, but for the scalability, we also talk about, why I use BGP as the example. We also talk about how we handle ISS and a static route with the similar idea. And also we talk about how to handle another kind of risk, which is non-deterministic routing update racing. So here's some deployment results. So we deployed Hou-Yan 2 years ago. And during that, we used it as two ways. One way is that there is a continuous running background checker to just check the potential risk that exists in the online configuration and try to fix it before it can be triggered. And the other is that it is kind of become a mandatory tool that before operator to update any configurations on our WAN, it needs to use Hou-Yan to verify it. And these are all the errors that it finds over time. And these are the just auditing error, and this is the update error. And interestingly, we found a very interesting case during the real life. This is a simplified version. It's showing you what does it mean by non-deterministic update racing problem. So given if these are all BGP pairs, and if C and D are announcing the same prefix with to A and B, and they have the same prefix but different local prefixes, and but the weight are the same. But A has a policy, egress policy, that when I forward this, I will change the weight from 0 to 100. So that what happened is that if C's update arrives B before D, because of the egress policy, the weight has been changed, so that the D's announcement will be dropped. And this is what happened when C's announcement reached B first. But if D's announcement reach A first, what happened is that the local preference wins, so that the A's routing table will point you to D, so that this will be the routing table and the traffic direction will just non-deterministic because of the arriving order of the updates. So this is the bug. But the use Hou-Yan, we actually find that bug, and this is quite impressive to our operators. So here are some experiments on our entire WAN. So we find that with existing tools, especially when we consider the K failures, so no existing tool can just be scalable enough to verify our WAN. But the Hou-Yan, actually, with our optimization, it can very quickly verify our entire WAN. So this gives you the idea of how fast it is, and especially under failures, and also some for reachability and the row equivalence. So these are some experiments. Because other tools cannot simulate our whole WAN, we found a very 20 routers small subnet to compare Hou-Yan with some important existing tools. You can find the scalability gain from between Hou-Yan and Minesweeper and Bearfish. So this is the 80 routers. And under this skill, you will find that, Minesweeper start from k equals to 1, and the badfish, it cannot be finished within 1 day. Okay, here's the conclusion. So we emphasize accuracy, scalability, coverage just from our practical point of view. And I know that network verification is kind of an old topic, but this is kind of new to production, right? So, and to make it really working and accepted by the operators in daily uses, we should conquer a lot of challenges. And then these three are the most important one. And as the result, so Hoyan has been used in Alibaba for 2 years, and it helped us to reach a very high level of network stability under the configuration updates. And it also, in last year, it significantly reduced a lot of potential outages. So it's quite a useful work. So I will stop here and happy to take any question.
Okay, thanks to Hongqiang for the presentation. Any question? If there are any question, you can just raise your hand here. Okay. I think Shen Huang has a question, or I don't know. No? Okay. Dongshu, you have a question, right?
Yes. So Hongxiang, I have a question. So with Hoyan, how does the operator now change the configuration rule?
That's a good question. So currently, the operator will make a plan, and then they will write the intent of them, and they will say that with this updates, will there be any visibility change, or how will it change, and what's the device equivalence relationship on the network. They will just write some kind of high-level intended language, and then they will design the kind of updated configuration and insert it to Hoyan, and the Hoyan will just answer them whether their intent is achieved. And if not, the Hoyan will point out where exactly the root cause. And of course, so under the whole update pipeline, there will be some other kind of validation tools, but the Hoyan will be the first part, because it's kind of a pure logic, and it just judges the logic of the configuration update.
So is the intent specification part of Hoyan, or is it part of some other system?
What kind of sorry?
Intent specification. I'm wondering whether the intent specification is something that you had earlier before Hoyan, or is that part of Hoyan that you had to develop?
I think it's it's part of Hoyan, but generally we have the intended language is for multiple purposes. You can view this as a kind of specific designed language for operator, and also Hoyan use that for express intent, and the others can also use it to generate the configuration. So it's kind of independent design, but very related with Hoyan.
Okay, thank you.
Okay, Hongqiang, I have a question about the first example you used, where you said that some problem coming from different vendors, use vendor A, vendor B. In that example, so it's the behavior of the vendor B's router. It's just its normal behavior, or it's come from some misconfiguration.
It's a kind of most of the time it comes from different definition of default behavior. So that some vendor put the default behavior as you don't change the community, and some just they will remove community if you don't explicitly specify it. And this also happens in somewhere else, like what's the default behavior. So if you don't specify any static route or ACL, and what's the behavior when you just in the paper we list all the the specific behaviors that we found, and we also specify how big the impact of that. So basically, most of the time, it's kind of beforehand when you write the verifier, you don't know about that. This is not a bug; it's just the intended behavior that the vendor wants this device to behave.
Okay, thank you. If no other question, let's thank Hongqiang for the presentation.
Thank you. Thank you.
Okay. Okay. Our second speaker is okay. Our second speaker is Professor Qun Huang. He's currently an assistant professor in Peking University. He got his PhD degree from the Chinese University of Hong Kong in 2015, and his bachelor degree from Peking University in 2011. His research focuses on network measurement now. So, Qun, I think you can share your screen. Okay, Qun, are you around? Okay. If Qun is not here, so maybe we can just start the next paper. So, Chen, are you around?
Yes.
Okay, maybe I think you can start before Qun. Yeah. So are you ready?
Yeah, I guess.
Okay. So let me make a brief introduction about Chen Sun. Chen is currently a network engineer in the network research team at the Alibaba Group, together with Hongqiang. He received his PhD degree from Tsinghua University in 2019, and his research interests include SDN, NFV, programmable networks, and network monitoring. He has published over 10 papers on top conferences and journals. So let me give the time to Chen. Chen, can you share the screen? Okay. I guess he's rebooting. Okay. So I think you can just start now.
Okay. Okay, can you see my screen?
Yes.
Okay, great.
Please go ahead. Yeah.
Hi everyone, I'm Chen Sun from Alibaba Group. Today I'm going to talk about Netsphere, a flow event telemetry system based on programmable data plane. Today, networks are becoming large and complex, and network applications are increasingly sensitive to network performance. On the one hand, traditional cloud applications like block storage services demand increasingly high throughput. On the other hand, interactive applications have become a major driving force of network business growth, while they have strong SR requirements, unstable and low network latency. If the network can deliver satisfactory performance, we can get great quality of user experience. But bugs and failures in configuration, software, and hardware are inevitable for networks. Thus, applications often suffer from unceasing network performance anomalies, or NPAs. NPAs can violate SLA. Even occasional latency spikes can bring unacceptable damage to user experience. In reality, applications may encounter 3 types of performance anomalies, including long-tail latency, bandwidth loss, and packet timeout. Statistics from production networks show that about 46% of NPAs are caused by networks, which must be timely mitigated to minimize the impact on application performance. The life cycle of NPA mitigation includes 3 steps. The first step is NPA location, which requires operators to answer questions, including who to blame, what kind of NPA is it, and where the NPA happened. And the second step is to recover NPAs according to their locations. In production networks, the life cycle of NPA mitigation can be quite long and can last for hours or days for some cases. Specifically, we observed that NPA location requires 90% of the entire mitigation time. Therefore, making NPA location fast and accurate is crucial for fast NPA mitigation. To achieve fast NPA location, operators must be able to correlate flows and events. First, the monitoring granularity should be flow level, which can be directly mapped to customer applications. Second, operators should be able to precisely capture all performance critical events, including congestion, path change, packet pulse, and packet drops. And if we put them all together, we could have eyes on every single abnormal events that happen to every single flow, which could equip efficient NPA location. Unfortunately, existing network monitors cannot satisfy the requirements for locating NPAs. First, traditional switches have black box data planes with weak visibility. Thus, they can only export coarse-grained monitoring information. For example, some monitoring tools like syslog could provide event-only information, such as a port is down. And some monitors like NightFlow could provide flow-only information, like one packet passed one port at some specific time. Without explicit correlation between them, we have to combine coarse information from multiple sources and guess the root cause, which could take a long time, even for experienced operators. While the overhead of the black box solutions are small, the coarse data granularity cannot satisfy NPA location requirements. As switches become more configurable, packet telemetry is proposed for obtaining fine-grained data plane information. By mirroring original packets or related metadata, packet telemetry can precisely capture flow events. It can extract flow information from packet headers and get event information carried by packet metadata. Although packet telemetry enables fine-grained flow event monitoring, it introduces unacceptable monitoring overhead since it has to transmit loads of monitoring data to the management plane. So existing solutions either compromise scalability or sacrifice the data granularity. So is there an ideal solution that can achieve both granularity and cost efficiency? Recent advances on the programmable data plane have provided us a solid foundation for rethinking flow event monitoring. Our key vision is that we can perform flow event monitoring directly in the data plane and export the concise flow event information to the management plane, which only needs to perform simple flow event parsing and storage. We call this new architecture flow event telemetry, which can achieve both fine data granularity and cost efficiency. Thus, we propose Netseer, a flow event telemetry-based network monitor. Netseer watches all individual flows and comprehensively detects flow events. The key idea of Netseer is to detect flow events and compress event data entirely inside the data planes, so it can significantly reduce the monitoring overhead as well as preserving the fine data granularity. We can change the long-standing situation that NPA mitigation is slow. With NetSeer, NPA location can be done within seconds, which enables second-level NPA mitigation. However, realizing NetSeer is challenging in 3 aspects. First, it is hard to achieve full event coverage, especially for inter-switch packet jobs that happen outside the switch programmable pipeline. To work on this challenge, we have an event packet selection step. And second, it is hard to achieve high monitoring scalability of event transmission and process. To address the scalability challenge, we propose event deduplication and event extraction and batching. Finally, it is hard to ensure high data accuracy within limited ASIC memory. We propose false positive elimination using switch CPU. As shown in the figure, the overall workflow of NetSeer contains 4 steps, and the final bandwidth overhead is as low as 0.01%. Next, I will introduce the challenges and solutions in detail. For coverage, NetSeer should be able to discover all flow events from high-speed network traffic. There are 4 types of network events, including congestion, pulse, path change, and packet jobs. Especially, there are 4 types of packet jobs. Among them, the pipeline job, MMU congestion job, and hardware failure job could belong to intra-switch job. Intra-switch job and other events are pipeline aware. NetSeer could trace the entire packet processing pipeline and its logic to comprehensively detect them. But inter-switch job happens outside the programmable pipeline. Although only occupying 18% of job cases, but they consume 41% of total job location time, which is a big problem to solve. Inter-switch job happens between the ports of NICs and switches. Due to reasons like bad transceivers, bad fiber, packet bits could flip abnormally when the packet is transmitted from upstream port to the downstream port. The packet will encounter FCS error and be dropped at the port MAC layer without pipeline awareness. This makes it hard to detect inter-switch jobs and recover the flow information of dropped packets because the packet headers may already be wrong. NetSeer proposes to leverage inter-switch coordination to detect inter-switch packet jobs. First, for detecting packet jobs, NetSeer marks each packet with a sequence number, and then the downstream switch will check the sequence number of each packet and detect packet jobs when discovering inconsecutive sequence numbers. Second, for recovering flow event information, the downstream switch will notify the lost sequence number or sequence numbers to the upstream switch. And before sending a packet, the upstream switch should already record the flow information and the sequence number of the packet with a ring buffer. After getting this loss notification, the upstream switch can recover the flow event information from the ring buffer. As mentioned before, NetSeer can reduce the monitoring traffic volume by event packet selection. However, extreme situations such as severe congestion can result in massive congested or dropped packets. The situation can go worse if you consider a large network. Imagine a data center with 50,000 servers. Suppose all servers encounter incast and congestion and drop happens everywhere in the network. Then we need 50,000 more servers to process the monitoring data, which brings unacceptable overhead. Our key idea to overcome the scalability challenge is to eliminate redundancy in monitoring data without compromising the information integrity. First, NetSeer removes redundant event packets by event deduplication. which could compress event packets into flow events. Next, NetSeer removes redundant header and payload by event extraction and batching. In this step, NetSeer will generate batches of concise flow events. For event deduplication, the state-of-the-art deduplication method is hashing-based approach, such as Bloom filter. However, due to hash collisions, the Bloom filter has unavoidable possibility of false negatives, leading to unreported flow events, which cannot satisfy NPA location requirements. To realize false negative-free event duplication, we design a group caching mechanism. Group caching maintains a hash table. Each entry in the table records an exact 5-tuple in order to avoid false negative. We hash each event packet to a specific entry. If hash collision happens, the entry is replaced with the 5-tuple of the new packet. Then, both the evaded flows and the new flow will be reported. In this way, we could enable effective deduplication with 0 false negative. To further remove redundancy, NetSeer extracts only event information and flow information from raw packets and metadata, and can compress each flow event into 24 bytes. Next, flow events are sent to the management plane via Ethernet packets. Since an Ethernet packet length is no less than 64 bytes, sending one event with one packet will lead to large overhead. To address this problem, NetSeer proposes to batch event packets, which packs multiple events within each packet to reduce bandwidth and processing overhead. The event batching mechanism has an event stack. Each incoming event is pushed into the stack for temporal caching. Meanwhile, NetSeer generates circulating event batching packets that constantly recirculate within the pipeline through an internal port. When hitting the stack, it pops one event and appends the event into its payload. Once the event number exceeds a threshold, the packet is forwarded to the management plane and cloned at the same time with an empty payload to collect future events. As mentioned before, for event deduplication, we use group caching tables to avoid false negatives, but it inevitably introduces potential false positives. False positives not only increase data volume to be transmitted, but also mislead operators as if multiple independent events have happened to the same flow. However, due to the limited programmability and memory, it is hard to fully eliminate false positives on programmable data planes. To overcome the accuracy challenge, we propose to leverage ASIC CPU coordination to achieve 0 false positive. First, in switch ASIC, NetSeer conducts best effort deduplication, which can effectively compress flow event data with high speed. Then, the flow events with false positives will be further processed by switch CPU, which can leverage massive memory to fully eliminate false positives. We have implemented the above design on Tofino and Smartnix. NetSeer has about 12,000 lines of code. And NetSeer data plane is implemented as an extension of switch.p4. This figure shows the overall implementation structure of NetSeer switch. Currently, NetSeer is under deployment in Alibaba Cloud Networks. NetSeer brings moderate data plane resource usage. On SmartNIC, there is 5% additional memory usage. On Tofino ASIC, NetSeer brings less than 20% resource usage, except for the SID4 ALU, which is mostly used for interswitch job detection and batching. We evaluate NetSeer on a testbed with a factory topology. And we do the evaluation in 3 major aspects. First, NetSeer can effectively accelerate NPA location with 61% to 99% location time reduction. Second, NetZero achieves 100% flow event coverage without false positives. And third, NetZero is highly scalable with 0.01% bandwidth overhead. To understand NetZero's effectiveness on troubleshooting MPA, we study 5 real and representative MPA cases, including congestion, configuration error, silent drops, etc. From our experience of analyzing and debugging evolved cases, we observed that existing monitoring systems fail to gather necessary information for MPA location, leading to long location time. In comparison, NetZero could help operators quickly find related events in seconds. And finally comes to the conclusion. We propose flow event telemetry, FET, for fast MPA location. And we design NetZero, a FET-based network monitor that captures flow events with high efficiency. It leverages inter-switch coordination for high coverage and ASIC CPU coordination for high scalability and data accuracy. NetZero is currently under deployment in Alibaba Cloud. And this is the end of my talk. I'm happy to take questions.
Okay, thanks for the presentation. Any question? Okay, Chun, please.
Okay, thanks for the nice talk. And I have a question about the balloon filter. And as we know, balloon filter already guarantees 0 false negative, but it may cause some false positives. But here you mean that you want to, so your approach is also want to guarantee 0 false negative. So what's the problem of balloon filter in your case?
Okay, thank you for the question. Actually, I think we have a different definition of false negative in different contexts. For our event detection, we want to report every single unique event without missing any of them. Due to hash collision, if 2 events are hashed to the same bit, the balloon filter will consider the second event has already appeared, but actually it has not. And in this case, we consider it's a kind of false negative. It's like that this event is happening, but we do not report it. So this is what we call false negative. And I think there's kind of different definition for that. Yeah.
Oh, okay, I see. Thank you.
Okay, and the other question? Okay, I have one question. So for the overhead, you mentioned that the bandwidth overhead is just very little. But how about the additional overhead for the CPU, including this switches CPU for monitoring, as well as the controllers, the CPU requirement of the server controllers for the analysis?
Okay, thank you. That's a very good question. Yes, actually, we use the switch CPU of each switch to perform partial processing and leave little burden to the final management plane CPU. For each switch CPU, we realized that the switch CPU may not be as powerful as servers, so we kind of introduce only very minor tasks like pacing or like a simple hashing for false positive elimination for the switch CPU. And actually the switch CPU consumption is relatively small, like below 20%. And with more powerful switch CPU, we can do better things. Like we can perform more steps in the switch CPU, but with a weaker CPU or fewer CPU allocation for our NetZero task, we can also perform partial false positive elimination, but it may not be as effective as a situation where we have enough CPU. And for the management plane, as I have shown here, it's kind of like 0.01% bandwidth overhead. Therefore, if you consider a a data center with 50,000 servers, we may use only like 5 to 8 servers to process all the event packets. Yeah, that's the overhead.
Okay, okay, thank you. Another question? Okay, if not, let's thank Chen for the nice presentation.
Thank you.
Yeah. So next speaker is Professor Chun Huang. Chun just got offline because of the network problem. Okay, Chun is currently working in Peking University. Okay, I just made a brief introduction for you, so I think you can just go ahead, Chun. Yeah.
Okay, thanks for the introduction. And sorry that I'm just be back due to some power failure in my home. Okay, today it's my pleasure here to present our paper. And this is a joint work from Peking University, Chinese Academy of Sciences, the Chinese University of Hong Kong, and Microsoft Research. Okay, and in this paper, we address flow level monitoring. We consider a typical network. There are some end hosts in the network and they are connected by switches. All end hosts and switches can execute some monitoring tasks. And there is also a centralized controller in the network to manage all the end hosts and switches. For each packet in the network, we abstract it as a key value pair. The key identifies the flow this packet belongs to, and the values indicate the information carried by this packet. And the goal of the flow level monitoring is to group packets into flows based on the flow keys and compute various statistics such as packet count, byte count, and so on. Network administrators usually hope the monitoring to be highly accurate, and at the same time, they also want to keep the resource usage limited. In previous study, we often need to make a trade-off between these two objectives, but in this paper, our goal is to achieve both full accuracy and resource efficiency. For full accuracy, we expect the monitoring can cover all time intervals, all devices, and record all flows. And for each recorded flow, we also expect that its statistics are computed with zero error. Such full accuracy can benefit many network management applications because full accuracy can avoid noisy interference due to the measurement error. So eventually, the efficiency of network management will be improved. For resource efficiency, we observe that each type of entities in the network have its unique resource limitations. So we want to avoid resource overload in all of them. For end hosts, they have sufficient memory, and their CPUs provide great flexibility to realize arbitrary processing logics. However, we need to control the complexity because the CPU is a bit slow when processing the high-speed network traffic. In addition, end hosts have limited visibility. They have no information about the network internals. Switches, they can process traffic at line rate with the switch ASICs. However, the memory in switches is limited, and there are many restrictions on their programming models. And for the controller, it can integrate computational resources of multiple physical servers to form a cluster. It also has the global view of the network. However, the link capacity between the controller and each data plane device is limited. So we cannot transmit too much traffic to the controller. Given the various and tight resource restrictions, existing approaches often make a trade-off between the resource efficiency and full accuracy. One extreme is the classical SNMP techniques. They consume very few resources, but they are too cost-gram to provide accurate results. Another extreme is the hash table. Hash tables achieve full accuracy by exactly tracking each flow. However, per flow tracking exceeds the memory capacity of switches, so hash tables can only be deployed in end hosts. Between the two extremes, there are many approximate approaches that trade off accuracy to reduce resource overheads at different errors. For example, sampling, event matching, and top K counting reduce overheads by only monitoring a subset of flows. However, their results are not complete because a large number of flows may be missing. Another class is sketch. Sketch techniques allow multiple flows to share counters to reduce memory overheads in switches. However, the accuracy of sketch techniques remains approximate due to the flow conflicts. So different from these approaches, our goal is to achieve both resource efficiency and full accuracy at the same time. Before presenting our design, we first analyze the root cause of the resource and accuracy trade-offs. We find that existing solutions usually deployed operators in end hosts and switches. This is a very common approach to reduce the overheads of the controller. However, the operators in each device is executed individually and lacks of collaboration. For example, an end host cannot control the processing behavior in any switches. In this case, the operator in each device has to contain complete functionalities, including flow key extraction, value checking, and resource allocation. This makes the operators very heavy, so they have to sacrifice accuracy to fit the resource limitation of the devices. So based on these two observations, we are motivated to optimize the two design choices in existing solutions, heavy individual operators and limited collaboration. So in this paper, we present only an architecture to achieve our goal. Our key idea is to redesign the underlying architecture of flow level monitoring. Instead of deploying the complete functionality in each device and executing them individually, we collectively employed all entities in the network to build a distributed telemetry system. In particular, we want to answer these two questions about the architecture. These two questions are raised from the perspective of distributed systems. The first question is how to distribute network telemetry across different entities and coordinate these entities. And second, as in common distributed systems, we need to deal with some unreliable issues such as inconsistency and message loss. This is necessary to guarantee our distributed telemetry architecture works correctly. We first consider the first question. Our answer to this question is to follow the split and merge principle to propose a novel architecture for flow level monitoring. We divide the network-wide monitoring into 4 partial operations. Each partial operation is responsible for a piece of monitoring logics. This breaks the heavy individual operators in traditional solutions. Then we coordinate the resources of all network entities to realize these partial operations in a distributed manner. The coordination ensures that the 4 partial operations will eventually form zero-error results, and at the same time, the resource consumption is limited in each device. Now I will introduce how these 4 partial operations are realized one by one. For the first operation, flow key tracking, we observe that we only need to record the flow key once in each flow key once in the network. Thus, we record the key of each flow in its source and host. Then the second operation is the flow value updating. We check flow values in both end hosts and switches. In each device, we allocate some slots of counters to store flow values. There are 2 types of slots designed for egress traffic and ingress traffic, respectively. And when a packet arrives in a device, we select one or more slots and then update their values based on the packet. The third partial operation, flow mapping, determines how a flow associates with its slots. Since the resource constraints in end hosts and switches are different, we employ different strategies here. For end host, each flow has its dedicated slot because the memory is sufficient in end host. Since the flow keys are also checked in the source, we organize the flow keys and egress slots as a hash table. But in the destination and the host, the flow keys are not checked for ingress slots. So to solve this problem, for each flow, we embed its location in the hash table as the host index in the packet header, and the destination host can extract this index to locate its slot. In switches, since the memory is limited, we allowed multiple flows to share the same slot. This is very similar to Sketch. However, Sketch algorithms compute slots by hashing the flow key at switches. Our approach is different. We compute the switch slot by coordinating the controller and the host, but not as switches. Since the controller has the global view of the network, this can significantly reduce the conflicts at switches. And when the switch indexes are computed, they are recorded in the hash table in the source and the hosts, and also embedded in the packet header. Each switch extracts the index and updates the corresponding slots with the packet information. The final partial operation, collective analysis, is performed in the controller. It collects the results from all end hosts and switches to form the final flow statistics. Since the slots at the switches can be shared by multiple flows, to achieve full accuracy, collective analysis also needs to restore flow values from the shared slots. Recall that in each end host, we have recorded flow keys and flow values with dedicated slots. So our basic idea is to decompose the shared slots in switches with the aid of end host information. Here we present an example. Consider a switch slot with value 24. This value must be contributed by multiple flows. Fortunately, we have recorded flow keys and flow values with 0 error at each end host. And we also record the switch index for each flow. So we can find which flows are actually mapped to these slots. In our example, there is a flow 1 with value 13 and a flow 2 with its value 11. So we can decompose the value in the switch slot into the two flows according to the source and the host information. So far, we have introduced the 4 partial operations. In summary, the resource usage is acceptable in each type of network device. In end hosts, the memory is sufficient to host per flow hash table, and the hash operation is acceptable for general CPUs. In switches, we only extract switch index and update the counter. Both operations are supported by commodity switch ASICs. And since we let flows to shared slots, the memory consumption is also limited. In the controller, we mainly leverage its global view to allocate slots and perform collective analysis, so the resource consumption is also acceptable. Now let's move on to the second question about the reliability guarantees. In this paper, our architecture faces 2 challenges from the unreliable network events. First, network monitoring is usually executed based on time intervals, but we do not have a global clock to synchronize time intervals across devices. And second, packet loss is very common. So in some devices, the flow values may not be recorded correctly. In previous studies, these 2 issues do not become a big problem because previous studies have limited network-wide collaboration. However, in Onimon, we need to deal with them. Otherwise, the architecture may fail to work. Here we present an example to illustrate the impact of the 2 reliability issues. Here we have 2 flows with their values 13 and 11 respectively. These 2 flows shared a slot in switches. Ideally, the value in the 2 flows should be recorded in the switch. So the expected value in the switch is 24. However, if some packets exhibit long network delay, part of flow values may be included in different time intervals after the long delay. And another case is the packet loss. With packet loss, some values are even not recorded in the switch. In both cases, the value in the switch may be low. In our example, the value in the switch is now 20. Since there are multiple flows with long values, we cannot decompose the value in the switch because we do not know the actual contribution of each flow. We propose two mechanisms to address the two challenges. For the lack of global clock, we propose a hybrid consistency model to synchronize time intervals. By hybrid consistency, we mean that it's a strong consistency in most of the time, but it will be degraded to weak consistency at some times. And similar to our architecture design, the hybrid model also coordinates all entities in the network. It provides two guarantees. The first guarantee is that each packet is included in the same interval by all devices in its path. And second, it also guarantees that all entities reside in the same time interval in most of the time. And for packet loss, we propose a linear system to infer the loss. We also propose a flow mapping algorithm to make the linear system correctly works in general cases. And here I skip all the details and you may find more results in our paper. We build a prototype of Omnimon with DPDK and P4. We conduct cheese-driven evaluations in both testbed and simulation environments. We first measure the host overheads. We compare Omnimon with packetgen that is also implemented by DPDK. Since packetgen has no monitoring functionality, we use it as the baseline. In the left figure, even when we add the end host monitoring functionality, the throughput drop is less than 10% compared to the original packetgen. And in the right figure, we profile the overheads. We find that the most overheads comes from hash lookups, but the overall CPU resource spent in each packet is less than 40 cycles. The next experiment is switch overheads. We deploy Omnimon and compare it with 4 recently proposed sketch techniques. Here, each sketch technique only monitors packet count, and we also have 2 versions of Omnimon. One simple version also only monitors packet count, but another full version monitors 9 types of statistics in one configuration. We observe that Omnimon consumes less resources than sketch techniques because Omnimon does not perform hash functions or record flow keys. And Omnimon can achieve full accuracy, but sketch can only provide approximate results. And we have more experiments such as the overheads in the controller, the efficiency of our reliability guarantees, and 3 use cases on anomaly detection, failure diagnosis, and load balance evaluation. And in summary, we propose the Omnimon architecture with 2 reliability guarantees. And we also build a prototype and conduct experiments to compare it with 11 state-of-the-art solutions in various aspects. And our source code is also available now, and you may download if you are interested. Okay, that's all of my talk. Thanks for your attention.
Okay, thank you for the nice presentation. Any question? So Chun, I have a question. So, about how to make consistency between different switches. Yeah, just this slide. So, you mean that okay? The details of your solution, just we can read your paper. I just have a rough question. So you say that you just divide the into different time slots. So what's the granularity of this time slot?
Okay, that's a very good question. The key idea is that here we in our consistency model, we assign different loads to the different entities. For end hosts, they actually determine the time intervals, And because end hosts have very powerful CPU, so they can run very complicated consistency protocols. And after the time interval is determined by the end hosts, an end host embed this time interval information in each packet. So each switch in the past only extracts such time interval information from the packet and update the corresponding time slot in its memory. So the switches are just a follower in our protocol, and the end hosts are the actual proposer of the time interval. And there is we also use the controller to help the synchronization. Because there may be some straggler in end hosts, and the controller will identify this straggler and push the clock in the straggler to catch up with other end hosts. So this is our key idea.
Okay, thank you. Okay, Chen has a question. Yeah.
Okay. Thank you for your inspiring talk. Actually, I'm just a little curious about one thing. Are there any design behind deciding which flows should share a switch slot? Do we just do the equal split, or any considerations for that?
So sorry, I cannot hear clearly. So can you repeat your question?
Yeah, sure. In short, which flows should share a switch slot? Are there any design behind that?
Yes, we have such a design. This is determined by the controller. And since we need to decompose the slots in the switches into individual flows, so the controller can know how to make these flows. How to make these flows share the slots with the minimal flow conflicts, so that we can decompose them very efficiently. So we have such a mechanism, and it's based on it's determined by the controller. And after the controller computes the slots for each flow, and the controller sends this message to end host. So the end host can embed this information in each packet, and the switch will extract this information and update the corresponding slots.
Okay, thank you very much.
Okay, any other question? Okay, if not, let's thank Chun for the nice talk.
Okay, thank you.
Okay, the following three talks in our session are all from very young people. They are either undergraduate students or first-year PhD students. So yeah, we are very happy to see rising stars in our community. So the next speaker is Yue Wu. He is a senior undergraduate student in Peking University, and will pursue his PhD degree at Yale University. His research interest spans on computer systems, in particularly wireless network systems and embedded system. His advisor is Professor Chenren Xu at the Peking University. So Yue, I think you can start. Share your screen.
Okay, thanks for the introduction. Hello, everyone. I'm Yue Wu, an undergraduate student at Peking University. Today, I'm going to introduce our recent work, Turbo Boosting Visible Like Backscatter Communication. This is a joint work with my colleagues, Pu Rui, Kono, Li Lei, and my advisor, Chen Ren. As the Internet of Things is turning into reality at a quick pace, billions or even trillions of ambient objects are expected to gain Internet access in the near future. Deploying such a massive amount of devices becomes difficult if we need to either wire them to power source or replace battery periodically. Today's wireless technology for IoT consumes tens or hundreds of milliwatts, for example, Bluetooth and LoRa, which hinders the development of devices with long battery life. Recently, backscatter communication has become an active research field, as it effectively offers merely orders of microwatts connectivity to small sensors, and hereby becomes a compelling communication solution candidate in the IoT era. Essentially, instead of active signal transmission, backscatter communication reduces energy consumption by signal reflection. Recent work shows it is possible to heat-check the information over the ambient signals such as Wi-Fi, FM, and LoRa. However, radio backscatter will bring two potential issues when deployed for indoor IoT scenarios. First, it interferes with normal daily traffic and exacerbates the spectrum crunch problem. And the second, its leakage through wall yields serious security and privacy concerns in room area networking use cases. Along the line, but exploring a different medium, visible light backscatter communication presents an emerging and potentially better solution. It can leverage the existing infrastructures for communication purpose, specifically the dome light. The optical medium intrinsically addresses the RF interference, security, and privacy concern aforementioned. Like most backscatter systems, VLBC systems consist of mainly two parts called reader and tag. To establish a bidirectional communication link, reader first sends downlink data to tag with modulated light. We define this reader to tag link as downlink. The tag demodulates downlink data and prepares for the response. At the meanwhile, reader sends carrier signal and listens for response. The tag began replying by selectively reflects light with liquid crystal modulator, which is called a uplink. The final step is that reader receives the reflected light signal and demodulates uplink data. The downlink can easily achieve hundreds of kilobits per second because the photodiode receiver and LED transmitter can reach 1 GHz and 10 MHz respectively. In this case, the downlink throughput is limited by power consumption design. The uplink, on the other hand, only reaches sub-kilobits per second data rate because of the slow LCM transmitter. You can think of a high-end game monitor that has 240 Hz refreshing rate, and that's approximately the speed limit of liquid crystal modulator. We come to a conclusion that the slow response of LCM as uplink transmitter is the bottleneck of VLBC. So here is a pair of LCD modules. Being charged or not, it can selectively let through the light or block it. If we apply square wave driven signal to the LCD, it reaches stable states with low frequency. But with higher and higher frequency, the response shrinks to only 4% of the total amplitude with 1 kHz. Thus, traditional OK deteriorates quickly above 250 bits per second, which is the 125 Hz streaming source here. Have a closer look at the received signal. We can find that LCM has an asymmetric response. That is, the charging edge transition lasts only about 0.3 milliseconds, while the discharging edge lasts even longer than 4 milliseconds. The huge gap between them is never considered before for communication purpose, and thus the data rate is limited by the slow discharging edge, despite the 10 times faster charging edge. If we want to improve the data rate, we could try two directions. The first one is designing advanced time amplitude modulation and coding scheme. Actually, there has been some works on this. For example, Miller coding finds a way in improving the data rate to 1 kilobits per second in time domain. For amplitude modulation, there is pixelated AM that use amplitude to carry information. The other direction is to explore more independent channels for parallel transmission. For example, using multiple light colors. Our solution includes two core technologies called DSM and PQAM. Delayed superimposed modulation improves data rate in a single channel by arranging multiple LCM pixels. Polarization-based quadrature amplitude modulation explores additional channels by exploiting the optical properties of LCM. The figure below demonstrates the signal in DSM view and PQAM view, which can work in a complementary way. In order to understand how DSM and PQAM works, we need to dig into the physical principle of liquid crystal modulator. We would start from a liquid crystal shutter that is a glass box with liquid crystal inside. The intermolecular force and electric force are competing each other. As a result, it rotates polarized light by 90 degrees in normal state, while keeps the polarization angle in charged state. Then we add 2 pieces of polarizer in the front and behind, so that it becomes a liquid crystal display. It blocks the light when it's being charged and lights through the incoming light when not being charged. And this is how LCD monitor works. One more step forward, we come to the first design of VLBC, which includes a retroreflective fabric that can steer the light back to source. The same as LCD, it absorbs all incident light when being charged. The final step comes our liquid crystal modulator that removes the front polarizer. In charged state, it retroreflects vertically polarized light, and in normal state, it retroreflects horizontally polarized light. In other words, LCM can manipulate the polarization of retroreflected light. The takeaway message here is that LCM can selectively reflect the 0 degree or 90 degree polarized light. And because of the internal competing forces, the charging edge is 10 times faster than discharging edge. Let's consider the first attribute. How can we explore more channels with it? The Mellow's law tells us how a polarized light is attenuated when passing a second polarizer. If we use a liquid crystal modulator with 0 degree polarizer, called a ILCM, the received signals are shown here. Despite the charging and discharging transition, there are 2 stable states. The same for a LCM with 45 degree polarizer, called a QLCM. Given the fact that light intensity is linearly superimposed, if we use both ILCM and QLCM to send 2 bits information, we can get 4 stable states in the received waveform. Those stable states form a constellation plane of in-phase and quadrature channel. Furthermore, if we use binary divided pixel error ratio for ILCM and QLCM, it forms a higher order constellation. In real-world deployment, an angular misalignment between reader and tag is very common. We find that a physical rotation of theta reflects a 2 times theta in the constellation plane. However, the distance between symbols does not change. This attribute shows that, with polarization-based QAM, an angular misalignment does not deteriorate performance. This is our final design of PQAM. It explores 2 independent channels for parallel transmission, while at the same time it tolerates angular misalignment without performance loss. We define the number of points in the constellation as PQAM order P, and PQAM improves data rate by log P. Let's go back to the attributes of liquid crystal modulator. We then look at the second attribute. Charging edge is 10 times faster than discharging edge. LCM is a nonlinear module because the same bit inversion does not result in the same signal difference. We need to keep LCM response deterministic and controlled in order to demodulate data successfully. The basic idea is that we give enough time for LCM to go back to its normal state so that it behaves the same every time. We arrange the slow discharging edge in a fixed time slot and fire the faster charging edge at multiple time slots. We can see the different responses of those 4 code words. This design is quite easy for demodulation. Just take samples at those right points. The basic design shares the same time slot for discharging edge to improve the data rate. We define the number of LCM pixels as DSM order L, and it improves data rate up to 1 divided by T. However, this convergency is very slow, and we cannot use a very large DSM order L because the total signal strength is usually a design constraint. With larger L, each bit will result in a 1 divided by L of the total amplitude, which would be too small to recognize. We try to make DSM even faster by overlapping the discharging edge and charging edge. The blue discharging edge follows each red charging edge without waiting for others. The received signal behaves like this. A naive demodulation algorithm detects if there is an ascending edge at those red points. However, this naive solution does not work when combining with PQuam, which will be discussed later. This is our final design of DSM. It interleaves multiple LCMs and improves data rate by 1 divided by t, totally eliminating the effect of slow edge. In order to predict the received signal, we suppose that the pulse response of each LCM is identical and limited in a time range from 0 to W, which is exactly a DSM symbol duration. Given the noise signal and transmit bit sequence, we have the expected receiving signal below, which would later be used for demodulation. It's quite straightforward to combine DSM and PQuam. We send PQuam symbol at each DSM slot. To give you a brief illustration, here is our tech hardware design that sends 8-order DSM and 16-order PQuam signal. You can see that each pixel returns to its normal state before trying to send the next symbol. Next, we go to the receiver design. It has 3 parts. Preamble design helps to detect the packets and do frame alignment as usual, while it does one more thing, to correct the PQuam rotation. Demodulation design includes an optimized decision feedback equalizer for near optimal performance. Channel training in the end handles sub-channel heterogeneity from different LCMs to assist the demodulation. Our demodulation design takes the idea from both optimal solution and the computational effective one. MLSE has optimal performance, but even optimized Viterbi algorithm has a complexity of n times p to the power of L. A typical setup of p equals 16 and L equals 8. The constant is about 4 billion, which is too large for real-time demodulation. DFE has a small computational complexity, but suffers from error propagation. Our solution is a k-branched DFE, which stores at most k branches. Given a sufficiently large k, it is equivalent to the optimal MLSE. An appropriate k value could reach both near optimal performance and low computational cost for real-time operation. Here is an example of 16-branched DFE. Given the received signal, we find those candidates that best emulates the received signal. By keeping the candidate to at most 16, the computational cost is bounded. Keep doing this for the rest of the packet, the demodulation result is the best one among all candidates. Demodulation process needs accurate model of LCM to reconstruct the expected received signal, but we found several defects of the simplified pulse response model. This defect leads to the failure of our early experiment, and thus we designed a channel training process that takes them into account. The channel training design is composed of 2 parts, an offline channel training that takes hours to collect, which results in a set of reference spaces, and an online channel training solving the coefficients of those reference spaces and reconstructing responses for individual LCMs. We developed customized reader and tag hardware to verify our design. The tag is composed of 4 LCMs with retroreflective fabrics behind. It supports up to 8-order DSM and 256-order PQuam. It is also optimized for power consumption. Reader includes 2 front ends receiving in-phase and quadrature polarization light signal, and a backend using voltage-controlled amplifier for a wide working range. It can connect to PC with USB port streaming live data. Our real-world experiments use a default setup of 4 watts reader LED power and a ±10-degree field of view. We send 30 packets, each 128 bytes. The default data rate is 8 kilobits per second with 8-order DSM and 16-order PQuam. Our experiments includes bit error rate results to test the physical parameters, and a micro benchmark to evaluate software parameter selection. We also have emulation results for massive deployment and extended usage. The working range is 7.5 meter for 8 kilobits per second and a 10.5 meter for 4 kilobits per second, which satisfies most indoor IoT scenarios. Thanks to the carrier signal design, our system behaves consistently regardless of the ambient light condition. There are two kinds of angular misalignment as illustrated here. PCOM tolerates raw angular misalignment theoretically, which is verified in our experiment. For the yellow angular misalignment, our system tolerates at least a plus minus 40-degree misalignment. DFE performs worse than the optimal Viterbi ones, while our 16-branched DFE performs near optimal with low computational cost. In channel training, if we consider no previous bits, the system would fail. With 2 bits considered, it is nearly close to 3-bit ones, and thus we use 2 bits version for near optimal performance. In the emulation of higher order modulation, we reach 32 kilobits per second under a 55 decibel SNR restriction, which corresponds to a 3.5 meter distance. Coding helps to improve output in a wide range of 22 decibel. In conclusion, we revisit material and optical properties of liquid crystal modulator. Based on that, we propose 2 novel modulation schemes and that exploits LCM's asymmetric response and polarization manipulation capability. We push the data rate of visible light backscatter communication by 8 times in real-world experiments and 32 times in emulation. Thanks for your attention. Any questions?
Okay, thank you for the great talk. Any question? Okay, yeah. Actually, I don't have any technical question, but I just want to just can you share some specific experience as doing a CCOM level research work as an undergraduate student? Can you share some specific experience?
Well, I want to talk about some of my experience before. So I have 2 summer intern experience in Rice University with Professor Lin, and there I have a further vision of the front end researchers, where I took some of the ideas from that into this project, and of course I focused on the system level design. For example, the DSM design is proposed by myself, and also I love to collaborate with my colleagues. And Puree actually proposed the total idea of PQuant, so that our those 2 core technologies can work complementary in a complementary way, and I think we cannot lose any of these ideas in this CCOM work.
Okay, that's great.
Thanks.
Okay. I think Lisa has some question, right?
Yes. I have a simple question. Compared with traditional visible light communication, what's the unique difference? I mean, why you design a lower modulation scheme? Can you introduce more details?
Yes, let me find the profile here. So the traditional VLBC systems is based on the on-off keying, the modulation scheme. And later there is a passive VLC, the work published in Mobicom 2017, that use meter coding to improve the data rate to 1 kilobits per second. And there is also some pixelated AM that improves data rate. And also we found some works in the in exploring more independent channels for parallel transmission. So this idea inspires our initial design, but our design is different from those that we improve data rate even further.
Oh, I see. Thank you.
Thanks.
Okay, another question? If not, let's thank you for the talk.
All right, thanks.
Yeah. Okay. Our next speaker is Zili Meng. Zili is currently a first-year PhD student in Tsinghua University, and supervised by Professor Mingwei Xu. His research interests include the intersection of machine learning and the networking systems. He has published a paper in CCOM, is in multimedia, GSEC, and also received the gold medal of CCOM 2018 student research competition and the best paper award from ICC 2020. So let me just give time to Zili.
Okay, so thanks for the introduction. Can you see my slide?
Yes, please go ahead.
Okay, thank you. Hello, everyone. I'm Zili from Tsinghua University, and I'll be presenting our work interpreting deep learning-based networking systems. And this is a joint work with Minhu, Jiasong Mingwei from Tsinghua, Hongzi from MIT, and Hongxin from Clemson. As you may know, many recent networking systems start to employ deep learning algorithms, and some are even being deployed in the industrial applications. And the reason is quite straightforward. Deep neural networks can offer higher performance than heuristic algorithms by around 30% in those systems. However, operators might confront a series of problems when deploying the deep learning-based network systems. The first is how to design the neural network structure themselves with limited knowledge in deep learning. A naive solution might be a fully connected neural network, which is actually adopted by several projects on the last page. And there might be many candidate neural network structures. Note that despite they are equivalent when you consider the neural network as a black box, different structures can lead to different training efficiency and affect the final performance. Network operators might not have enough knowledge to decide which structure is better. And the second question is how to debug and fix the problems in DNNs. Let's look at this example. The x-axis is the scheduling decisions of flows on the switch, and the y-axis is the distribution of different actions made by the DNNs. Now, one flow is hardly chosen. If the algorithm is a conventional one, say the shortest job first scheduling, operators might realize that, oh, it is starvation, by discovering that it's always the longest job that is not selected. Therefore, they can introduce the aging mechanism and fix the problem. But among massive numbers of neurons, how can operators know which part of neural networks goes wrong? The third question is how to deploy those systems onto network devices. And the first barrier among them is the resource consumption of neural networks at the inference stage. Many networking systems are deployed on resource-limited devices, such as switches and mailboxes, mobile phones, and smart TVs. For example, on the data plan of a switch, doing flow number calculation has already been very difficult, let alone deploying a neural network. The computation ability, memory, and storage of network devices do not match the need of deep learning. The second barrier is the long decision latency of neural networks. Let's consider a case of deep learning-based data center switch scheduling. If operators want to optimize the scheduling decisions at the per flow level, what would the control loop be like? When the first packet of a flow arrives, the switch will report the information of that flow to the neural network. Then it will compute the scheduling result. The inference of neural networks usually takes tens of milliseconds. And during this time, packets of this flow are still being processed with some default rules. When the decisions finally come back, after tens of milliseconds, most flows in the data center have already run out, making the decisions useless. Finally, when operators want to ad hoc adjust the existing rules of networking systems, such as routing reconfigurations, how can the adjustments be performed on the DNN-based rules? Let's see an example of a deep learning-based routing optimizer. The neural network has already decided the routing path for two flows, as shown in the figure. Now the network operators want to migrate the flows away from the link between node 7 and 10, due to some reasons, such as pricing or maintenance. If it's a conventional routing algorithm, such as the shortest path routing, network operators can just recompute the second optimal path for those affected flows. But for neural networks, The decision of one flow may affect another flow because neural networks are not robust to input changes. Other unrelated flows, such as the green flow in the figure, might also be affected in their computation, which will increase the migration cost. Now we know that DNNs are difficult to design, deploy, debug, and ad hoc adjust from the view of network operators. And the root cause is network operators could not understand why deep neural networks make such decisions. So what if we can interpret the behaviors of deep learning-based networking systems and speculate how and why they make such decisions? Thus, I'm going to introduce METIS, a general framework that provides interpretability for networking systems, and therefore sheds light on the problems above. So here is a challenge. As we can see, there are many scenarios under the umbrella of networking systems. How can we interpret those diverse systems? Are there any similarities among them? Our observation is that we can briefly categorize them into two types: local systems and global systems. Local systems collect information locally and make decisions for one instance only, such as congestion control agents on the end devices. Global systems aggregate information across the network and make global planning for multiple instances, such as the software-defined networking controller. For local systems, we find that existing policies are usually rule-based, with a simple decision logic. Therefore, our solution is to convert the neural networks inside the local systems into simpler and self-interpretable models. According to recent advances in the machine learning community, there are many candidate models that could be the target of the conversion. Our design choice is to convert those policies into decision trees. The first reason is that decision trees are non-parametric and can represent very complex policies by design. The second reason is that decision trees are lightweight enough for networking systems, which we will later demonstrate. Moreover, the structure of the decision trees also resembles the rule-based essence of local systems, such as routing tables. Therefore, we adopt a conversion method based on a teacher-student learning process. Operators still need to train the DNN first. The high-level idea of the conversion is that the DNN acts as the teacher and generates the input-output samples to construct the decision boundary in the state space. The decision tree is therefore constructed according to the samples of the DNN. And for more algorithm details, please refer to our paper. For global systems, our observation is that we can formulate many of them with hypergraphs. So what's a hypergraph? In the traditional graph, an edge connects two vertices. And in the hypergraph, a hyperedge can cover multiple vertices. So why can many global systems be formulated into hypergraphs? We find two outstanding features of global systems: the graph structured input outputs and the bivariate mapping. Graph structured input output means that the inputs or outputs of global systems are graph structured, such as the network topology. For example, in the routing results of a deep learning-based routing optimizer, we can formulate the interaction between routing paths and the links as the relationship between hyperedges and vertices. Bivariate mapping means that the global system constructs a mapping between two variables, such as allocating resources to requests. In such case, the two variables can therefore be formulated as a node and hyperedge. With the hypergraph formulation, the next step is to find out which connection between hyperedge and the node is critical to the optimization result. In the interest of time, I can't go into the details. The high-level concept is that we calculated the importance of every connection in the hypergraph. Network operators can therefore use this information to understand why DNNs make such decisions. And to make sure that the interpretation results to be understandable, we have three metrics to optimize and balance. The first metric is the performance degradation. The critical connections found by METIS should be those connections that have a great influence on the output of networking systems. The second metric is the interpretation consistency. Usually the number of interpretations that humans can understand is budgeted. Therefore, the number of critical connections should also be concise enough to be understandable for network operators. And the final metric is the determinism. That is to say, we expect each connection to be either critical or not critical. Otherwise, this crafty agent will learn to allocate all connections with the same importance and generate meaningless interpretations. Now I will show you some experiments that we did. We implemented Mattis onto 3 deep learning-based networking systems, including Pencil, an adaptive bit rate system, Auto, a switch flow scheduler system, and RootNet, a network optimization system for software-defined networking. 2 of them are local, and the remaining one is a global system. The interpretations of Pencil is a decision tree. We can clearly see the decision logic of Pencil in the figure. On the top 2 layers, Pencil first classifies inputs based on the last trunk bit rate, or RT, which is different from the existing methods. Mattis discovers that the information contained in the RT affects the performance significantly. Later, Pencil makes decisions based on buffer and throughput, similar to existing heuristics. We further show how Mattis helps to improve the design of Pencil. As we interpreted before, Mattis finds that Pencil significantly relies on RT when making decisions. Therefore, we concatenate RT to the output layer so that it can affect the prediction result more directly. The modified DNN will focus on the significant feature, or RT. We then evaluate the quality of experience of 2 models. From the curves of the original model and the modified model, we can see the modification improves both the training speed and the final QoE. The second case is how Mattis helps operators to debug Pencil. Pencil is known to have the problem of missing bit rate. We present the frequencies of selected bit rates by different algorithms. But when it comes to Pencil, 2 bit rates have an extremely low probability to be chosen. That is to say, they are missing, indicating that Pencil falls into a local optimum, which has also been mimicked by Mattis. Without Mattis, operators have to retrain the DNNs for hours to days without knowing whether it can escape the local optimum itself or not. The conversion from DNN to decision trees in Mattis exposes an interface for network operators to fix the problem, since the dataset to train the decision tree is highly imbalanced. We oversample the missing bit rates during the conversion. And compared to the original Pencil, the oversampled decision tree outperforms by about 1% on average on 2 sets of traces. Note that even 1% improvement in QoE is significant, considering the volume of videos for the current internet video providers. We further introduce a case of how Mattis helps to deploy on the case of Auto, which is a deep learning-based data center flow switching schedule, data center flow scheduler optimizer. The per flow decision latency of Auto is 62 milliseconds on average, during which 94% of the short flows in data centers will run out, according to the statistics of DCTCP. Converting DNNs into decision trees enables us to make per flow decisions for more flows with a shorter latency. In this case, Mattis together with Auto can cover 39% of flows on the same traces. And precise per flow control on more flows will also improve the performance of the system. By covering more flows, Mattis together with Auto can improve the average performance by up to 5% on 2 traces. Detailed analysis show that the improvement mainly comes from the optimization of those median flows, which are newly covered by Mattis. Finally, we have a case on how Mattis helps network operators to ad hoc adjust the RootNet system. Suppose we have a flow from node A to node E, and it needs rerouting away from the original path P0. There are several candidate paths, such as P1 and P2. The actual performance of each path is unknown until the rerouting rules are installed. Our observation is that since the candidate paths diverge at different nodes from the original path, we could estimate their performance by the significance of the connection between the diverting node and its next hop link. For example, P1 diverges from P0 at node A, and W01 is the significance of the connection between P0 and link A to B. Since W01 represents the significance of selecting link A to B, rather than other links. A lower significance value of a connection means that the selection is not critical in deciding the routing path. Therefore, lower W01 value indicates that path P1 might also have a good performance. Therefore, we hypothesize that the relationship between W01 and W02 is correlated to the delay of path P1 and P2. We verify this observation with the dataset evaluated in RouteNet. About 90% of points fall into the yellow and the green area. This demonstrates a strong correlation between these two pairs of values. Thus, we could provide an indicator for network operators to decide which path to reroute without estimating the end-to-end path latency. As a summary, we first demonstrate several problems of existing deep learning-based networking systems. We then design METIS, which first categorize diverse systems to local and global ones, and then interprets them with decision trees and hypergraphs. In our experiments, we implement METIS onto 3 systems, Pensive, Auto, and RouteNet, to show preliminary cases on how METIS can help network operators to design, debug, deploy, and ad hoc adjust those deep learning-based networking systems. More information and the open source codes can be found in our website. We do hope that METIS could shed light on and accelerate the deployment of deep learning-based networking systems in our community. So if you have any questions, please don't hesitate to reach out to me. Thank you.
Okay, thanks, Lee, for the nice presentation. Any question? Okay, Zli, I have 2 questions for you.
Sure.
The first question is that when you transform neural network to a decision tree, will you lose some accuracy or no?
Actually, almost no. In our experiments, for the case of Pensive and Auto, the performance degradation is about up to 3%, I think.
Okay, just very
yeah, because the actual policy behind the adaptive bit rate streaming is usually very simple. You can see, for example, the industrial usually use the buffer-based, which is actually very simple policy. So using neural network, even if you use the network, the policy learned by network may be also very simple.
Okay. The second question is that does your solution apply for reinforcement learning?
Actually, the conversion between the neural network and the decision tree is trivial if you are not the reinforcement learning, because you can just collect the data sets and retrain the decision tree. And in my case, or in cases evaluated in our paper, say the Pensive or Auto, they are based on reinforcement learning. So actually, we have several designs on reinforcement learning in our paper.
Okay, thank you. Another question? Okay, if not,
I have a question. Hi, Zli. So how your interpretation help to improve those systems, for example, for Pensive or for Auto? So what new insight you observe from interpretation? And then
yeah, sure. Yeah, as I just discussed before, if you can see this, we find that actually the last trunk bit rate, or RT, is very critical in the decision logic of Pensive. Because if you are using the traditional APR algorithms, such as the buffer-based or the BOLA or other algorithms, they usually focus on the throughput and buffer. And we found this one is very important. So we have a design on fix or improve the design of Pensive by putting this variable near to the output layer, or in other words, shorten the distance between the input variable of RT and the output layer, so that the training will be speed up, because the network will focus more on this variable. And the evaluation shows the similarity. The QE can be improved by about 5%.
So any relation with your approach to AutoML?
That's to some extent they are similar, because you are trying to find the neural network structure. Yeah, they have some ways to neural architecture search. But maybe they are too, I think from my opinion, they are too heavyweight for network operators because there are many parameters or the platforms to tune.
Okay, thank you.
Thanks.
Okay. Another question? Okay. If not, let's thank Zili for the presentation. Thank you.
Okay, thank you.
Okay. Then it moves to the final presentation in this session. The speaker is Dongzhu Xu. He's also a first-year PhD student from Beijing University of Post and Telecommunications, advised by Professor Anfu Zhou and Professor Huadong Ma. His research interest is network measurement, open source 5G, and MEC. Okay, Dongzhu, please go ahead.
Oh, thank you. Can you see my sharing screen?
Yes, yes.
Oh, great. Okay. Thanks for the introduction from my session chair, Prof. Li. Hello, everyone. Welcome to my talk. My name is Dongzhu Xu. Today, I'm going to present our measurement study on commercial 5G networks. This is joint work with my colleagues Guixian, Xi, Tongkai, Yiming at Beijing University of Posts and Telecommunication, advised by Prof. Anfu Zhou, Liang Liu, Huadong Ma, and also Prof. Xinyu Zhang from UCSD. 5G, as a monumental shift in cellular communication technologies, holds tremendous potential for spurring innovations across many vertical industries, with its promised multi-Gbps speed, sub-10 milliseconds low latency, and massive connectivity. Despite the huge potential, one should be cautious that it takes time for 5G to evolve and mature. The current 5G deployment commonly follows the pragmatic non-standalone mode, reusing the legacy 4G infrastructure to reduce cost. Specifically, the 5G radio only operates with a data plane and resides on the legacy LTE for control plane operates, with sharing the same EPC. On the other hand, whereas 5G optimization mainly resides on the radio access network, the end-to-end performance of mobile applications also depends on the WLAN path, cloud servers, and even the processing capacity of user devices. All in all, at this early stage, one natural question is, how far away is 5G from its prospects and ecosystem? In this presentation, we demystify operational 5G networks through a first-of-its-kind measurement study. We have collected massive trees and released them on GitHub. Our measurement focuses on 4 major perspectives. I will first talk about the 5G coverage issue. Briefly speaking, the early 5G deployment has poor coverage even at high base station density, and there exists a large gap between indoor and outdoor coverage. We first perform a blanket measurement within our campus region with 6 5G GNBs and 13 4G ENBs. We believe the campus coverage profile is representative because the 5G base station density on our campus is on a similar scale across our city's urban region. We traverse all road segments while carrying a laptop tied a smartphone to monitor the physical layer information using a commercial toy called ESCO. We then summarize the number of locations in each signal strength categories in the table. Despite the high deployment density, many coverage holes still exist. We then only focus on the same 4G ENBs coexisting with 5G counterparts. We found that even under the same deployment density, the fraction of 4G coverage holes is only 3.8%, still much lower than 5G. This may be due to the higher carrier frequencies used by 5G, and hence higher attenuation loss over the same distance. We now characterize the coverage profile around Y typical 5G GNB. We first 5G phone to lock on a specific cell. The contour plot connects the same locations with the same bit rates. We observe that the contour lines obviously derivates from the ideal circle shape, mostly biased by building blocks and multipath reflections. In addition, near the location A, B, C, and D, we measure the bit rate in the immediately adjacent indoor and outdoor spots. The resulting plots show that, on average, 5G has more than 2 times indoor-outdoor bitrate gap than 4G. We attribute the large drop to the higher frequency 5G signals, which suffer more from the penetration loss than the 4G signals. Considering the meager coverage of 5G indoor, we believe combining microcells with the current macrocells, such as 5G and Wi-Fi CPE coexistence, will likely fill the coverage holes. Next, 5G claims to support Gbps bitrate and sub-10 milliseconds latency through its new radio technology. However, its practical performance faces many attribution factors. To understand it, we measure the end-to-end performance of 4 mainstream transport layer protocols. In particular, we conduct some TCP and UDP experiments and use IPERF3 and trace-through twice, of which the server side is deployed in the closed server and the client side executes on our 5G devices. For each experiment, we log the traffic trace by Wireshark for offline analysis. Overall, our measurement is cross-layer by nature, spanning physical layer all the way up to the transport layer. We say that the UDP baseline for 5G downlink is 880 Mbps on average. We further examine the performance of 3 representative categories of TCP algorithms. For 5G, BBR achieves reasonably high bandwidth utilization. However, the traditional TCP algorithms suffer from extremely low bandwidth utilization. The result is a bit counterintuitive. To identify the root cause, we examine the packet loss under different traffic loads by sending UDP traffic at a certain fraction of the baseline UDP bandwidth. The results show that the packet loss of 5G sections already exceeds 3% even at about half of the baseline. We then proceed to locate the network bottleneck where the packet loss takes place. A potential reason lies in the buffer overflow along the intermediate routers within the end-to-end press. We thus estimated the network buffer size following the classical Stanford mode. We observe that within the RAN, the 5G buffer size is 5 times over 4G, but within the wired network, the difference is about 2.5 times. As the wired network buffer takes domain role, the buffer size on the whole 5G path is roughly 2.6 times compared with 4G. In contrast, recall that the capacity of 5G downlink is 5 times over 4G. That is, the capacity growth is incommensurate with the buffer size expansion in the wireline network. The end-to-end latency plays an important role for network performance. We select one example network path consisting of 8 hops and measure the RTTs as the hop count increases. We observe that 5G network paths achieve a network latency of 22 milliseconds on average. Clearly, the current end-to-end latency of 5G NSA module is insufficient to meet 3GPP's requirements of 10 milliseconds. We also found that the delay reductions mainly comes from the second hop. The reductions attribute to the flattened architectures of 5G in our measurement study. To put the above delay reduction in a big picture, we measure the RTTs of 20 remote open web servers and rearrange the RTTs according to the geographical distance of each path. We say that the RTTs of both 4G and 5G increases with path length, but the ratio between the gap becomes smaller as path distance increases. The findings cover a key message: the untamed latency in the wireline path, which is beyond mobile carriers' control, may neutralize 5G's latency advantage. Okay, besides the basic network performance, the application quality of experiments also depends on other factors. Here, we investigate the interplay between the communication and computing factors of immersive applications. We have developed a Ultra HD panoramic video Android app, 360tel, which connects to an external 360 camera with an H.264 hardware codecs. It can stream the captured video to the cloud server running RTMP service with up to 5.7K resolution and 30 FPS. We measure the video throughput as a receiver using the Wireshark. We also record the frame delay using a stopwatch timing method. Briefly, we use the instant camera to shoot the stopwatch and then record the time from the same stopwatch displayed on the video receiver. DRT is the end-to-end video frame delay. Okay, figure 1 shows the results. We observe that the average received throughput of all resolution videos doesn't exceed the 5G uplink capacity. However, we also observe that dramatic traffic fluctuation in dynamic sense, which occasionally overshoots the bandwidth and thus causes frame freezing. In this example, we find 6 frame freezing events within a shorter period of 30 seconds. We can conclude that despite enough bandwidth of 5G network capacity, the large fluctuation of video streams may cause low quality. The end-to-end video frame delay is critical to QoE of the real-time video telephony. Surprisingly, even for 5G, the radio frame latency remains 950 milliseconds. We thus break down the frame delay by separately examining camera capture, frame patch splice, codec, network transmission, video render, and show. We found that the frame transmission delay is around 66 milliseconds. We then estimate the frame capture and splice to be about 414 milliseconds. We also found that the encoding and decoding time is about 160 milliseconds and 50 response relatives. Overall, the frame processing latency is 10 times over the network transmission delay. In other words, the frame processing latency conspicuously parallels the end-to-end delay even under 5G NSA pattern. Thus, it's imperative to improve the smartphone's processing capabilities in order to support 5G's native applications, which demands both high bandwidth and low end-to-end latency. As we know, 5G's high bitrate comes at the cost of more sophisticated signals and packet procedures and radio frequency hardware. In the next section, we explore its corresponding impacts on the mobile device's power consumption. To obtain the energy consumption statistics on cost smartphones, we built a power logging and analysis toy called Power Strike. Specifically, the Android kernel driver naturally supports the bitrate state supply and record it to the system directory, so we can monitor the directory status periodically and put the log files in offline analysis. We first profile 5G smartphones' energy consumption and then break down the overall energy cost. The results show that the 5G module dominates the energy cost, far exceeding the screen display. The heavy energy consumption of video attributes to its more powerful RF hardwares and immature system-on-chip design. We know that the mainstream 5G smartphones adopt separate but less energy-effective 5G modems as a plug-in to the legacy 4G SOS system. So we argue that the 5G ecosystem requires long-term co-evolution with not only the latency internet infrastructure, but also the factors of 5G user devices. Based on the hardware, 5G radio tops the disk containers reception software machines and opportunistically switch from RC status for power saving. We employ the fine-grained energy traces for an example application session, where we trigger a web loading per 3 seconds for 10 times. Comparing the same experiment for 4G, we found that 5G has an excessively long tail stage. When running back from RC connected to RC idle status due to the NSA architecture, which leads to an additional waste of energy. It encompasses that the operator's traditional power management scheme is no longer effective for the new 5G smartphones. Okay, the above experiments indicate a simple way to improve the power efficiencies of the 5G state machine. We can adopt a dynamic model switch scheme, which turning on the energy-hungry 5G modules only when necessary. We design a trace-driven simulator to verify the effectiveness of this scheme. For comparison, we implement an Oracle approach, that is with perfect sleep and a weak transition under 5G. We observe that dynamic mode switching saves a remarkable amount of energy over the NR-NSA configuration for unsaturated web browsing flows. The NR Oracle does not show a significant advantage over NR-NSA, implying optimizing the 5G power management protocol alone pros marginal benefits, and the bottleneck may lie in the hardware itself. To sum up, we perform a massive measurement study. Our measurement reveals the imperative issues that hamper the performance of 5G. Some of these problems, for example, surprisingly low bandwidth utilization, can be solved through proper network resources providing, or more intelligent protocol adaptation. But others entails a long-term co-evolution of 5G with the latency internet infrastructure and radio or computing hardware. Our measurement insights point to feasible directions to optimize 5G. For more details, please refer to our paper and open source dataset. Thank you. Thank you for your attention.
Okay, thank Dongzhu for the great talk. Okay, so Chun, you can ask the first question. Oh, and I think just another Chun. Okay, so Jian Hong, I think yeah, you can go ahead with your question.
Can you hear me?
Yeah.
So you mentioned that RTT of 5G increases with the path length in internet, which cannot meet the 3GPP requirements. But can't this be solved by bringing the remote server closer to the client, such as edge computing approach?
Okay, thank you. That's a good question. Of course, the 5G's key technology like the MEC, mobile edge computing, could put a remote server to the closer to the UE user devices. The delay from the end-to-end performance will improve with the deployment of the MEC. But in our measurement, we argue that some end-to-end applications like the end-to-end telephony and the tel dimension is also depends on the end-to-end path, which includes the UE. Of course, the UE's computing capacity and the base station and the link from the core lines to the internet. also the whole end-to-end path often need the improvement of the 5G ecosystem of the all paths. So this which we in our environments we suggest the operators should improve the not only the RAN, the radio size of the network, but also the other components of the 5G networks.
Okay, thank you. And actually, I have one more question. So,
okay.
When do you think the 5G SA standalone can be fully deployed, and will the problems of 5G NSA will be solved after then?
Oh, sorry, I can't catch the last sentence. Could you repeat
So
again?
I noticed that most of the problems in 5G at the current moment is that it's because of its NSA deployment. So yeah, I was wondering when do you think the 5G SA can be fully deployed?
Okay. At the early stage of commercial 5G networks, the NSA mode is the commonly deployment method. As we know, so far the main operators of the world is only depends on the NSA mode to develop the 5G networks because it's low cost and easily deployment. But as the for the future deployments, the NSA will evolve to the SA architecture, whereas the control plane and data plane only plane depends on the link from the GNBs. This is a 5G base station to the 5G core. In our environment discouragements in the paper, we discussed the issues of the evolutions of the NSA modes. Briefly speaking, the many issues of our paper in this presentation is intuitive for the current deployment. But for the SA mode, SA architecture, some issues like the coverage hoist and the transport layer protocols adaptation will improve more. But other problems like the 5G devices, like power management and other for the not depends on the networks itself may still exist. For more details, you could find our papers and welcome to offline discuss.
Okay, due to time limit, I think for other questions, let's just give it to offline because I did not make a good control of the time. Sorry about that. We just okay. Yeah.
Okay, thank you.
Yeah, sorry for that. So that's all of the talks in this session. I think we are about 20 minutes behind the schedule. I think maybe we just have a 5 minutes break, then start and 3 o'clock Beijing time, or
yeah, I think we can just have a short break before we go into the industrial session. Yeah.
Okay. Thank you all for the participant. Okay.
Okay, so it's 3 o'clock. Let's come to the next session, the industrial session. So in this session, we will have 3 excellent talk. Okay, they're from Tencent, from Cisco, and from NVIDIA, Manox. All right. So our first speaker is Alan Lee. Alan is currently the chief architect of Tencent Cloud. Okay, and he's working on the cloud networking and data networking. All right, so today he will share us his experience about the scalable and flexible routing services for Tencent Cloud Access Network. All right, so let's welcome Alan. So please.
Okay, thank you. Can you hear me?
Yes, yes. Yeah, please go ahead.
Okay, thank you for the introduction. Hello, everyone. My name is Alan Lu, engineer at Tencent. I'm honored to be here to share some works with you. Today's topic is scalable and flexible routing service for Tencent Cloud Access Network.
Alan, sorry to interrupt for just a second. So I think during the talk, especially industry talk, there may be a lot of questions from audience. So for those, if you have question and you don't want to talk, you can type your question in the screen. All right. There is a chat button there. You type your question there. I can help you to ask the speaker. All right. So yeah, please go ahead.
Okay. Okay, this is today's agenda. First, I'm going to give a brief introduction of the Tencent Cloud Access Network, the scenario, the challenges we face, and explain why the traditional way cannot meet this challenge. Second, we will have a look at our new router architecture. And then I'm going to dive into the design details, take some use cases to see how we address these challenges with our new architecture. And last, I'd like to share some operational experiences and our future work. First, overview of Tencent Cloud infrastructure. Tencent Cloud International operates 54 availability zones spread across 27 regions globally. We have over 100 terabits per second public network bandwidth reserved and 15 exabytes for storage. And the scale is still growing rapidly. Tencent Cloud Access Network. This is what we will focus on today. With more and more customers deploying their services on Tencent Cloud, which are represented by the VPCs on the left of this diagram, how to efficiently interconnect customers' infrastructure with Tencent Cloud is becoming more and more critical for us. So first, we have provided a private LAN technology to allow direct connection between customers' on-premise data centers and Tencent Cloud access sites, that's providing high bandwidth, low latency network quality with high security. Okay, second, we have used the VPN technology to press these branches within their resource with low cost via internet. A third, for end users visiting these cloud services provided by cloud customers, we have built a large Tencent Internet Exchange infrastructure TICs in these access sites globally. And initially, we mainly relied on deploying traditional commodity routers in these access sites to meet various access requirements. However, as the cloud business grows rapidly recent years, more and more new challenges are emerging. And we found that the traditional way cannot continue to sustain anymore. So what's the challenges? The first is large scale forwarding table as well as the VRFs tunnels. For example, private LAN gateway requires up to 10K VRFs for a large number of tenants, and TIX requires up to 10 million forwarding table. Second, we had to roll out new network features fast to meet the various requirements from our business team, such as on-demand traffic engineering, interoperating with different kinds of networks and the services. Next, the capacity must be able to scale up easily to keep up with the fast growth of traffic volume. And meanwhile, we have to keep the cost at a low level to balance with the revenue. Okay, why the traditional router? Why the traditional router cannot meet this new challenge? Generally, the traditional router comprises 3 pieces of components. Processor acts as the control plane, running protocols like BGP, OSPF. LAN card acts as the forwarding plane with limited routing tables, echoes, and fixed forwarding behaviors. And switching fabric in the middle is responsible for high-speed internal interconnection. These components are usually tightly coupled. The processor capacity, routing table size, and bandwidth are usually configured with the fixed ratio. It's impossible to independently scale one dimension of them. And moreover, as the traditional router is always hardware, software vendor lock-in, a managed change may take vendors several months or even more to design, implement, test, and release. And in short, the traditional router doesn't target cloud purpose. So it's hard to scale, lack of feature velocity, and expensive. So obviously, for cloud scale purpose, we need a new router architecture. So the design principles include, first, scalability. Each component, data plan, routing plan, control plan is able to scale up independently and on demand. And additionally, each functionality inside one component is better to scale up as needed. The second is the flexibility. New network features must be able to roll out as quickly as possible. Then the reliability. Cloud services require higher network quality compared to Tencent self-operated services, which have built-in HA mechanisms allowing them to fail over fast. However, for cloud services, they highly rely on the availability of the network. The network quality required is at least 1 order of magnitude higher. Operationality. The network service must be easy to configure, debug, and monitor. So based on those design principles, this is our new router architecture, software-defined router. We call it SDR. The key insight is moving the complex router functionalities into software running on the number of servers, which is overlay network in this diagram on the top of the diagram. For overlay network, we further decouple them into data plan, routing plan, control plan, and global orchestrator. Each candle of the component is deployed on a separate server cluster. Each of them can be designed, maintained, and scaled independently as needed. And meanwhile, as overlay network is totally software-based programming, so it's very flexible to develop new network features and interoperate with different kinds of networks and services. So for underlay network, on the bottom, it just acts as a simple IP backbone by leveraging simple commodity switch for interconnection of internal components and external networks. Next, let's dive into the SDR insight to see how these components work together. First, at the edge of the SDR, bottom right in this diagram, we deploy edge access switch EA to connect with external router. EA is a simple commodity switch, works at layer 2, and does layer 2 isolation for different tenants or RSPs. Data plan is responsible for high performance packet processing with large 14 tables. It communicates with EA via layer 2 VXLAN tunnel and communicates with the VPC via TGRE tunnel. TGRE means Tencent GRE. We have just customized the standard GRE for some special purpose. The data plan is also responsible for redirecting signal messages like BGP and BFD to the routing plan. In addition, the VXLAN fabric has been built among the whole SDR domain for traffic engineering. Okay, the routing plan is responsible for peering with the external routers for routing information exchange. And the BGP message are carried over layer 2 VXLAN tunnel between external router and the SDR. So the routing plan and the external router are able to establish BGP session directly. On the top, the orchestrator acts as a global controller. It is responsible for distributing operators' configuration requests to corresponding SDRs. And orchestrator is also responsible for collecting particular traffic scheduling requests. Some of them may form the external management system and synchronizing them to corresponding SDRs. Control plane acts as the local controller. It is responsible for programming configuration from orchestrator to corresponding nodes of the local SDR. Apart from that, control plane has provided distributed message queues in order to efficiently synchronize dynamic forwarding rules among data plan cluster and the routing plan cluster inside one SDR. So we can see that these different kinds of components are loosely coupled with each other. We can easily add or remove one instance into each kernel component independently for scaling or upgrade purpose without affecting other components and affecting the whole system. And meanwhile, from the outside network perspective, SDR just behaves as a role of router. Now let's revisit the customer access scenario I described earlier and look at how SDR works for them. On the top of this diagram, we deployed SDR as PL gateway, private LAN gateway. Customer router is connected to Tencent EA switch. Different tenants are isolated by layer 2 networks. And the BGP session is directly established between the PL gateway and the customer router. On the bottom, we deployed SDR as VPN gateway. For VPN gateway, IPsec tunnel will be deployed first to provide the security for the traffic traversing the internet. On top of that, BGP session is established between VPN gateway and the customer router. both the routing information from PL gateway and the VPN gateway will be propagated to VPC side. Usually, VPC will choose the optimal route, which is from the PL gateway to send the traffic back to the customer side. Once PL gateway fails, VPC can quickly switch to use the VPN route to send the traffic back to customer side. The PL gateway and the VPN gateway can back up each other. Sorry. By deploying SDR, we can easily interoperate with both the traditional customer networks and SDN-based VPC networks. Moreover, SDR can support up to 10K tenants per tenant rate limiting and statistics for billing. All these capabilities can scale up as needed. Okay, this is the end user access scenario. For this scenario, we deploy the SDR as TICS with Tencent Internet Exchange to communicate with both the ISP routers and our internal VPCs. Again, EA is used to connect with the ISP routers and does ISP isolation via layer 2 networks. BGP session is established between TICS and the ISP. The routing information will be propagated to VPCs and other SDRs. For traffic engineering purpose, the VXLAN fabric has been built across the whole SDR domain. For inbound traffic, after ACL processing, SDR forward the traffic to corresponding VPCs. For outbound traffic, SDR uses the BGP routing information along with the flexible rules to choose the best exit for user traffic. Sometimes SDR may forward traffic to another SDR traversing Tencent backbone network. Okay, the key challenges for this case include massive scale routing table and the various traffic engineering requirements. By deploying SDR for TICS, both of them have been greatly improved. Next, I'm going to take some user cases to demonstrate the flexibility of SDR. Most of the time, BGP can work well for traffic forwarding. However, it's not enough, as BGP just indicates the network reachability based on the shortest path of destination IP. And sometimes we need to take more metrics like source IP cost into consideration for the traffic forwarding. For TICS scenario, we like to differentiate services to better use our edge resources. So for example, we want to schedule the lower QoS required traffic to a particular exit for cost purpose. So to do that, we program flexible rules as source IP, destination IP tuple mapping to a specific exit into the SDR data plan to overwrite the BGP route. Even more, we can encode the VNI to identify one specific peer among multiple peers in one site for fine-grained traffic engineering. Yeah, of course, we had to inactive those flexible rules and fall back to use BGP for packet forwarding when the related BGP rules are withdrawn. Moreover, as the traffic is transmitted via VXLAN fabric, all of these overlay forwarding rules are transparent to the underlying network, so we can still keep the underlying network simple. By doing this, we have greatly improved the flexibility for both Tencent Cloud services and Tencent own services. Actually, we have received lots of such requirements from our business teams. This one, next one is about the security service. We deploy firewall service associated with the SDR for security purpose. For one specific user's traffic, the firewall service needs to be fed with both the inbound and outbound traffic. So to do that, we program flexible rules as destination IP mapping to the firewall VNI tuple to steer inbound traffic to firewall service, and rules as SIP mapping to firewall VNI tuple to steer outbound traffic to the same firewall service for security processing. To allow flexible deploying firewall service, we also have built a very excellent fabric between the firewall service and the SDR. Currently, SDR can support up to 100 key flexible rules for firewall purpose. And we can scale up them as needed. Apart from the firewall service, we also deploy DDoS service associated with SDR, especially for the TIC scenario. A DDoS is just for the inbound traffic. Once the attack traffic detected DDoS, it uses the BGP to advertise the related routes to SDR. By programming the routes into data plan, SDR is able to redirect the attack traffic to DDoS. Yes, same. It's very simple. It's very easy. However, the DDoS traffic is always short burst and high volume. So to protect our servers, to protect our data plan, we want to redirect the attack traffic to DDoS service at EA instead of data plan. To leave our data plan only handling the real traffic. At the attack traffic, we just described is forwarded based on layer 3 routing table. That means the EA has to act as layer 3 switch. However, in our design, EA works at layer 2. How a layer 2 switch forward traffic based on layer 3 routing table. This will, thanks again to the flexibility of server-based programming. With a minor modification of SDR, neighboring system, and some configurations on EA, EA is able to use the routing table to forward traffic. So specifically, attack traffic will be redirected to DDoS service at EA switch according to the routes advertised from DDoS service, and the normal traffic will be forwarded to data plan according to the default route pre-configured on EA. And for the outbound traffic, EA still works at the layer 2 network. By leveraging the flexibility of server-based programming and standard function of commodity switch, we're able to build a flexible and robustness DDoS service for our customers. For practical reason, SDR has to support incremental deployment and interoperate with existing traditional router inside Tencent network. As this is different from the interoperating with the outside network. Okay, this is just for the Tencent inside network. And the traditional routers are running in MPLS network. How to efficiently interoperate with them is a big challenge for deploying SDR in the production network at the beginning. The straightforward approach is to implement the Intel MPLS functions on SDR servers. However, it's complex and not a good idea for future evolution, as we target to keep SDR simple and clean, and we don't want to introduce additional features which will be deprecated later. So Finally, we choose to deploy a commodity MPL switch between SDR and the MPLS network. This MPL switch acts as a PE to communicate with the traditional router using MPLS technology and communicate with SDR with only IP technology. BGP session is established between SDR and MPLS switch for routing information exchange. What we have done is just a minor change in the SDR software. After that, SDR can interoperate with the existing MPLS work properly. And the whole MPLS network is transparent to our SDR. This approach greatly speeds up the process of deploying SDR in our production network. Next, I'm going to talk about the scalability of SDR. For SDR interconnection network, we leverage classic clause architecture, which has been broadly deployed and fully verified in our data center network. And BGP is deployed among servers, access switches, and core switches. Each server is double connected to two access switches. Data plan, control plan, and the routing plan has implemented its own scalability mechanisms respectively. With this design, each layer of the network is able to scale up horizontally. Even more, underlay network and overlay network can be operated by different teams accordingly. So currently, SDR provide 3.2 terabits per second forwarding capacity and 100 key per second routes update capacity. And the capacity can be scaled up easily by adding more instances into the cluster. Okay, the hardware acceleration. To further improve the forwarding capacity, we have also introduced the programmable switch, Tencent Smart Switch for hardware acceleration. In order to cooperate with the Tencent Smart Switch for offloading, here data plan employs an efficient offloading framework for real-time detecting and reporting the elephant flows to the control plan. The control plan then programs Tencent Smart Switch with the flow information. Apart from that, the control plan is also responsible for collecting specific flow informations related to high volume traffic, mainly from our external management system, and synchronizing them into Tencent Smart Switch for offloading purpose. So after that, for the traffic, match the flow rules on Tencent Smart Switch is forwarded directly. For the remaining traffic or signaling packet like BGP BFD or IP fragments, it will be redirected to the server-based data plan for normal packet for processing. Tencent Smart Switch provides us hardware level high performance with general forwarding pipeline, which have greatly improved the SDR forwarding capacity and meanwhile maintain a high flexibility. Reliability. Reliability is another critical piece of capability we had to provide for our customer. First, according to the redundancy architecture design, we know that any single point failure, no matter it's a server, a link, or switch, will not affect the whole system availability. Second, if the Intel control systems fails, data plan is able to continue to process packet accordingly as it keeps the last good state of forwarding table. If the entire routing system fails, and the control plane is also responsible for real-time monitoring the health of the routing plan. Control plane will stop synchronizing the forwarding routes from routing plan to data plan. Thus, data plan can still forward packet properly. Apart from that, normally we deploy the 2 routing instances at each site for routing plan redundancy purpose. For scenarios which only 1 BGP session is allowed, we had to use another mechanism. Specifically, we split BGP functions into BGP speaker unit and the BGP root computation unit, and then distribute them among servers at the granularity peer, which allow us to limit the failover scope, restart a single instance, and recover the BGP session quickly. We also have implemented a couple of probing and fast failover mechanism to improve the reliability of SDR. By leveraging these technologies, we are able to provide non-stop forwarding and non-stop routing capabilities for our customers. For operationality, we have built a real-time monitoring and operating system, RMOS, on the bottom of this diagram, covering all aspects of the SDR system. Here we just take the data plan monitoring as an example to illustrate the mechanism. First, 3-level data plan probing, which are cluster level, server level, and the core level probing in order to quickly detect and handle failures. Second, we have conducted a critical resource monitoring for resources like buffer queues inside the data plan. Once any anomaly detected, related servers will be isolated soon. And in addition, sufficient statistics and events like packet jobs, CRC errors will be reported to control plane in real time. When it exceeds a certain threshold, the device will be removed from the cluster. And the RMOS system is still in the rapid iteration process, and more new features will be delivered in the future. Next, I'd like to share some operational experiences from the production deployment. First, to minimize the operational error, using the centralized orchestrator instead of manual configurations on different components to configure the whole SDR system. And second, provide robust one-click operation to quickly and safely turn off the SDR system for operators when needed. And third, keep the message queues among different components reliable and efficient. As these components are loosely coupled, any minor configuration difference may cause unexpected forwarding behaviors. So it's really, really important. Next, I'd like to share some future works. First, for network visibility and monitoring, we need a global view end-to-end network quality detection and analysis system for different network layers, underlay network, overlay network, and application level network. The second, based on the results of the end-to-end network monitoring, we are going to explore automatic traffic engineering by taking more metrics into consideration. A third, we plan to implement the simulation and the verification system for both the data plan and routing plan in order to detect and fix system abnormal behaviors in advance. Okay, in conclusion, by leveraging this disaggregated software-defined router architecture, we managed to provide Tencent Cloud a highly scalable, flexible, and cost-efficient cloud scale routing service. That's all. Thank you very much.
Okay, thanks, Alan, for the great talk. So we have plenty of time for questions. Okay, I think it's a great opportunity, right? Alan, tell us a few things about Tencent Cloud Access Network, right? So for any question related to his like practical experience, so this is the opportunity to ask him. So let me see. Let me see. Okay, Chen Chen, you have a question?
Hello, can you hear me?
Yeah, yeah.
Okay, thank you for giving me the opportunity to ask a question. And Alan, thank you very much for sharing the interesting practice in at Tencent. So I have a question related to your underlay data plan. So you mentioned there could be up to 10 million rules. So what kind of underlay data plan you are using in Tencent to support so many rules and guarantee all the matching for the rules would be in time?
Okay, first, the data plan is in overlay network, not in underlay network. So that's the key point. So all of the 10 million forwarding rules are installed in the overlay network in our server memories, not so it's transparent for the underlay network. So no.
Okay, so can you support, so if that case, I guess you support like per flow processing, not per packet processing.
Yes, we mainly use the, most of the time we use the LPM algorithm for the traffic forwarding. For some specific cases, we use the flow-based forwarding. Yeah, I just talked.
Okay, so
the
if
different
the
scenario, yeah.
Yeah, if the rules or the flow tables are kept in, accommodated in server memories, so how fast can you support the matching, the processing through that?
Okay, we have an internal mechanism to optimize the packet processing. Yes, I know that you mean
yeah, so
so
can
many,
you share
so many
some
stages for packet forwarding, so how to maintain the performance and with large memory. Yeah, we have an internal mechanism. We optimize the whole packet processing continually to improve that.
Okay, so if possible, can you share some a result or some information related to the throughput or delay related to the processing?
Yes, I just described that we can support currently with the, yeah. Okay, well, I can't talk too much about
I'm
that.
just curious.
Yes, I know that it's not a secret, but I can't talk too much. I think we will publish more details about this, our design.
Sure.
Yeah, yeah. Okay.
Sure, no problem.
Thank you.
Okay, thank you, thank you.
Any other questions? Yeah. For the rest, you can think about your question. Actually, there are some questions from audience in the chat. So let me ask Alan for them. So here's a question. So how much the cost does SDR takes in order to operate in additional features compared to a traditional router?
Sorry, how many what cost?
How much cost does SDR take in order to operate additional features compared to a traditional router?
So how much cost or class, sorry?
Cost, expense, cost.
Oh, how many cost?
Yeah.
Oh, you mean the compared to the traditional router, right?
Yes.
Yeah, generally as so, yeah, this question is that generally we just take the commodity router, commodity switch, so compared to the traditional router. So the cost is a good question, but I I can't talk too much about that.
All right. So yeah, it's okay. So maybe the next question, not talk about the money, right? That's sensitive. So
yeah, we'll focus on the technology. Sorry.
Okay. So are there any performance issues when you use SDR instead of hardware solutions?
Performance issues, so the first we just leverage the commodity switch or leverage the user space networking stack, the high performance IO, and to improve the performance packet processing on our servers, and then we also introduce the hardware acceleration for our performance improvement. Yeah, okay.
Okay. So here's another question. How can non-stop forwarding and non-stop routing can actually be implemented in SDR? The sort of question.
I just described the mechanism of them. So I think if you are interested with that, we can talk about this offline.
Maybe offline. Okay. So all right. So any other questions from our audience? Any more questions? Because this year, because online, we have no panel session. So this is only an opportunity for you to ask questions for industrial speakers. All right. So if no more questions, let's thank Alan again. And let's move to the next speaker. Thank you, Alan.
Okay, thank you. Thank you very much.
So you can stop sharing and we shift to the next speaker. All right, so let me introduce our second speaker. Our second speaker is Philip Wang. Philip is the principal solution architect of Cisco Great China area. He's leading the multi-cloud and zero trust security solution development in the region. Since joined Cisco in 2006, like over 14 years ago, Philip has been an active practitioner and thought leader in SDN, IoT, and network security. And before joining Cisco, Philip had 15 years experience in delivering innovative banking solutions during his tenure with Microsoft and IBM Hong Kong. Okay, today he will be talking about the end-to-end zero trust network security framework. Let's welcome Philip. Philip, please go ahead.
Thank you, Chen. Thank you very much. And it's a very honor to be here to share with you the Zero Trust Network Security Framework. As the framework implies, it's an open platform that we can talk about some collaborations after the sections. So without further ado, here is my agenda for today. I will talk about briefly about the trends and challenges that we have encountered. And then I guess many of you have heard about the keyword Zero Trust. But today I'm going to share with you a practical Zero Trust approach. And also we'll finish it with some use cases that we have been working with customers. And at the closing, we will talk about some of the extensions that we may be able to cooperate or collaborate in the future. So I guess everybody understand or find out that we are in this mobility world, and we have a sheer number of mobile users or remote users. And we have many devices, and these devices could be from the original mobile or laptops now to more IoT devices. And in the previous section, you have heard about 5G is coming. So many of these trends actually increase the total number of users and also the devices that require network connections into, and they will be fully meshed together. And that's on the people and the entity side. And we also have another, on the other side, that's the transformation on the application side, that we are transforming not just from the type of applications, from the traditional single unit, be it a bare metal or virtual machines. Now we actually transcend to microservices, container-based applications, and these applications are actually scattered or geographically dispersed everywhere. It could be running on cloud today, or it could be running on-premise, or it could be a hybrid of both. So in all these factors adding up together, we have a very blurred line of perimeter. In the past, when we try to provide protections, and we sort of use a very traditional way of thinking and a castle approach. If we have to establish our perimeter as our fence to fence off the attacks, this kind of approach works for many. It has been working for many years and all the way. But with this diverse device, mobile device, and growing number of this 5G trend, and together with the shifting of the application services to scatter everywhere, we just have a different parameters that we need to handle the situations. But can we do it the other way? We still need to grant the access, right? We can't say that because there are attacks everywhere, we have to shut down all the ports, shut down everywhere. We still need to grant the access. Don't get it wrong, but we try to grant the access to be very specific. So here we have, you probably heard about a term that also been talking some elsewhere. It's called least privileged access, which means we grant access, but we grant very specific. By means of very specific, it could tie into not just a device, a person, but we also take into consideration of other factors like locations, the timing, the whereabouts of this person, the whereabouts of this device. Is it going through a wide connections or mobile connection or wireless connections? All this kind of what we call the contextual data we need to take into consideration when we try to develop the protections. So it's actually a paradigm shift from in the past we focused on the attacks. Okay, where is the parameters that this attacks will be coming from? We stop it from there so that we can fence off the attack. But in the new approach, we should more focus on how we protect the data. We just treat it as the fact that there will be attacks anyway. So you can make the very broad assumptions that all environments are hostile or breach. So in that case, if that's the case, then we need to think from the other way around. Is instead of stopping the attacks, we need to think about how to provide protections from any point, and it has to be very specific. It has to be very to the point. And if that's the case, there is also some mindset change. For example, we no longer will only authenticate a user only or authenticate a device. We have to consider a device and a user plus other parameters like what I've mentioned just minutes ago about the locations, the way that this device and the user combination happens. We need to take into consideration of all these information. And also the authentication doesn't mean the authorization. In the past, maybe you are authenticated and then you can free to mill around the networks and you can access all the resources. Not anymore, because authentication is maybe just a step, maybe the very first step that we're talking about. So with that, before we get into the architecture things, then just a quick recap of the Zero Trust. Actually, the word has been around since 2004. If you Google, you can easily find the Jericho forums. That the original thought is about a bunch of CISOs, and they talk about a very three-dimensional problems of the perimeters, how to deperimeterization, how to they recognize the fact of what I just mentioned about this. The perimeter is so blurred. You can imagine that those group of people are really talented, and they have these visions more than 16 years ago. And then over the years, there are many implementation of this Zero Trust, and the word of Zero Trust has actually been transformed and redefined by the by some consultants outside. And I think today it's quite fair to say that zero trust architecture is a more general term that the industry sort of come to a consensus point that is accepted as an idea. So we need to, if we are going to embrace this the zero trust architectures, we have to recognize there are, before we come up with the sample architecture, we need to have some pillars, some foundations that we need to think about it when we design our zero trust architecture. So first of all, as I said, the perimeter is so blurred that let's eliminate the level of trust. So don't just think about in the past that you cross a zone, a DMZ zone or whatever zone, then you are secure or you are more secure. Let's put it aside and say that this kind of flags will exist not just external, but it will also be inside within your usual protected areas. And then we talk about the user and the applications, the device, and all this need to be, we shorten the authentication. Even though if you still rely on the authentication, you need to shorten the authentication time windows to maybe within seconds, or even if necessary, could be microseconds for that kind of access authorizations. And then since we are talking about so many devices and so many people, and together with so many parameters that we take into considerations, we can't use the traditional rule base. We still use rules, but we can't use a lot of, in the old networking world, we use this access control list to protect the VLANs. We still use this kind of, as the last mile to protect some zoning. But if we are going to protect the resources that we're talking about so scattered, even down to microservices, we need some kind of policy-based, I will elaborate more. Basically, the policy-based, and many people have different definitions, but basically is through the grouping of the nature or similar nature of the resources or person or device together, and then apply the policies using a policy-based engine. So we don't apply the policy down to individual devices, but we use this grouping concept to apply the policy up point. And the policy has to be dynamic, because we talk about the timing is also very important attributes. The location, the whereabouts of person or device is also very important attributes. So adding up together, we need to calculate this kind of scoring or the posture, or so that we can be able to always authenticate whether these resources, this combination is allowed through your network to access the ultimate resources that they want to reach out to. So as a result, logging, continuous monitoring, and this kind of rescoring is definitely necessary. And adding up all this, manual process is no longer feasible. So we need automation. So that's why we need open API. We need this kind of a DevOps mindset. You can have the DevOps automations to automate the entire things from how you categorize the devices, how you establish the trust engine, and then to how the ongoing running, you monitoring it. And we also need to leverage probably some machine learning capability to find the anomalies or the abnormal behavior or malicious behaviors. So from Cisco point of view, we take a broad, generally speaking, we take three big steps. The first step is we establish the trust. So we still need to establish the trust, although now to establish trust, we need to consider many factors. And then we do the enforcement based on the trust that the model, the policy that we establish. And then the final step is not the ending step. It's actually going through the enforcement and the continual monitoring of the enforcement and how actually the resources access behavior or deviation from the normal behavior, feed it back to the policy trust creation engines. That will be in never-ending cycles. So in each of these different areas, we will have different components to do that. So say, for example, in establish the trust, we need to have the user identity so that we can identify the person's roles, his whereabouts, his location, his other context information. And because we come from a brownfield world, so there will be a lot of legacy information we need to also take into embrace. For example, the Active Directory, the LDAP. These are the informations that we also need to consume into this trust establishment model. And during the enforcement, we need to as I said, we need to be very specific to the point and give the least privileged access. But the enforcement could be anywhere, because it could be on the cloud, it could be on-premise. So we need to not limit the enforcement engine, the enforcement points, or the policy enforcement point. The next chart you will see that to be more diversified, so that we can, even though you may escape one checkpoint, you may not be able to pass through the next enforcement point. So and in the continuous monitoring of these resources, we need not only the previous engine of the log, we need some intelligence, like machine learning or intelligent baselining that can help us to fine-tune the entire business model. So of the many different zero trust architecture in the markets, and this is a sample that I would like to share with you. So we actually borrow the concepts of the software-defined network. We have this control plane and data plane, and everybody understand what it means about. And if we put it into the context of the zero trust architecture, you can view that the control plane is actually in summary, is the policy establishment, how we establish the policies. And the data plane is actually where we enforce the policies. So, so if we zoom into each of these areas, let's take a look at the control planes first. We talk about we need to consider different parameters. First of all, we need to understand who are going to use the resources. So the user, the inventory, the user directories, the roles, the responsibility, all this kind of metadata we definitely need to collect. And for the device, similar for the devices. The devices could be mobile devices, any devices that will be participating in the networks. And this device will either consume the services from the network, from the entire architecture, or provide the data, because then there may be some sensor, as simple as IoT sensors, also a device that we need to monitor these kind of devices. And last but not the least, is definitely the workload, the applications that provide, ultimately is the application of microservices that provide the services to us. So these are the inventory, the area that we also need to monitor. So all these components together with other sources, the other parameters, I will get to that point later in our illustrator examples. All this adding up together is what we call it the PIP, or the policy information points. These are the points that provide the policy information, or the raw data for us to build the policy engines. And then in the center, we have the policy engines, the zero trust policy engine. Here is like the SDN could be the controller, or it could be the SDN controller. Here's where we will do the administration of the policy, create the policies, and correlate the policies, as well as my title, my section topic title is end-to-end. We not only cover one areas, we need to cover multi-cloud, we need to cover multiple areas. So this is the point that where the policies will be dropped, and also will be disseminated to the enforcement areas. And we also need a trust engine. The trust engine is the rule-based engines that would, remember we talk about how we classify the workloads in all the devices in the groups, and then based on the groups, based on the profiles, we apply the policies engines through the policy and administration or decision points. So this is the way that how the control planes look like. On the data plane side is where the policy is going to be enforced. Then you will see that as I said, the policies enforcement point will be happen on the different areas. For example, on the networks and different network components. It could be on the switches. It could be on the router. It could also be on the service appliance like firewalls or some other third-party devices. These you need to be based on an open architecture, because certain area you may not be able to do the enforcements. And also another enforcement point could be on the device itself, or it could be on the workload itself. If we're talking about the application, it could be on the application, it could be running on the bare metal, it could be a server, or virtual machines, or a container instance, or it could be running on the public cloud areas, it's a instance, or also a microservices. So these are all the policy enforcement points. But the question will come up is, some of these enforcement points I may not be able to do the enforcement, because I may not be able, if you need to do enforcement, you either leverage the OS, this operating system's capabilities like IP tables, firewalls, features, or some other add-on agents. So we need to have a more broader view, the more open-minded capabilities to do this policy enforcement. So say, for example, if you cannot install the agents on the container host, how could you do the enforcements? Then you think about it. Could I do the enforcements on the physical port that hosts that container host? Or if I don't host the bare metal server, can I do it on the virtual machines? Or could I do it on the virtual port group area? All these are the policy enforcement points. Or if all those options are not available, then you have to do it some other way. Say, for example, outside the host, outside the networks, maybe on the leverage on some service appliance, or that, or in between the path, you have some inject some devices which the policy engine will be able to talk to provide this kind of enforcements. And remember the step of this entire architecture, the final steps or the policy enforcement point, we still need the feedback engines to feedback the actual traffic, the attacks, the data attacks, or the violations that being monitored or being captured at the enforcement points. So this information needs to feed back to the policy information point as a basis to fine tune, to change the policies. So that's how the overall the sample zero trust architecture will work in these examples. So if we extend this concept, right now we have a sample architectures, how we are going to implement this or do this enforcements or implementation on the actual environments that we are facing. From Cisco point, where we classify them to the into three major areas. What we call here is called the workforce, workload, and workplace. Workforce, as its name implies, is talking about the people and the device. So it's more focused on the how we can protect the people with the device, how we authenticate. It's more like the device authentication based on the person together with the additional parameters like where are you connecting to the architecture. Are you using the mobile connections? Are you in-house using a Wi-Fi, or you're somewhere around the world? These are all the other contextual data that we want to take into considerations. Based on this in combination, we will perform the corresponding authentication. And then the workloads is where the applications, the microservices, the containers, the actual applications runnings will be providing. And this is the way the resources that we surely need to protect, and we will have some examples to talk about this. And then the workplace is more like the office environments. So you will have the wireless and the network. And also we're talking about different devices like the campus network type of protections. So it will be the key part after we classify them into this workload, workplace, and workforce categories. The most important to have the end-to-end is these policies that we talk about from the provisioning of the zero trust architectures. They need to be interchanged. They need to exchange these policies so that the policies from where you authenticate as a device, as an owner into the network will be carried forward to where you can access the workload. And with that, we also take into consideration of where in the workplace, which zone, which departments that this device and the person combination is being used to access the resources. So today I may not have much time to talk about all these three areas, so I pick up one of the use cases in the workload area to elaborate how we do apply this zero trust architecture in the workload protections. So as I said, this very first rule is that there will be no network-centric authentication. So it doesn't mean that the workloads, then if it is behind the firewall, behind two levels of firewall in the color zone, protected zone, that workload is being put is a trusted workload. So we still need to move the perimeter very close to the workload. Ideally, we want to move the protections down to the unit of work that provide this kind of services, or this particular unit of work to consume the services. And what's adding the challenge more is this so-called unit of work to provide the services, to provide the work application services. We are actually moving to a serverless world, be it we are moving workload to cloud, or be it we are transform our applications from so broadly, so geographically. So then we need to have first of all, we need the engine to help us to do the auto discovery of these services and be able to tell us from the actual flow of the traffic how these workloads are talking to each other. Are these workloads are using the protocols that we want them to be to talk to each other? And then, so this, first of all, we need to monitor and capture every flow. Secondly, instead of using persons or people to monitor it, to classify them, we apply machine learning. We apply supervised, unsupervised machine learning, which is basically the grouping capability to form the cluster by observing the traffic patterns. We can be able to classify the workloads into different clusters. So we do have a white paper to talk about how we can do that. Very simple, we can use the centroid theories to calculate the vector distance, just like calculate the center of gravities of critical shape mass or changing mass. So we can tell whether the group loads belongs to this cluster or the others. Another capability that we can use is we use the baselining to monitor the activities of these workloads. So that, for example, be it a container or virtual machines, we can measure the capability or the behavior of this. Does it frequently behave as a provider, or does it more as a consumer, or does it have a pattern that it tends to be a provider during the day, and it will be a consumer during the nighttime batch processing? These are all the footprints or fingerprints that we can baseline it, and the whole purpose is we want to identify the anonymous. We want to identify this what is the suspicious behaviors of these workloads. And then once we get at this machine learning, clustering, observation, baselining, then we can the system will be able to help us to establish the trust policies. And as I said, the policies after being established, before we enforce, we also need to do some simulation. Because simulation is very important. We don't want to drop some legitimate flows in the architecture. So we need to do some simulations. So the solution itself must be able to carry like a time machine that record everything, like a recorder, record everything, and then you can play back this against the simulations. And as I said, sometimes we may not be able to do the enforcements. You may not own that piece of workloads. So the enforcement has to be multi-domains. So if we can own the workloads, we can use agents there. The agents will be able to do the enforcement for you. Or if not, then we can rely on the network. We can rely on the network, which is similarly can take the policy model in that you establish the models and then enforce the policy on the physical port or the virtual port group, or even down to the container port to do this kind of enforcements. And last but not the least is, of course, the open integration with other third-party appliances, like the layer 4 to layer 7 appliances, also a point that we can do the enforcements. Or, of course, if it is switching, we can also do, if they can inject some third-party rules and like YAML or netconf, we can also do this kind of enforcements there. So one of the great challenges that I talk about is migration from the mode 1 to mode 2 application, or people will say that it's from VM to containers. The more deep the idea or the ultimate goals that people want to protect is we are living in a brownfield world, or unless you are like fintech or startup, you completely start your application profile from the microservices containers. You don't have this problem. But many of my customers actually have these issues that they're migrating from this mode 1 to mode 2, or they're going to have this hybrid mode applications, that they have a significant amount of applications that are on-prem using the brownfield and more like a VM-based or traditional-based server-based hardware. But they also have the workloads being migrated, or be it through the partnership with some other third-party developers, or through the M&A. They may have some new partnerships or divisions that they develop the application completely new on the new platforms. So how could you securely bridge the gap of these traditional applications and the new applications they're running on from nowhere, that the IP address no longer, actually you can catch them with the IP address, because if people can familiar with the container applications, the IP address or MAC address doesn't mean anything, because the application is actually morphing and they will change the IP every minute or every second. So you need new ways to signify or identify this kind of workloads in order to do the brownfield and greenfield coexistence. So what we could do is we make use, as I mentioned before, why we need to embrace open data, open source of data should be calling it, is we try to use the annotation from the other sources of workloads, if we take workloads in this case examples, to ask kind of identification, so that we will be able to signify, to classify them into different clusters. So in these examples, so we take Kubernetes as one of the external orchestrators. We know that in this container world, that something more meaningful is if we want to classify the workload is instead of using the IP addresses, use their services name or the name port or data port or port names. These are the names that we want to fetch from the other worlds, and so that we will be able to see that the capability of the signify them. So then with service endpoint as an example, we can be able to, by having this kind of annotation integration, we can be able to know the actual, at this point in time, the IP address, because we still need the IP address to where about. It will reside somewhere with an IP address and MAC address. Only that we need to recognize the fact that it keeps changing. So instead of catching them with the IP address, we try to classify them with the names that we quite sure that is using a service endpoint in this case. So as a result, we can build many of these kind of annotations or classification that you can say it, be it using the namespace, port, service, different service name as an example. With that, we will be able to do what we can to mix and match different workloads from the brownfield world to the greenfield world. Because no matter where you're residing, I'm not using hiding, you're residing because there's a legitimate workload. But we know that where you are, we know where we can find you, and we know where the point that we can put the policy enforcement point, or as the policy enforcement point, with the policies that we want to, be it a single port access. So this is all from the examples that we have encountered before about the workloads. As an examples to illustrate how we can reach out to somewhere that so morphic or so evolving the parameters in the upcoming future. But I also want to talk about how we can extend this to even further, not just only confined to workloads, although I don't have too much time to talk about the workplace and workforce today. But there is one thing that is examples to talk about how can we expand to a much wider scope with a context data exchange platform. From Cisco, we have a platform exchange platform called PXGrid. So basically, it try to fit the scenarios. There's many different kinds of scenarios, but one of the scenarios I try to illustrate today is, say for example, I have a device. It could be I have a device. I want to enable this device into this zero trust architecture. So how could I do that is, I need to publish this device. I need some mechanisms to publish, to let other people know that what this device is capable of providing. For example, what are the information I'm going to publish outside, and also what kind of information I can consume. Or it could be I could be a person, or I could be a person with a device, or could I be a mobility device manager that I want to participate in this the zero trust the capability. But they're from different angles. You're still using the same platform. We call it PX Grid here. So I just try to integrate with a device, but you can think about, if I have an application, I want this application to provide this, to participate in this zero trust. How could I be able to do that? You also go through this identity participations through the PX Grid Exchange platform. So basically, what it does is it's a publish and subscribe model. So basically, it's a bidirectional, of course. So you can say, for example, if I have a device provided by an ecosystem partner, I can publish it as with some attributes to describe what this device is capable of. Similarly, you can apply a vinyl application. You can also do that. So this attribute after publish will form the profiles as a baseline, and these profiles will be, because it's going to be recognized by our. If you go back to a previous slide, you see that we have an identity. I didn't talk much about the platform. We need a identity service engine that intake this attributes and in the form of XML. XML is a very universal language that you can describe your devices, your capability. And after you inject into it, it will build up the profile based on this device, for this device. And it will be the starting point that we can be able to turn this into ultimately the policy enforcement point. But before that, we need to establish an exact profile. So you may have many devices, but they can be classified as a group. It's very typical that a certain device may have a different models, and model 1 and model 2, but they are actually sharing the same asset profile. So you can make use of these profile concepts to build a profile around, to wrap around your device. And then with that profiles, with that, you can build a policy based on the policy engine, because the policy platform will inject into the profiles. We understand what this device is capable of doing and what kind of service they will provide and they will consume. And then ultimately with that, we will be able to build the policy enforcement that this device needed. And so that when this device is being consumed by other ends of be it the application services on the far end of the data center or on your campus network, we will be able to authenticate along the path so that the device will not, we will be able to consume the way that it should be. And also it will also be providing the services that it meant to be. Because ultimately we want to, in this era of IoT, we don't want the introduction of devices, intelligent devices, to cause any compromise of your securities. So with that, that wraps up my presentation today. And we do have, if for your interest, if you have would like to know more, we do have all the information on our developed DevNet networks, and so I posted here for your reference. We have also particular zero trust white papers, and for the particular the platform exchange grid that I'll talk about briefly, we will also have our white papers in there. So with that, I pass the floor back to Chen.
Okay, that's thank Philip for the great talk. So question time. So here's a question from an audience. Let me ask: does this system okay, hold on. Let me see. More questions. All right. Does this system require special hardware? Are there any performance degradation compared to traditional methods such as VPNs?
Okay, the enablement of the zero trust depends on the different scenarios. I talk about the workplace, workforce, and the workload. In each of this specific scenario, there will be we use different approach. Say, for example, in the workload environment that I mentioned about, there will be a policy engine, because if you recall the policy, the map that I talk about, we need to have a zero trust engines to provision the policies and to gather those the actual data flow from the workloads. So these kind of informations will be stored in that central appliance, but they will act as a central control plane. So during the enforcement, it will leverage the original source of the workload. Could it be the server, the VM, or the container host, where we will leverage the industry standard, like let's say if it is Linux, it will be IP tables. It will be if it is Windows, it will be Windows Firewall to do the enforcement for us. Or if you opt not to install those agents to do the enforcement on the host itself, you can do the enforcement on the network. And then there are many enforcement network out there who can take the policy enforcement. So in simple words, the answer depends on the scenario. We will have different policy engine on the control plane that we require. But if the enforcement itself is on the host itself or on the switch or router, well, that will depend on the particular implementations. But normally nowadays, many of these are on the ASIC base, so we don't actually see much ongoing enforcement penalty on the host on itself. And besides, when we, in particular for our agents will have throttle control on the CPU bound. So remember we are talking about the continuous monitoring of this flow from the enforcement point. Many customers worry about that. Will this kind of feeding of data will diminish or reduce my CPU? That's why we also introduced these throttle controls to limit the agent's consumptions on the host. I hope I answered the question, Chen.
Okay, yeah. So here's a very long question from Jiwon Lee. So how about I just unmute you, Jiwon? Can you like direct talk to Philip? That would be more efficient. Okay. I just unmute you. Okay, talk. Jiwon Lee. Okay.
I think, Chen, I think it's okay. I can answer it. I think I get the point. Yeah. I think that's a very good question. So the question is actually like, if the policy is too loose, how can we detect the suspicious activities? That's why in the normal zero trust practice, before we do the real enforcements, migrate to the zero trust or micro-segmentation, before we do the actual enforcement, we will do, from the customer experience, we actually do a very long period of monitoring of the how the actual flow in the, take workload as an example. We take a monitoring period quite long. We sometimes even ask customers to try to simulate during this policy establishment their month-end processing, their quarter-end processing, their year-end processing. The reason why is we don't want to meet something that are legitimate, as what you pointed out. Either it's too loose or too strict. And that's why before we do the full-scale enforcement, we will do a monitoring. And also that's why, if you remember in my previous sharings on that workload, I emphasize one point that we do simulations. Because simulation is the way that we simulate the policy against the historical data. So that we know that if we don't drop some legitimate flow and cause interruption to the business. Back to you, Chen.
Oh, okay, great. So yeah, so here, David, can you ask a question? Yeah, your turn.
As I chat, in order to provide powerful zero trust, Cisco collects useful private information about the users, such as data in the PIP. So what I want to question is that from the user's point of view, a user could be concerned that his data may be leaked. So is there any protection mechanism for such private data beyond the encryption?
Oh, okay. So quick questions. Let me clarify a bit. Maybe there are some misunderstanding here. For the workload that I talk about, the flow information that we collect is actually the actual flow header without collect any payload data. So say, for example, many of the customers' data, they carry the actual data payload. Those kind of information will not be collected. We only capture the TCP header information. So it's only the source and destination IP address. That kind of information we will collect this. So so for the same, that's why in some case, some customer ask if we can tell whether the TRS version 1 or version 4, like what they did today with the layer 4, layer 7. We don't do that because we never look into the payloads. We only look at the header informations.
Chen, you had to ask a question.
Okay, so Philip, so can you hear me? Can you hear me?
Yeah, I can hear you, Chen.
Oh, okay.
Yeah.
Okay. Very nice talk. So it's quite good solution that by removing the central trust, engine and put into the trust enforcement at the endpoints. So my question is, okay, can you compare with the permissioned blockchain system, like Hyperledger? Yeah.
Oh, okay. The Hyperledger is a blockchain system. So basically, it's a container implementations of the blockchain. The solutions that we talk about here is more for generic workload protections, be it the workload is a container, be it the workload is a virtual machines, or be it the workload is a virtual bare metal servers. So it can also be a container platform like Kubernetes. It has its own network policies protections. Like say, for example, blockchain, also the implementation itself under Hyperledger, it has its own policy implement in between to protect. You can view what we try to protect is on the underneath layers, because all these endpoints, be it a blockchain instance, a Hyperledger instance, it is still an implementation of a containers. What we try to do at the layer is underneath this network connection of these containers, or the virtual machines, or the physical servers, how we can protect further in that network segments. There's nothing to do with the application policies within your application system. So be it a blockchain or Hyperledger instance, or be it OpenShift or Kubernetes, you still have your protection inside. It's just like you can imagine it's another layer on the network layer that provide this kind of protections.
Okay.
I hope I answered your questions.
Yeah, thank you.
Thank you.
Yep.
Any more questions? Okay, I have a last quick question. Does your solution, this zero trust framework, also protect the data privacy?
Data privacy. I think from the point is we don't touch on the data content itself. So you can still in your network you still carry your encrypted traffic, right? As I said, like the workload, we don't look into we don't even look into your the payload. So I think the data privacy is we protect like the door lock to control the whether you can access to this door, but whether you open it, whether inside the content is encrypted or not, we don't know. So, from the protection of it, we protect the access, still on the access because we're from the network access point of view.
Okay.
I hope I answer your questions.
Yeah, great talk. So, any more question? If no more question, let's thanks Philip again. Okay, thank you.
Thank you.
Yeah, so let's switch the speaker. So our last speaker, let me see. Our last speaker is from NVIDIA Manlox, is Gilad Shanner. Gilad is a, so can you share your screen?
I wish I could, but the previous presenter is still presenting, so I cannot.
Oh, yeah. Philip, can you stop sharing?
Oh, thank you.
Okay. So Gilad is a senior vice president of the marketing for Manlox networking at NVIDIA. Now it's NVIDIA, right? Focusing on high performance computing, artificial intelligence, and the InfiniBand technology. Today he will talk about InfiniBand. And he has been with Menelux for nearly 20 years, okay, as a designer, engineer, and later served as a senior marketing and management, since 2005. And he is the chairman of the HPC AI Advisory Council organization. And today he will be talking about the InfiniBand in network computing technology and the roadmap. So Garrett, please go ahead.
Thank you very much. So yes, I'm Gilad, been with Mellanox almost from the beginning of Mellanox. Mellanox is a company that design and manufacture and sells networking solutions based on the two leading standards for data center connectivity. One of them is InfiniBand, and the second one is Ethernet. Early this year, Mellanox was acquired by NVIDIA, and now we are part of the NVIDIA networking business unit. In my discussion or in my talk, I'm going to focus on the InfiniBand network, not the Ethernet side or not the Ethernet network. And I'm going to focus about the elements that InfiniBand enables as part of making the network a first-class citizen in the job runtime. And you will see the examples what I'm referring to. So first, I wanted to kind of put the environment in place, and we're talking about the new scientific computing world, which covers multiple aspects, essentially. In the past, when we talk about scientific computing or simulations, we talked about supercomputers. Large data centers include multiple of compute elements. All of them are connected together. And you need to have a very low latency network, a very high throughput network that can connect all of the computing elements together in order to form one large supercomputer that can run complex simulations or can be used for other data or compute intensive applications. The infrastructure of the scientific computing world actually being extended nowadays to go into more and more areas and more places. Today, when we're looking on an infrastructure, we're covering everything from edge computing through the supercomputer for doing analysis, for appliances that can participate in compute elements, and obviously storage. And you have a network, or you need to have a network that can connect everything together. And in every area, you can actually run compute. So today, when you look on edge computing, you start doing analysis at the edge because you cannot move a greater amount of data to a data center, to a supercomputer to analyze that. And you need to start analyzing at the edge. So you have smart edge computing, and then you move the necessary information. That necessary information will go to the storage, will go then to the supercomputer, and then will go to the appliance. The network is the heart of everything in the middle. And when you look on that, the network needs obviously to enable a very high throughput, reliable, and secured data motion. So to be able to move data from all of the areas, it needs to be very low latency, obviously. And then if we want to get to the next level of capabilities, you actually need to bring or to enable also compute engines on the network. And I'll show you what I mean. So first, a little bit about InfiniBand. InfiniBand today provides a end-to-end server-to-server connectivity of 200 gigabit per second, or server to storage. We have 200 gigabit per second InfiniBand networks in production for 2 years, which connecting the world-leading cloud infrastructures or AI infrastructures or high-performance computing infrastructures all around the world. If it's for research, if it's for oil and gas simulations or automotive simulations, weather simulations, and so forth. NVIDIA built probably the fastest industrial system in the US, which combines a lot of GPUs, all of them connected with the 200 gigabit per second InfiniBand, which is the number 7 on the top 500 supercomputers list that was just released last month. Microsoft, for example, have lots of InfiniBand networking in Azure to enable high performance computing in the cloud. People that wants to be able to run complex simulations or to achieve much better throughput for different kind of jobs can choose to use the InfiniBand connected Azure instances and be able to leverage from 200 gigabit per second at extremely low latency for their jobs. And we're seeing InfiniBand going into more and more large cloud infrastructures, web services, and obviously empowering the largest supercomputers of the world. Now, why InfiniBand has been growing that fast, and why InfiniBand has become the de facto networking for high performance computing, why it's becoming the de facto for AI today, and why we see more and more hyperscale environments starting to adopt InfiniBand, relies on the basic elements, on the fundamentals of InfiniBand that enables to bring lots of innovations into the network. The main fundamentals of InfiniBand are 4. The first one is building a very, very smart endpoint. You have an endpoint or network adapter that sits very close to the CPU memory, very close to the GPU memory. And with that, you can do very interesting things on the memory, on the application memory. That would yield RDMA to be able to move data directly to the user space or the host memory, or GPU direct RDMA, which does the same thing for GPU memory. InfiniBand is a full transport offload network, full transport offload, not stateless offload, not partially offload, it's full transport offload. All of the network functions are running on the network, not on the CPU, not on any other compute element, which means that you can maximize the efficiency of the CPU or GPU and have more cycles that can be dedicated for the actual workloads. The second fundamental is that the switch network was designed to be able to scale. And not just that, it was designed to be very simple, extremely simple. You can take the same switch building block and use it everywhere. There is no sense of top of rack, aggregation switch, and so forth. There is one building block that can use for everywhere, and you can build any size of infrastructures together. And then you can bring a lot of innovations into that, and you can bring compute elements into the network and other things of that sort. InfiniBand was also born as a pure SDN fabric before people knew what SDN is, which means that you can control the entire routing. InfiniBand enables not just congestion control, but also a fine-grained adaptive routing. So increase the efficiency of the network almost to 100%. You can manage all of the routing from a center of place. You can look on everything that happens on a network, and you can manage that in a very, very simple way. And of course, InfiniBand is a full standard. The standardization is being managed by the InfiniBand Trend Association that continue to release more and more capabilities and obviously drive the next generations of InfiniBand. Some of the key things, by the way, around InfiniBand, and I'll touch some of those. First is speed of light. InfiniBand is the first network that closed an end-to-end loop of higher and higher bandwidth speeds. It was the first one to close the 100 gigabit per second end-to-end, the first one to close the 200 gigabit per second end-to-end. And we'll see it's also closing the 400 gigabit per second end-to-end in the near future, and so forth. It has native RDMA capabilities, and it's 3x faster than anything that exists or anything that will exist out there. So for latency sensitive applications, InfiniBand is probably the best option. The other key element of InfiniBand is what's called SHARP, or Sharp AI technology. SHARP is actually covers compute engines that sits inside of the network silicon devices on the InfiniBand. And those compute engines that sits inside of the silicon devices of the network, inside of the data path, can do data manipulations, can do data calculations on the data as it moves. Unlike any other network, the switch fabric look on the incoming data and then figure out where it needs to go. On the InfiniBand world, you have compute engines that sits inside of the data path that can actually do data analytics, okay, do data calculations. And with that, the network, or the InfiniBand network, has become a distributed CPU. Not just moving data from one side to another side, but actually actively participate in the application runtime. Another element of InfiniBand is called Shield, which is leveraging the compute engines that sits inside of the silicon devices to increase the resiliency of the fabric. Not just to detect errors and report errors, but actually to be able to overcome errors by creating a smart and targeted communications between switch elements. So remote switches within the data centers can get information about issues that happen in other places, so they can actually modify or optimize their routing schemes in order to bypass or overcome failures within the network. And the last part is the management elements of InfiniBand. You can manage InfiniBand the same way that you manage Ethernet or vice versa. But InfiniBand also bring other capabilities of management with very rich telemetry information, combining that with deep learning algorithms to be able to bring predictive maintenance and security into the data center. So one of the things that InfiniBand enables, it's actually the migration of the data center from being a very CPU-centric data center, which means you need to move data all the way to a CPU, or you need to move the data all the way to the GPU before you can do something on the data, which is becoming a performance bottleneck, definitely when you have larger and larger amounts that you want to analyze. To the data-centric approach, or to the data-centric data center. And in the new approach, the idea is that you want to stop moving data to the compute, you want to move compute to the data. And moving compute to the data means that you want to enable compute everywhere, including in the network. And that's one of the key innovations that InfiniBand provides. Now, there's a lot of elements, a lot of innovations in the different elements of the network, and I'm definitely not going to be able to cover them all. But just to give you a little bit of taste, InfiniBand as being a pure SDN fabric, enables to build any sort of topology that you want. It could be factories, it could be dragonflies, it could be hypercubes, it could be toruses, it could be meshes, it could be anything that you want. You can optimize the data center topology to the application, to the cost criteria, to future expansions and other things of that sort. On the other side, because InfiniBand is pure software-defined fabric, the InfiniBand switch network is more cost-effective than Ethernet, for example. When you buy an Ethernet switch, every Ethernet switch comes with a server inside the box that runs the network operating system of that switch because of all the algorithms that you need to manage. InfiniBand does not carry a server inside of the box. It's not needed. And now you get a much more cost-effective network infrastructure. So that's on that level. When you go up the levels of the network, there is a lot of advantages from congestion control and adaptive routing and quality of services, self-healing capabilities inside of the network, and then all of the way to compute engines that sits inside of the data path to do data arithmetics on the data, to be able to participate in the job runtime. There is accelerations for NVMe fabrics. There is accelerations for putting containers on top of the network. And then there is actually engines that enable to accelerate all the way to the application side. I wanted to show you a couple of things related to the capabilities of the network. And the first one I wanted to show you is SHARP. SHARP stands for Scalable Hierarchical Aggregation and Reduction Protocol. And SHARP is the name for the technology that enables to do data aggregations or data reductions in the network itself. And that's being done by using compute engines that sits within the data path, or it sits on the data path in every switch, that can do all of the data arithmetics of integer and floating points. And those engines look on the data that goes within the network packets, looks on the data portion, and then they can do different data manipulations on the data. One of the things that we're using those engines for is to do data reduction or data aggregations. And that's critical for high performance computing, that's critical for deep learning, and that's critical for any other multi-process applications. And when you're running a multi-process applications, you split a problem into multiple pieces. You give each piece to a different core or different CPU to calculate, and then you need to aggregate the result into a single answer and repeat that over and over and over and over again. Now, you can do the aggregation on the CPU, which will take you a lot of time, and that times will increase with your system size. And that will increase the amount of data that you need to drive within a network. So that's one way, which is the wrong way. Or you can do the reduction on the network, which enables you to run things much faster, in full parallel, much more immune to the system size, and then reduce the data motion. And the way that it works is that the switches will be actually the entities that receive the data from all of the hosts. We'll do the data aggregation. We'll send it to the next level of switches, which will do the data aggregation between the switches. And then actually the switch will do the broadcast back of the result all the way to the hosts. So what do we get from that? So here a couple of examples. This is looking on MPI, message passing interface, and looking on the all reduce algorithms, all reduce operation, the data all reduce operation, which is doing the data reductions. On the left side, we're looking on a small scale of a data center from 2 servers all the way to 128 servers, and then running the reduction operation, the data aggregation operation of MPI. Doing that on 8 bytes or 128 bytes messages, or 1 kilobyte or 2 kilobyte messages. The dashed line is the latency when you're running the reduction operations on the software or on the CPU. And the solid line is when you're running the reduction operations on the network itself using the compute on the network. And what you get on the network is flat latencies. So if you do data aggregation, data reductions on a CPU, the more nodes you have, the more processes you have, the more cores you have, latency goes up. You run it on a network, you pretty much get flat latencies. On the right side, it's looking on the comparisons for a data center that has 1,500 nodes with 40 processes per node or 40 cores per node. So running 60,000 processors together. And the difference in latencies between running that operation on a CPU and then the network just move data to where the network does the reduction operation, the network does the compute, the difference in latencies is 7x. Here's a comparison between InfiniBand and Rocky. And Rocky, it's the Ethernet technology that has RDMA that actually bring low latency into Ethernet. On the left side, we're looking at small messages. InfiniBand, just InfiniBand, simple InfiniBand compares to Ethernet, that's around 2x of performance improvement, almost 2x for the behalf of InfiniBand. And then when you run InfiniBand with Sharp, which only exists on InfiniBand, you have 4x performance difference, 4x. On the right side, this is looking on large messages where it's still InfiniBand is faster than Ethernet, Rocky in a small gap. But then again, with comparing Rocky to InfiniBand with Sharp, you get more than 4x performance difference. And then when we look on AI or deep learning, in deep learning, the most important operation is data reduction. The most important operation when you're running a deep learning on the network, it's data reductions. And here, as you can see, the performance increase of running a 1000 GPUs, the latest Ampere A100 GPUs on InfiniBand, and then comparing the performance of InfiniBand versus InfiniBand plus Sharp. And then Sharp gives around 2.5x performance boost for deep learning operations. And from those reasons, we're seeing the InfiniBand increase adoption in AI, and InfiniBand is becoming the de facto connectivity for AI. Microsoft already implemented 200 gigabit per second InfiniBand for data and compute intensive applications, for AI applications in Azure. NVIDIA has built one of the largest supercomputer for deep learning that is based on HDR. And then there's many more. So I included one example from of Continental, that there was a press announcement last week, I think, about them using InfiniBand for the autonomous vehicle development. And then ACE, it's an example for one of the large AI cloud data centers that was built in Japan based on InfiniBand. So that was one part. Now, if I do have compute engines on a network, I can use them not just for computing processes or not just for participating in the application runtime. I can also use them for resiliency. And this is what we did with Shield. Shield is a name of a technology that enables self-healing capabilities within the network. And the motivation around Shield is to have the network not just detect failures and then provides notification to a software management that will come and do something, but actually to be able to overcome that on a network level. And the reason is that if you're waiting for a software management to come and do something, it will take you a long time. It can take you a second, it can take you 5 seconds. And that means is that for that time, you are dropping data. And if you have latency sensitive applications and you're dropping data for 1 second, you're gonna crash those applications. And we wanted to solve that problem and created a technology that called Shield. And the way that Shield works, I can show you in a simple illustration. Let's say that we have a data center, and data center has 3 levels of factory from a topology perspective, and we're moving data from one side to another side, and everything is nice and happy. One thing that may happen is that you can have an issue in one of the upgoing links when you go up the tree. This is a very simple case because once a switch detects that there is a failure in one of the links, it obviously can move the data to another link, do rerouting by itself, and just use another path. The more interesting case is when you have a link issue when you go down the tree. Now, in a factory topology, when you go down the tree, unless you have built a high availability within the network, there is only one path you can choose. And that means that once the data arrives to that link or link that has issues, it will be discarded. And if you're going to discard data here for a second or for a few seconds, the application that is waiting for the data is going to crash. And this is not something that you want to do. So in this case, when switches detect failures, switches will create notifications. very dedicated notifications. They're not sending a storm of information to everywhere, but they're creating a very dedicated information that goes to very specific switches and asking those switches to eliminate routes that may drive the data to reach the failing link. In this case, the switch that will get a notification is the switch here, and that switch will do the rerouting. And by doing rerouting, the data will go to another path. Now, shield becomes also very important when you are running adaptive routing, because when you're doing adaptive routing is a local switch decision. Every local switch looks on the outgoing ports. It looks on which one of the outgoing ports is the least busiest one, or take a group of the least busiest ones, and then send the data to that least busiest group. Now, if you have a link failure and you're dropping data because of that, that will probably become the least busiest port in some other switch in the fabric, because the path is completely empty. So link failures can become black holes for adaptive routing. And by using shield eliminate choosing routes that may cause issues in switches around the fabric. And by combining shield and adaptive routing, you can completely eliminate those black holes for adaptive routing. So a little bit about InfiniBand. InfiniBand, or the end-to-end solution for InfiniBand today includes, from the NVIDIA side, the Mellanox Connect X6 adapters. Those are host adapters that support 200 gigabit per second with PCI Express Gen 3 and PCI Express Gen 4. And 200 gigabit per second switches that support 40 ports of 200 or 80 ports of 100 or any mix in between, including modular switches that goes to 800 ports of 200 gigabit per second. Bluefield is a smart NIC based on Connect X6, and Bluefield 2 takes Connect X6, combine that with multiple cores of ARM, a DDR4 channels to put memory on the NIC, and provide a programmable NIC. So the Connect X6 adapters has compute capabilities for data analysis. The Mellanox switches, the InfiniBand switches, have compute capabilities to process data. And then Bluefield 2 adds ARM cores on it. So now it's programmable devices, which means you can run Linux directly on the network devices and run your own algorithm much closer to the data. There is a gateway, by the way, from InfiniBand to Ethernet. So if someone is building InfiniBand data center for compute and data intensive applications, for running an AI, and one of the key advantages as well of InfiniBand is being more cost effective than Ethernet, for example. You can simply connect the InfiniBand data center to the Ethernet side. And there is a gateway that has, each box has 8 ports of 100 or 200 gigabit per second InfiniBand on one side, 8 ports of 100 or 200 gigabit per second Ethernet on the other side. And it's doing the gateway between side or migration between InfiniBand to Ethernet, from Ethernet to InfiniBand in a 200 nanosecond latency. And there is also a box that enables to extend InfiniBand reach to up to 40 kilometers apart. So you can have a native InfiniBand between 2 InfiniBand data centers, between InfiniBand and a remote storage. You can put data in a remote location for disaster recovery and so forth, and enjoy all of the InfiniBand semantics using that box. There are also boxes from a company named Vicinity.io. And Vicinity.io enables to extend InfiniBand reach to thousands of miles. So you can actually connect InfiniBand data centers across continents and run native InfiniBand between sites for high throughput, for RDMA, and for all other things that I mentioned. And the last part is the management element. InfiniBand management provided very rich capabilities of telemetry, and monitoring. And the management utilities enables obviously to do orchestrations and connect to the job schedulers and to apply SLAs, check the health of the devices, looks on the congestions and other maps of the network and so forth. The recent management appliances of InfiniBand also brought deep learning algorithms into managing of the data centers. And by combining deep learning and telemetry or rich telemetry, you can enable predictive maintenance. Not just predictive maintenance, but also security, bringing cybersecurity and anomaly detection into the data centers. There are 3 different appliances for management of InfiniBand data center. Obviously, you can connect the telemetry information and run it to the tools that you are using within the data center already. But if not, you can use those tools as well. The recent elements that we've done on combining telemetry and deep learning enable us to do interesting things. So the appliance, the newest appliance, it's called UFM Cyber AI that you see on the right side. It's connecting to the data center and reads a very rich telemetry from the adapters, the cables, the switches, the transceivers, everything that you have there on the network. And it builds a database, historical database of a telemetry information. And on that database, it applies the deep learning algorithms that it has. And with that, it can do, or it can find performance degradations in a very, very early stages of those. And then using past information, it can gives a prediction, a very accurate prediction of potential failures in the future based on reading of performance degradations over time and apply that to deep learning knowledge or history knowledge from their data centers and other data centers. So you can get a prediction, a very accurate predictions of potential failures in the future, which means you can set a maintenance period instead of waiting for a component to fail. And by also doing correlations between events, you can get better understanding of why things happen. What may cause some issues that may happen, even though previously those issues were more seen as a random issues. The other part of the UFM Cyber AI is the ability to build a network footprint based on the workloads that are running. So it learns the fingerprint of the workloads. It learns the communication patterns of the workloads. And in that sense, if someone is running an application that is not supposed to run there, and that application has a different footprint on the network, you can get an alert of abnormal system behavior, which means someone may be using the system for a not approved usage. And with that, you can go and check it out. So overall, if you look on the InfiniBand side, you have 200 gigabit per second to the end-to-end, extremely low latency, extremely low latency. The switch latencies of InfiniBand is in the range of 100 nanosecond. The adapter of InfiniBand is a range of 150 nanosecond. It's nothing yet close to that. And then you have the computing engines that sits within the network devices, which do not increase latencies, but they are able to provide computing capabilities, which meaning the network is becoming a distributed CPU. Within the data center, there is other resiliency element in adaptive routing and congestion control and quality of servers and the rest of the elements. And obviously gateways to be able to connect from InfiniBand to Ethernet and from Ethernet to InfiniBand. So I hope that you got a little bit of the feeling of what the next generations of network provides, and definitely what InfiniBand provides today. And the network is no longer a medium that just moves data. The network has become an active part in any job runtime, same as a GPU, same as a CPU. Thank you very much.
Thank you. Questions from our audience? Okay. We mute one. Chen Chen, you can talk.
Okay. Hello. My voice is clear.
Yes.
Okay.
Yes.
Yeah. Thank you for a very interesting talk. Besides the SmartNIC, there are quite a lot of applications now there to offload the computing. So can you give some advice? What kind of application would be more properly located in the middle of the network? For example, the switching fabric. So it may be more straightforward to have the stateless, applications, but how is the stateful application? Where maybe some of the packet like the TCP reassemble might be needed.
Okay, so we need to separate, I think, the two things. First, you have the network transport, right? If you're talking about TCP or we're talking about RDMA and things of that sort. In the InfiniBand world, the entire network transport runs on the network itself. So it not runs on the CPU, for example, and that gives a good advantage. Now, from an application perspective, there are two kinds of computing engines on the network, which sits on switches inside of the switch silicon or sits inside of the NIC. There are computing engines that were created for very specific algorithms. And I'll talk about some of those. And there are computing engines that are completely programmable, such as ARM cores that sit inside of the data path, that actually gives the ability for application folks to move their pre-processing of information and run that on the network, or to move the control path of application and run them on the network. So now you can actually increase the speed of analysis. You can do pre-processing of information, and according to the pre-processing, to decide to which CPU that data needs to go through. I may need to drive it back to the network and send it to another place that it needs to be analyzed, and not in the data where it was arrived. So you can do interesting things. The dedicated engines that we have brought into are mainly to move communication frameworks from the host to the network. And the communication frameworks that we're looking at right now are covering communication frameworks that are being used in high performance computing, such as message passing interface, or MPI, or SHMEM-PGAS, or UPC, and communication framework that are using for deep learning, such as NICL, for example, or others of those. And the reason that we're moving those communication frameworks from the host or from the CPU or GPU to run on the network is to reduce latencies dramatically or to increase the throughput dramatically. So this is what we're focusing on. Obviously, because you have programmable engines within the network, you can look on other pre-processing or other control path of workloads that you want to move to the network. And by moving them to the network, you can run things in parallel. And one of the key things to remember is that the network has much more parallelism than on the server side. Every switch, every compute that I do on the switch can cover multiple servers that are connected to that, and I can do it in parallel. And having two switch tiers or three switch tiers in a data centers, I can connect hundreds or thousands of endpoints together, and I can do operations in just 3 tiers of switches. So I think we're just at the scratching the edge of what we can do with computing on the network. You can think about other things such as security. We are moving security to the network. And the reason for that is that the main security issues of today's are because you're running the security domain on the same place you run the application domain. And if someone got access to that domain, he can get access as a guest OS, and he can get access to the memory. That's why most of the security issues are because of. Now, if you're doing security on the network, if you're moving the encryptions, decryptions, and run them on the network is a trusted domain. I can encrypt the data on the network. The data arrives to the memory already encrypted. Any intruder, any malicious user that got access to a guest machine and trying to get access to the system cannot touch the data because it's already encrypted. So there's a lot of things, not just the applications, but you have also security and many other capabilities that computing on the network enables you to do.
Yeah, really comprehensive answer. So here I relay a question from an audience. He asked when the multiple group of nodes are working on simultaneously use SHARP, okay, the first system you introduced. I think the data is concentrated at the several switches according to a network topology because of tree-based approach. So how do you handle this congestion problem?
It's actually reducing the congestion problem, because when you have nodes that needs to do data reductions between them, what happened without SHARP is that all of the nodes will send data to one specific nodes from that group. That node will need to do the data aggregation, and then that node will need to send back to those nodes. So you actually have a lot of data that goes between that group of nodes. If you do the data reductions in the switches, the switch does the data reduction. So now the data that moves within the network is much less comparing to if you were doing the reductions on the nodes. And then I also do the data broadcast back from the switches back to the nodes. So I'm saving a lot of data that needs to go from multiple nodes to a single nodes and back by actually doing the operation on the network. So I'm actually reducing the congestion. This is one of the benefits of SHARP, not just reducing latencies dramatically, but I'm also reducing data motion. So I'm also reducing the congestion on the fabric.
Okay, Dan has a question, so go ahead.
Yeah, I also have a question about the SHARP. So if you make the reduction operation in switches, so can it seamlessly work with modern deep learning software frameworks such as TensorFlow or PyTorch? And another problem is that how to debug if there is some algorithm, if we want to do some algorithm details. Yeah.
No, it's a good question. So the second part is that same as you're running compute on the CPU, you can run compute on the network. There is Open API that you can run on the compute on the network, same as you run on the compute on the CPU. And you get the full information of all, you can, let's put it like that, you can completely debug that. You can see nodes, you can know exactly what stage, what happened in which stage, let's put it like that. And with that, you can do full debug of the algorithm, the same as you do debug on running the same algorithm on the CPU. And you can repeat the same process again and again and again, and you can get the same result. So you can debug that the same way that you debug application runs on the CPU in a very simple way. Regarding the first question, any AI framework you will touch, take TensorFlow for example. You know, you can run ResNet 50 or whatever. You run an application on top of TensorFlow. TensorFlow runs on top of a framework that does the data reductions for deep learning. If you're using NVIDIA, there is a library that's called NCCL, NCCL. If you're running on top of AMD GPUs, they have their own, I forgot the name, sorry for that. They have their own library that does the data reductions. Any company, some companies creating their own. But any AI frameworks runs on top of data aggregations. The data aggregation runs on the network. So for Nickel, for example, Nickel is already incorporated Sharp into Nickel. Other GPU vendors, I believe, also integrated Sharp into their frameworks, their software. So that's why it runs automatically on that and average that, and nothing you need to do from the application perspective, for example. So that's how you use it. People that writes their own, by the way, and there are people that writes their own frameworks, their own software. They can easily take advantage of Sharp, just run it or connect it to the API, or use the API for the network instead of the API on the CPU, and you can use the compute on the network for that.
Okay, thank you for your answer. I just want to confirm that you already integrate Sharp into Nickel, right?
Correct.
That's for
Correct.
Ethernet, right? How about Ethernet?
There is no Sharp for Ethernet.
Okay.
There's no Sharp for Ethernet. The main reason is that one of the main differences between InfiniBand and Ethernet is the complexity. Ethernet has many algorithms that you need to deal with on the network level. And some of the previous discussion covered that, from BGP to whatever. There is a lot of algorithms that you need to deal with. And that's why you put a CPU model in every switch box that you send in order to run the operating system of the switch. InfiniBand is not like that. InfiniBand is a pure SDN. It doesn't have issues of flag, doesn't have issues of spanning tree, doesn't have issue of anything. You connect multiple ports together, boom, they work together. You don't need to do something special. And because of its simplicity, it's easy to put more elements on the network. It's easy to put Sharp on the network on the switch and be able to run it in the same latency and without any imposing of further complexity. If you try to do something similar like that on an Ethernet switch, it will be very, very, very complicated.
Okay, thank you very much for sharing the information.
Sure.
And any other questions? Okay, I actually have a question. I remember in your page 11, so you have like bar is performance comparison. So you said InfiniBand with Sharp has around like 4 times performance improvement compared to InfiniBand and Rocky, right? So in that one. So I want to know a few more details about the experiment setup of this, and what are the application you are using. I assume use AI, like training or AI. So can you say a few more about how you can get like this 4 times performance improvement with Sharp?
Yeah, this is simple. So this is actually running MPI or reduce operation. In MPI or message passing interface in the HPC world typically use MPI as a communication framework, and then MPI has several multi-process communication algorithms. It has barrier, broadcast, reduce, gather, and so forth. The operation that's called or reduce, that's the one that does the data aggregation among multiple processes. So the benchmark that you see here, it's actually just running MPI or reduce. It's running the reduction operation of MPI on top of a cluster, and then cluster connected with Ethernet network or with RDMA over Ethernet with Rocky. The same cluster is connected with InfiniBand. So you run MPI or reduce operation on the Ethernet network, and then you measure the latencies. You run it the same on the InfiniBand network, the same cluster, and then you get the latency over InfiniBand. And then you can turn on Sharp with InfiniBand, which typically it's default on, but here we turn it off and turn it on. And when you run Sharp with InfiniBand, now the reduction operation is not running on the CPU, but actually moves to be run on the network. And now you measure latencies and you get 4x lower latencies.
Right. So my understanding is that the Sharp, for example, the bar, the graph, the figure on the right side. So basically, it's a Sharp, like in-network aggregation or something operation that take effect to achieve like 4 times the performance improvement, right? So what is the upper layer application of this experiment?
No, so this is running MPI. The application is MPI. We're running MPI. Who's the target of that? The application that runs on top of MPI, those are typically scientific simulations, meaning oil and gas reservoir modeling. If you're asking what application that runs on top of that, it will see the 4x performance improvement. From MPI perspective, those are oil and gas reservoir modeling, automotive simulations, weather predictions, bioscience simulations, anything that simulates movement in a sense, or everything that falls under high performance computing. The other elements that falls underneath is deep learning, because deep learning also uses data aggregations. So also deep learning is the reason that you see the large systems from NVIDIA, the superpods, the DGX boxes coming out, they're coming out with InfiniBand. Because with InfiniBand, you can dramatically improve the performance. Obviously, if someone wants to connect it to Ethernet, they can. But then they're going to lose a lot of performance. So the target applications here, the application that runs on top of that, those are AI applications or deep learning applications. Then everything that falls under high performance computing, which means any simulation based of any multi-process simulation base, essentially.
Right. So yeah, maybe my last question is for audience. So I ask for audience for like a question to you. So basically, many of the most of the audience are students that want to do research. So can a student do research with InfiniBand while still can do experiment with this? So that's you introduce like a lot of good things, especially the low latency with InfiniBand, right? So, but I think most students are still struggling, right? That if they do research on this, how can they do experiment with this?
So I think the InfiniBand gives or enables very interesting research areas, because typically when you look on research, you build a system, you have the network, you can have the algorithms of how you move data, what kind of topology that you want to build. InfiniBand gives you more than that. InfiniBand gives you compute on the network.
Yeah.
So with that, there is several areas of research. One research is on the application space, meaning I can take applications and break part of the application and run that application on the compute on the network. By the way, it's not just compute on the network, you also have memory on the network. I didn't talk about that. There is memory on the network that is accessible by the application. And the reason that I have memory on the network, it's for putting common information. And the simple example for common information is semaphores. Semaphore is an entity that you want to catch in order to take ownership of a resource. And today you put semaphores on the host memory. So all the processes needs to go over the network to one node to the host memory there in order to catch a semaphore. If you put semaphores on the network, it's much easier accessible by the workloads or by the processes, and I don't need to create any cache trashing. So you get memory, you get compute on the network. Now I can start breaking applications and run applications on the network, not just on a CPU. And you have a lot of research around that covers government labs and leading universities around the world that does it. So that's from a compute. There is also areas around usage of RDMA for applications. We just helped to facilitate an RDMA course, a week-long course with 2 weeks of university teams competing one with the other in China. And we had 40 universities that participate in that. So we do offer courses, we do create competitions between universities, and we do bring ways of research. And if people are interested, I think there are 2 areas that they can look for. One of them is that they can contact us. And the easiest way to contact us is to send email to hpc@mellanox.com, and that's a simple way to contact us. The other way, there is an organization that runs multiple courses and does perform in interesting ways of research, which is the HPC AI Advisory Council. So if folks want to check it out, it's hpcadvisorycouncil.com. And there is interesting information and interesting activities for students and for university teams.
All right. Okay. So I think that's all. Thank you for your great sharing today. Thank you. Yeah.
Thank you very much.
Okay. So to all the audience, I think that concludes today's program. Okay. So we're the end, and we'll see you tomorrow morning. Thank you.